Okay, good morning to everyone, and welcome back to this second day of the first edition of the School in Machine Learning of Dynamic Processes and Time Series Analysis. I want to thank you. I want to thank the invited speaker and the contributed speaker for the school. And now I want to introduce Lyudmila Grigorieva. Is correct. She's a professor at Computational Statistics and Econometrics at the University of Constance, and she's an expert on reservoir computing and neural networks. And today she will talk about reservoir computing with application to time series forecasting, in particular application also on financial time series. So, okay, thank you, Lyudmila, and we can start.
Good morning, everyone. So thanks a lot for joining today's session, to all the participants that joined on this Friday morning. And let me, of course, start with thanking the organizers. That's a great honor to be invited to give a lecture on this great event. And I would like to thank, of course, Julia, Piero, Stefano, and Fabrizio for making this happen. And obviously, I will not be an exception to tell that well, it is really unfortunate that we cannot meet in Pisa, and I remember very well my last trips there. It's a great place, and it's really unfortunate that we cannot be all there. But maybe this way we can have more participants, so this makes it all much more even responsible to lecture here. So thanks a lot for this opportunity. So as you can see from the title of this lecture, we will be talking about time series forecasting with reservoir computing. And my goal for today will be to cover the three parts of this lecture. And I already want to make a comment concerning the third part. So it will be the function of how fast we go and how much we manage to cover in this given time. In any case, concerning the reliable learning with reservoirs, I will still give you some main results that we'll have there, and also will give you a reference to look into, but I still hope that we will make it up to the third part. So in the first part, we will talk about reservoir computing as a machine learning paradigm, and we will talk about how can one actually cope with, set up a problem and actually solve particular cases of forecasting problems in the time series context with reservoir computing. So you heard already beautiful lectures by Joseph and Krista yesterday, and you heard already about these wonderful links that one can find between reservoir computing concepts and the signatures. Here, my goal is to try to deliver the point why reservoir computing as a machine learning technique or paradigm presents a value, and how it can be efficiently, if you want, online, randomized fashion used for time series forecasting. And then I will move on to the second part, where we will talk about the application, a concrete one, for realized volatility forecasting, where what we will be trying to do is to actually apply reservoir computing systems to forecasting realized volatility time series for financial assets in the markets. And then, as I said, the third part, we will see how far we manage to go, will concern the reliable learning with reservoirs. Obviously, this is some hot topic these days on understandable, reliable, and explainable machine learning. And this is what we're also trying to achieve with our work in reservoir computing context. Okay, so let me start with the first part. And let me tell you, first of all, let me start immediately from what we call reservoir computing system. And let me already show you the very first slide, where there would be something that rings the bell already for people who have seen nonlinear state space systems ever in their work or analysis. And we see reservoir computer system as a state space system. I will also use this abbreviation RC from time to time so that we don't repeat and not make the slides heavy. So we are seeing this reservoir computing system as a state space system, in general nonlinear, which is given by the two equations. And traditionally we call the first equation state equation, and the second one will be observation equation. So this RC system is defined using the two maps, which we call respectively either reservoir map or state map, F. And we have another map, which is the so-called reservoir, readout map, which is this H over here. So what this system does, it takes the input Z's and it provides us with the output Y's. And we're working in the context where, in the setup where the Z's and the Y's, we assume that these are the valued sequences, basically discrete time input and discrete time output. And both of them, we assume that they're infinite, okay? So later on, we will restrict to left infinite sequences, but for now, let's keep it for the general statement like that. So what this system is doing, it uses the state map, which allows you to transform the input, taking the previous state into a contemporary state, xt, and it later on takes the states and transforms them through the readout map into the output. So these two objects, F and H, obviously, depending on how you define them and what properties these two have, will define the behavior of our state space system, and in particular, will tell us in which occasions actually we can call this general nonlinear state space system a reservoir one. Okay? So very good, and one piece of notation is that we are referring to this capital N as the dimension of the state space, and we call these XTs reservoir states. So this is usual in reservoir computing literature to assume that actually inputs are embedded into the high dimensional state space, which means that the N, capital N, should be much larger generically than D, which we reserve for dimensionality of the input, and M, which we reserve for dimensionality of the output at time t. Okay, very good. So we have lower dimensional input output, the Z and Y, with respect to the dimensionality of the state space. So this, what we need to account for is that what are actually the defining features of RC architecture. So which nonlinear state space systems we will call reservoir systems, and let's first address the question of the architecture. So what we want from this nonlinear state space system, so that we call it a reservoir one, and it falls into this reservoir computing paradigm. So first of all, that we will require is that the components of reservoir map, or think of simply a reservoir map, needs to be randomly generated. But we often assume that it is sparse, so its components are sparse, and it will be fixed for the whole further modeling process. So if you want, the F is given for us, is fixed, and it stays unchanged for good, okay? The next feature is that the static readout will be subject to choice. Let me not call it training yet. Depending on the task that we want to handle with this reservoir computing system, right? And something which is natural already to think about, and which Joseph already brought up in his talk, is that it is customary to hunt for readout maps which are linear maps, okay? Because in that case, obviously choosing a particular one given a data later on will be simple, and we will be able to accomplish that with linear regression. And the states are observable. So this discriminates these nonlinear state space systems from the standard ones, which you can find in filtering theory, where it is customary to assume that states are latent, and also to solve filtering problems in that setup, right? So here you have a schematic. So, well, this is what I will be using also in a couple of more slides, where what we see is that this F in general randomly generated, it takes the previous states, the input at time t, and it transforms it into the state at time t, out of which with a readout we can read out, right, according to the terminology itself, the output. Okay. So this map H will be something that will require some choice, and the F is fixed. So let's keep that for good. Okay, so what do we know about these systems? So you can think of the literature. Here I don't put the references that I do intentionally. The reason to do that is because you will have the talk by Juan Pablo in the afternoon, where he will address different links with the literature in control theory and dynamical systems theory. And he will give you references which actually give you explanation or possible links with reservoir computing literature for all these problems that you see here. So if you think of these reservoir computing systems as simply nonlinear, in general state space systems, we can look at them from a different perspectives, right? So first of all, we can look at them as models, so they can approximate or model, if you want, input-output systems. And this is where the main body of our work laid. We worked mainly with the input and output systems and used state space systems actually to model or approximate those. And this talks to the realization problem in systems and control theory. You can think of internal representation through latent states, which I already mentioned in filtering theory. Think of Kalman filtering, for example. Obviously, there are links, and it is natural setup, state space setup for dynamical systems theory. Here, we may think of the literature, a very broad one. And I don't know if there are some people here in the audience already present who contributed to that, but there is a whole body of work that has been done in dynamical systems in terms of so-called synchronization, right? And Juan Pablo will also address that more in detail in his talk. And something that we will be interested here will be input-output systems and a natural state space systems point of view when we're treating stochastic processes. What are the perspectives which we can take here and lean on when we're looking at reservoir computing systems? Obviously, you can think of them as recursive algorithms. So this is important from the computational point of view. Well, here you can think about multiple advantages. So, for example, since we're at the school which is devoted to machine learning for dynamic processes, you can immediately see that such a recursive model allows a very natural and neat treating dynamic processes and sequential data, right? Something that also Joseph mentioned is that you can you have this flexibility in terms of the tasks that you can solve. So, for example, you can treat different inputs and outputs of different nature, and they can be treated in parallel. Here, in order to imagine that, think of one input of one type, and then you're handling the outputs. For example, you are interested at the same time in classification, let's say, and regression, or you're interested in forecasting for a couple of forecasting horizons at a time. So all of that can be accomplished in that setting, provided that your readout map is simple enough, let me say it like that in a vague fashion, so that you can actually make that happen. And then it is well adapted to real-time online computing. Everything that suffices is that also your readout map, since the F is fixed and remains unchanged, also can be tuned, if you want, or chosen, or adapted as the new data is coming in, right? So immediately one can think that there are multiple estimation techniques which can be realized in online fashion, right, via just updates of the estimator. Okay, and finally, something that I don't spend time with, but this is a huge community that is involved in that, who are trying to develop reservoir computing systems in terms of their physical implementations. So hardware implementations of RC systems, this is non-negligible, and I would say that the massive community of physicists who actually are involved in that work. And I remember the first meetings on reservoir computing that with Juan Pablo we attended when we were trying to get involved into that. These were purely physicist conferences and workshops where people were trying to implement these RC concepts in using optic devices, electro-optic, and there were tons of different devices and hardware implementations for these kind of systems. And even in the last meeting that we had in Constance in 2019, we also had a part of the community attending who are worried about making those devices happen. Because that allows us to propose efficient in terms of the energy and speed computing device, right? So from computational point of view, these systems are important. You have vast literature on that. Also, I think that Juan Pablo will give you some references. What is the center of our discussion for today's lecture is looking at reservoir computing systems as a learning paradigm. So what we are interested in, and already you could see in Christa's lecture yesterday, she was introducing already a learning problem in the context of stochastic processes. And for example, she was handling the learning problem in perspective of calibration for various stochastic volatility models in her lecture yesterday. So our learning problem, these learning problems obviously consist vaguely put first in the following definition, if you want. So if we're looking at the learning models in agnostic environment or partially agnostic, right? Because ultimately what we want is also to use some knowledge about the process, at least, that we're trying to treat. And this also, I don't spend time on that, but you can look at Vine and E's talks, for example, where what he's trying to do is to put first principles coming from physics, and there are also people working in chemistry in that direction, and other hard sciences where they're trying to take the first principles in order to combine them with machine learning techniques, so that at least some partial information which we know from the centuries of, let's say, scientific work in hard sciences can be used, right? Here we are also will take that some partial knowledge into account. However, let me put it first in the agnostic environment. So for example, out of partial information available, we want to reconstruct or learn the unknown target. So what kinds of targets we may have? And let me call it target that will be changing from the context to context. So in dynamical systems, for example, you may want to learn dynamical system out of the low dimensional observations of it, right? So here the target will be dynamical system, and well, the partial information will be low dimensional observations of it. And again, I refer here to the talk of Juan Pablo. He will devote a lot of time in his talk to those questions. So here you can think of, for example, Takens embedding theorems and many classical results available in dynamical systems theory. What one can do also learn the attractor of chaotic dynamical system, also out of observations. So this was actually the first work that has been ever done in the context of reservoir computing systems by Jäger. And this is again the paper that Joseph already showed to you, where Herbert Jäger was trying to use the ESN's eco-state networks as one particular example of reservoir computing systems to path continue the Mackey glass time delay different. So basically he was taking the time series from the time delay differential equations, so via sampling, right, its solutions, and then he was trying to path continue. And this way one can see that actually you can learn attractors of chaotic dynamical systems, and this work has been continued also by the group of Edward Ott, and many collaborators of him, who are trying also to compare reservoir computing systems with LSTMs and different gated neural networks, right, which are so popular these days, in order to see whether you can actually solve the learning of the attractor more efficiently with one class in comparison with the other, right? So this is an ongoing work and very, I would say, lively. Input-output system. So what one can want to do is, for example, learn the input-output system itself, so I/O system, out of finite observations of input and output processes. So we may think of that as learning the filter. Then what one can also think of is learning stochastic process out of finite number of observations of its realization, right? So, for example, if you assume some kind of a Bernoulli shift structure, you can think of learning a Bernoulli shift. And for example, also a very prominent case will be what we will be doing today is actually trying to forecast. And we will see that how can one actually forecast is that learn the conditional moments of a stochastic process out of finite number of observations, or learn the optimal predictor, right? So if you're thinking of optimal mean square error predictor, then all we're doing is learning the first conditional moment of a stochastic process, right? Given, well, all the information up to the moment out of which we're forecasting. Okay, so we will be looking from the learning perspective at these reservoir computing systems. And let me already tell you what in these just 2 slides, we will set up a statistical learning problem for reservoir computing systems and in general for dynamic processes, okay? So let me give you 2 inputs. The input and the target will be stochastic processes. So think of the sequence of random variables defined on some probability space. We're looking at the discrete time stochastic processes. And let me keep the same notation that, well, the inputs will be random variables. The zt's will take values in RD, and the y's will take values in RM. And let me give you the class of functionals. We're in the dynamic setting. So what we're interested in is not functions, but functionals, which actually allow us to take the inputs, to take the valued sequences, right, left infinite to RM. So these are functional H that you see in front of you. And this class will contain such functionals measurable, okay? So this is a broad class, as you can imagine, and we will see that from a learning perspective, this will serve as just a reference for us. So let us define the loss. The loss will be a non-negative measurable function, which takes RM and takes us to non-negative reals. And let me define for you the statistical risk or generalization error, which is associated to a given functional out of that class. So statistical risk we will define as expected loss that we commit with trying to reach a target y with our functional h out of the inputs, okay? So I'm trying to reach this target with the functional h, and this is the loss that I commit, and I'm looking at the expected loss with respect to the joint law of x and y, okay? So the ultimate goal obviously is to learn to get this base functional, right? So base functional is somebody who solves a problem that you see in front of you. That means that's a functional which has the smallest associated statistical risk within the class. So again, this guy will be used for us as simply a reference, since in principle it's going to be infeasible. For deterministic tasks, one can immediately see that actually under realizability assumption, I'm not getting into that, or for deterministic setups, you're expecting the generalization error to be equal to 0. And this already tells you that there will be no overfitting happening, right? Because the better you learn, the better you are, and actually you can learn perfect. Okay, so we introduce the inductive bias, as it is called in machine learning. So we pick hypothesis class H of some admissible functionals H out of this broader class. And now what we're hunting for is restricted to this class, trying to solve the same problem. So we're trying to find the one that has the smallest associated statistical risk already in the smaller class, and the one that actually realizes the smallest risk, we will call it oracle functional or best-in-class functional. So this looks like an already more feasible problem, because hypothesis classes, you may imagine, can be chosen very small in complexity. So you may already hope for this problem to be solvable. Unfortunately, you're defining your statistical risk as an expected loss. So the law of the z and y is not given to you. You are in the agnostic setting. So actually, the statistical risk will not be available to you. And then you cannot even hope for setting up any kind of optimization problem, even if you make it finite dimensional, right? So what one does then, one looks at the following problem. Can I come up with a rule that allows me at the same time to pick a hypothesis class well enough, in some sense, and at the same time to propose some rule with which I can pick a particular functional within this hypothesis class, such that I commit the smallest possible excess risk, which means that I will be solving a statistical learning task. Okay, so the task will be, I want to design a hypothesis class and to figure out what is the rule to pick in this hypothesis class a particular functional so that the excess risk is as small as possible. Excess risk with respect to the best base rule with the smallest risk within the class of all measurable functionals. Okay, so let us look how we can decompose that quickly, and we will look in our lecture. We will be addressing these two parts separately, and we will see how in reservoir computing context actually looking into both these components of this excess risk makes sense and makes us believe that reservoir computing is a nice machine learning paradigm. Okay. So if you simply subtract and add the risk of an oracle, you can immediately see that we have the estimation error and approximation error. What that means? So here we have the class of all measurable functionals. And let's say I have here the best one. This is the base functional. I'm choosing the class of hypothesis functionals, a smaller one. It can be, for example, even finite, right? If you hope for a good luck in that, right? But it's not our case. And I'm picking here with some rule, some functional h. I'm not telling you how exactly. I can do it via random choice, right? Or just choosing one arbitrarily, right? So whatever comes to my head. And I'm looking at the decomposition of the excess risk. So excess risk that I will commit with respect to the base one will consist of how good in general is my class, which is measured by approximation error. So the best within this class, how worse it's going to be with respect to the one in all measurable functionals. And then the second one will be the rule with which I picked my h, how good it was, how far was it from the best oracle. So, okay, why do we call it estimation? I didn't tell you that there was a sample here, right, yet. I will talk about that a little bit later, but let me plot for you now. You can see this usual trade-off in machine learning, which doesn't hold true anymore once you're using the data and you're using over-parameterized models. This is something that Krista already addressed last lecture. And this classical picture will happen for our reservoir computing story. But if you think of deep neural nets or maybe even deep reservoir computing systems that we don't know, maybe there would be a different phenomenon happening, which happens for deep neural nets, right? So this is the risk, our usual R of H, right? And this is approximation error, which goes down with the complexity of H. The larger is my hypothesis class, the more hope I have that my R, the base one, will happen inside. So I can commit the zero approximation error. And then the larger complexity is, the higher estimation error is. So the more difficult for me is to pick the H such that it is close to the oracle one. Okay, so this is the usual one. Unfortunately, none of these are given to you, right? So all you can hope for is to design a rule of picking this H so that both are under control. This one is under control. And then this one, it will be controlled via choosing the hypothesis class well enough, right? So that at least you stand the hope of having this approximation error small, which obviously will happen for universal approximators, where you can guarantee that the approximation error can be made arbitrarily small, right? For some class of functionals. Okay, very good. So how one is using this rule? Usually using data approach. Here you may say that none of this is the data. This is simply estimation, if you want. This is terminology which is not well defined here. However, if you are now thinking of how I'm going to pick this functional within the class H, I can do it data-based, and hence I can use my empirical risk minimization, structural risk minimization, or other techniques to pick this H. And then we will be able to control the estimation error for that particular case. Approximation is a completely deterministic error. Estimation one, once you use the data, will be a stochastic one, and then you can look at it as a random variable, study its moment behavior, control its tail behavior, right? And in general, try to infer its law, right? So this will be an ultimate goal. Okay, so let us move on. And why makes us think that the reservoir computing systems are good systems, right? Because the approximation error may be made as small as one desires, due to the fact that we managed to prove that reservoir computing systems are universal approximators. Let me give you a list of the literature over here, and let me quickly browse through these references Also, I guess you will have more in the afternoon talk by Juan Pablo. So we managed to show in the context of input-output systems. So dynamical systems is a different story, right? For the input-output setup, in the category of the so-called fading memory filters, for different setups. So for example, for uniformly bounded inputs defined to negative infinite times, for stochastic almost surely uniformly bounded inputs, and here you have the corresponding references. So we have a couple of papers. We started from this one in 2018, where we showed the universal approximation properties of reservoir computing systems for uniformly bounded inputs, and then also for stochastic almost surely uniformly bounded inputs, and in particular for some specific family, which is a so-called non-homogeneous data file system, which I will not be talking about here, but think of it as one of the kinds of reservoir computing systems. And then we move towards the more popular in practice families, which is so-called eco-state networks, and other families, right, that may present an interest. So characterizing in general reservoir computing systems, which may serve as universal approximators under which conditions does that happen, was a body of work for a couple of recent years. And you can see here some references on that. So we managed to move pretty far with that. And also the last papers here, I draw your attention. There is a paper that Lucas Gounod and Juan Pablo, they came up with, which is so-called fading memory eco-state networks are universal, where within the setting of FMP and so-called eco-state property satisfied for eco-state networks, they were able to show that, well, actually ESNs are universal. So they made, let's say, a different, they worked in a different setup than the one that we had in this paper with Juan Pablo, just two of us, in 2018. So I just advise you to look at it. Moreover, there are also bounds for this, approximation error available. And this is this paper that you can see here together with Lucas and Juan Pablo. And that you can also find in archive approximation bounds for random neural networks and reservoir systems. So that part of the story, if you want, to some extent, is already worked out. And obviously, there is still much work to do for deep reservoir computing systems and dropping some constraining assumptions and making the results stronger. But if you want, this is all already set up. So this makes us think that reservoir computing systems or functionals are good hypothesis classes, right? So hypothesis class constructed out of the RC functionals present nice hypothesis classes in terms of the machine learning. Okay, so what are the features that we need to respect so that we have these universal approximation properties? So we have two main features, and one needs to keep them in your head. In some occasions, you are able to drop the FMP, and this is again the work by Juan Pablo and Lucas. Here, I just give you this one, reservoir computing universality with stochastic inputs, where they do not work in the FMP setting. However, they are showing the universality with respect to LP criteria, so not L-infinity, the one that we worked out. Okay, so nevertheless, it's very convenient to work with FMP people and ESP. So let us look at what that means. So if you want just to take a message home, ESP just encodes the existence and uniqueness of solutions, and FMP encodes, if you want, the continuity property defined in a specific fashion. So let us look at that. So these are the two ingredients that we need in order to prove some of these universality results that you have seen, and also which makes these reservoir computing systems also nice when you are thinking of treating the observations of dynamical systems. So eco-state property. So what that means, that actually at the presence of this property, we can say that our state space system, reservoir one, determines an input-output system, right? So any state space system which has this ESP property will define an IO system. So at the level of the system of the two equations, so at the level of F and H, right? So the system characterized or defined with this pair of the state map and readout map that we introduced, I can talk about the ESP as follows. So for any input, which will be simply taken from the DD valued left infinite sequences, right? So this D is from that sequence space, there exists, so DD is simply a subset of RD, right? There exists a unique Y, so think of the output in our state space system, such that the state and the observation equations hold, right? So this existence and uniqueness allows us to define the so-called state space filter, which is associated to the state system, to the F and H. And this filter, which just simply takes us from this space, the sequence space to Rm valued sequences, left infinite sequences, as simply as this, right? So this is easy to define, but we need to respect that the Z's and Y's are linked by the state equation via this equostate property, right? Okay, so ESP at the level of the state equation, I can do the same, but I can construct this time around the filter, which is associated only to the state part of my state space system. And in that case, it's easy to see that the one which is associated to the whole system is just the composition of the readout with the filter associated to the state part of our state space system, right, to F. So these filters are causal and time invariant. That's important for us. The terminology is suggestive. That's easy to see. Time invariance is just that the time delay operator commutes with the filter. And then the causality means that actually whatever, if your two inputs coincide up to time t, then also the filter at that time will be coincide, right, taking the two guys. Okay, so this filter, we can also talk about, the bijection between these filters and functionals, which is nice. And here you can see that actually filters is not something that we're using. We're using mainly functionals. Also for this presentation that I provided you through the hypothesis, in terms of the hypothesis spaces, we're working mainly with the functionals. And this is also a very convenient object in terms of universality. Why? Because it actually maps the sequences, right, into Rm. So this makes the domain of the HF and FH tractable, right? So for various things. So for universality, for coming up with bounds for this estimation error, for various reasons, it presents convenience to work in many occasions with these functions. So fading memory properties, what that is, that's a continuity property. So think of that this is a continuity property, basically with respect to the topology used by the weighted norms in, well, this VD and VM, which are these time invariant subsets of the weighted sequence spaces, okay? I'm not stopping on that in detail. All you need to keep in mind that we're entering these sequence spaces by the weighted norms. And we work with weighted sequence spaces, which are defined as such that the weighted norms are finite, okay? So all we need is to encode the continuity in this language, right, with respect to that kind of a topology, and to keep in mind that once you work with uniformly bounded inputs, for example, once you can show that you have this FMP with respect to one weighting sequence, you can also will have it for any arbitrary another one, right? So actually this doesn't depend on the W anymore. So these are these two properties that helped us to put this universality in action. It also will be useful for our learning tasks. Okay, let me move a little bit faster and let me tell you that for this ESP, there are some sufficient conditions that one can propose. For example, one easy condition for the ESP to hold will be to design such a state space system that, its states are in a ball of Rn, right? So, and the state map is contracting map on the first entry. So on states, it's a contracting map. And here you can immediately see, so this will imply automatically the ESP. And think here about one of the examples of such systems, which is not very easy, very difficult to design. And this will be the so-called equostate network. So this is the hero for our forecasting exercise as well. So this equostate network is given by, we have the state and space and the observation equations, which are given by the following. So usually keep in mind that this term is not present in the equostate network. So you may forget about that. This is in the most generally represented acoustic network. So what that is, the F, the reservoir map is given by the activation function, the sigma, by the so-called connectivity matrix or reservoir matrix A, the input matrix or vector, depending on who the ZT is, C, and then we may have this so-called input shift zeta. And then you have the corresponding scalings here, which you can obviously drop or just absorb into the C and zeta. And what is the sigma? This is just an activation function, which is a component-wise application of some squashing function. Think of a non-decreasing function with two asymptotes. So think, for example, about the tan H, right, or logistic function. So these could be examples of such a function. Okay, so in many occasions, we will also require, obviously, continuity of the function, right? And then the readout is as simple as what Joseph brought up. It will be just simply an affine readout, or if you work with a situation where you expect the outputs to be, let's say, 0, then you can also drop this A from there, but usually it's very difficult to actually guarantee that this A is equal to 0. Nevertheless, this will be the one. And now what we will be doing with the ESN, first we need to think of ESP. So what ESP actually, the sufficient condition for the ESP, how we can guarantee it for this ESN. So I remind you that what we are working with is the state value in a ball, which will be for the bounded sigma the case, right? Tan H, logistic. And then we need also the contracting F, which will be given to us by the Lipschitz constant of the sigma and the, for example, a 2 norm of A. So think of the maximal singular value of A, right? This will automatically give you the condition so that your map is contracting when the product of the two is smaller than 1. Okay, so this is, as you can see, the system like this, which already talks to the recurrent neural networks with the random weights, because A, C, and zeta will be randomly drawn. And as I said, will remain fixed. This part of the reservoir computing system will remain fixed. And it's also the W and A will be subject to some, let's say, picking, right? So here you can immediately say that we already picked also the hypothesis class for the readout functions, right? We restricted ourselves to affine functions, right? This is a static readout. Here we already did some kind of a component of our statistical learning problem, which we saw before. Okay, we know that they are universal. Refer to the paper and then the extensions to LP norms by Lucas and Juan Pablo, the two of them that I already mentioned. So it tells you that, well, on the level of the filters, right, in terms of the operator norm, you can actually guarantee the approximation to whatever accuracy you desire, right? So here the clue is to work with the FMP and with ESP systems, which is the equostate network under this condition that I already brought up, right? That you can, the sufficient one for the ESP to hold. Okay, so under these conditions, you can guarantee the universal approximation properties of the ESN. This is all to tell you that now we're going to be working with this kind of family, and let me move on now towards the learning input-output systems with RC. So before we were talking about the fact that we are working with stochastic processes, and there was no data there. So now we will be thinking of sample paths realizations, and we will think about the finite actually number of observations of those, right? So we will be working with random samples of a finite length. What we need for the data-driven learning now, how we're going to be picking this H within the hypothesis class of reservoir functionals, is all we need to do now, since the F is already picked, like in the case of the ESN, this I already told you that this remains untouched. What I will be doing here, I will be simply going for picking the readout only, right? And this is the guy that I need to learn. So one of the ways to choose it would be an affine function, but in principle, you can choose it with respect to any desired loss. Very good. So we have this training, and we will be thinking of this truncated empirical risk, which will just look at the discrepancy on a sample between the finite output, the finite number of the values provided by the reservoir functional from the finite input, trying to reach the goal y, right, or target y. Okay, so we will be using that in order to pick, for example, the readout. So in the linear case, you can immediately think that if I take the loss, which is a squared loss, right, the L2 norm-based one, then it will amount to using simply the linear regression to choose the H in the class of affine readouts, right, like something that we had before. Okay, so there are phases. So here I refer to the literature by our colleagues, so by Pietro Verzelli, Ashwin, Levy. They have this paper which is called, recently presented in the Fields meeting, Learn to synchronize, synchronize to learn, where they present these stages of how you can conduct actually learning with the reservoir computing. So the first one is the so-called listening phase. And this is quite now becoming conventional to call this process like that. So in this phase, since my reservoir map is fixed, whoever that is, think of ESN, think of other representatives of RC systems. All you are doing, you're feeding with the input and you're just collecting the states. So all that this thing is doing is just you're providing with the states, right? Think here even of the finite realizations, for example, of your stochastic process, which you start with the Z1, and then you're just feeding, collecting the states. So this is listening, right? We're listening to collect the states. Second phase will be fitting. So let us look at the general target first. So for the general target, once you pick a loss, which is not necessarily, obviously, even for the affine map, right? I can obviously not necessarily use the quadratic loss, right? So in principle, I can solve my regression task with respect to any other loss, asymmetric one or whatever I want. So obviously linear regression will be the case for the quadratic one. So in principle, I can say, I'm saying who is the class of my readouts. So for example, affine maps, right? Affine functions. And I'm looking for a minimizer of the empirical risk, right? On a given length of the sample T. And I may want also to penalize. So for linear regression, it makes sense to penalize because of the ill condition covariance matrix. And then you penalize with basically the norm of your W, right? With the Frobenius, you penalize the Frobenius norm of the W, and this amounts to the closed form solution, which is the Tikhonov regularization, right? So here will be one example. So feeding and draining, what we're doing here, I'm here giving already a target that I'm trying to match, and I'm looking at the discrepancy between the two, and this is how I learn my HN hat, already taking the sample into account, okay, or observations. So, okay, this I have done. Think of polynomial readouts, this is going to be the same thing, right? Think of any kind of other types of readouts. Think of neural network readouts, for example, of the standard neural network readouts from the reservoir state, right? This could be also one way to look at this. Okay, so what happens if we're now moving already towards the forecasting? What happens in this situation is that we are taking as a target now a shifted version of our input. So if I'm interested in the P steps ahead forecasting, then what I will be doing here is just replacing the YT with a ZT plus P, right? And your penalty may also incorporate the dependence on the forecasting horizon, right? You may penalize more for example, extreme behavior for farther away for horizons, right? So this may be done. Okay, so here I'm not providing any target, I'm providing already the shifted version of my input. And now we are moving towards something which already explores the recurrent nature of our reservoir computing systems. Because something that you may immediately see is that in principle, no one prevents us from feeding the output of the reservoir computing system back as an input once actually this output is constructed in a special fashion that it's actually the shifted version, for example, of your input, right? So it lives in the same space, for example. So you can actually feed it back into your state equation. Let us see how that happens. So in principle, this will be a direct forecasting, right? Teaching on the shifted P steps into the future series, and I'm trying to match the readout. So to match basically whatever comes from my state equation, the states, readout with my readout, with a shifted version of the input. So this is direct multi-step forecasting, right? Think of ARMA processes, the same thing people are doing, right? So solving the regression. Okay, let us see what will be working phases. So the work phase will be the following. So once I have now my readout, which is tuned, now what I can do easily, I can just get the output of my state space system, of reservoir system. I am giving you each time the true input, that's important. And I'm each time giving you as basically on the surface, right, the output of the reservoir system, which is mapped by my learned readout map, right? So for example, by my W hat and A hat, which are least squares estimators, right? So this will be an example. Already this incorporates the sample that it has seen before. So before T, right? Before before we do this, and this obviously you can do also in sample, right? For any T from 1, so you can basically look at the performance also in sample. So this we can push forward also for the out of sample, but the only thing that we need to provide is always the true input, right? And it just fits to us the output. Okay, so again, for the multi-step direct forecasting, it's easy what we will get. We will get just a forecast, right, of our ZT, P steps ahead, as an output of transforming by our learned readout during the training phase, transforming the states, right, and obtaining the output of the reservoir system as DT plus P hats. Okay. Now let us think of this recurrent structure of our state space. So this recursive model also allows us now to think about the connection between this and this, right? So whether if we are making this P equal to 1, we can actually refeed it back into the state equation and make this equation recurrent, right? So we're basically refeeding it back. So immediately, if you're thinking about the forecasting setup, it's going to be the case for the so-called autonomous regime, when what I'm having is that once the training is over, I don't have any more the inputs. I will be giving to you the next value of the input as a now via just computing the output of the previous step. Okay, so I'm obtaining the one step ahead forecast and I'm refeeding it back. If you're looking at this diagram, that's not very difficult to see that whatever comes from the given unit, the state at time t, up to t, we had the training, so we had the inputs available, and at t including, but after the t, the time series values are not available anymore. So what I'm doing, I'm just reading out the states and refeeding back into the state equation. So this autonomous regime will have many implications for dynamical systems, and this is exactly how, for example, the attractors are learned, right? So Maki glass path continuation is an example of that. There, what Jaeger did is he path continued for 2,000 steps, and he could manage to show that it beats the benchmarks, which are, for example, these nearest neighbors based techniques and so on, which exist in, let's say, classical dynamical systems theory. Okay, so we will look at the two types now of doing the forecasting. So one will be direct and another one will be iterative, right? Conventional, analogous to the classical time series forecasting examples. So let us see what we do here. So direct P-step forecasting will be something for which we know how to lay hands on, actually, because this is like a general target. So here there is no connection between, not refeeding back, no feedback from the output to the input of the reservoir state equation. So what we are having is basically the following problem. We need to learn what you see in front of you. So let me first introduce the time delay operator, which we already in principle used to define the time invariant filters. But let me tell you that this is simply somebody who shifts for negative taus my left infinite sequence to the right. Okay, so you're basically looking at the more past tau tau remote in the past values of the series. Okay, so I'm looking at the z minus 1, then the shift on basically -2 will mean that I'm going to be looking at the z minus 3, right? So it means that I'm shifting my sequence to the right. So what we're learning here in the P step forecasting, we're actually learning this. I give you the input, and that my target will be just simply the shifted input, right? So P shifted input. Using this time delay operator. So this is just simply formal. What one can immediately think that I'm learning the h of z, which is just a projection, right, of my basically t minus pz, right? So this is a projection of a filter which is given to me, defined through this time delay operator, okay? So I know there are tons of ways to write it down, obviously, right? So this is all equivalent, this is formal. Okay, now, what about another example of this? If I lay a structure on these, right? This could be, for example, a time series whose structure I have an idea about, or at least I can assume something. So what if I assume the Bernoulli shift? So the Bernoulli shift means that my z and eventually y's, because the target is just the shifted z's, will have a following structure. They will be given by some measurable functional g, which takes the left infinite sequence of random variables which are IID, okay? And they are in principle RQ valued. So this Q can be any you may think of, okay? So my ZTs will have a structure like this. So it will see all the infinite past of my Xi's, but my Xi's are IID. So then it will be time invariant, causal, measurable, and then what I need to require also that basically the L2 norm of my Z's will be also finite, okay? And what I also is, this means that when I'm working with the Bernoulli shifts, I'm actually working with a strictly stationary, or you may drop, for example, the strict stationarity, simply stationary inputs. And I may look at the forecasting exercise as follows. What if I feed just my IID people and I'm just learning the functional, this is the same thing, of now this IID, which is just a projection now of my G and this guy. So this is just to tell you that there are different ways in which I can actually encode the problem. Okay, so direct multi-step, what we're doing here, and this is well studied, right? So also it's very well studied for time series models, obviously for linear much more than for nonlinear. Nonlinear time series theory is in principle still the references are extremely scarce. Direct multi-step is what? Well, I'm generating simply, looking simply at the conditional expectation of my ZT plus H, where H is now forecasting horizon. So sometimes I denote P, sometimes H, bear with me. Conditional on the basically information set, right? Conditional on this FT, which is simply a sigma algebra generated by the states up to T, okay? So for this kind of problems, we have obviously this falls into this universality properties that for input-output systems which we had. And moreover, we have some nice characterizations of architecture of reservoir computing systems which lead to a nice, let's say, tuning techniques of the architecture for these kind of problems. So for example, there is a notion of forecasting capacity for which we have the bounds, which is set up exactly for this kind of a direct multi-step forecasting exercises. And this is our paper. You have the reference. We have this paper on memory capacity for recurrent neural networks with Lucas, Juan Pablo, and myself, which this summer we got it published in Physica D, actually in the special volume, which was handled by Boumediene, Hamsi, and by Jérôme Moulin. So, okay, so iterative multi-step, what will be that? here the problem is more difficult, as you can immediately see, because what we will be doing, we will be conditioning for the one step ahead, obviously on FT, which is given to us, the states are present because we went through this listening phase, right? We collected the states. However, for the farther away forecasting horizons, we will have to condition already by the FT plus one tilde, which is what? Which is a sigma algebra, which is now actually generated not only by the states, but also by one additional xt plus one hat, which comes from what? Which comes from refeeding back the zt plus one hat into the state equation and obtaining this x hat t plus one out of that. So this has seen already the W, the readout estimator, right? So this is already will be sample dependent and depending on the estimator we used for the readout. Okay, so results are available for linear time series models. There is a whole literature on that. Even there, this is not straightforward. So one may look, the literature is really rich. You may browse through papers on that, all the way from 60s and 70s. For nonlinear is not trivial. And moreover, the comparison between the two, what is better, direct or iterative, is something that is also a subject of vast literature, and people are looking at all possible ways to compare with respect to different losses and different measures. Okay, so let me now see what can be done. So if I'm looking at this direct multi-step, there are things that we can say. So in terms of universality, moreover, we can also tell something about if I give you a concrete ESN or with a concrete dimension of the state space, n, can you say something about its capacity to actually solve the forecasting task? And for that, you need to introduce the so-called notion of forecasting capacity, which is inherited, or if you want, follows the same logic as the memory capacity one, which was also introduced by Jaeger, co-authors, and the notions exist for recurrent neural networks. So for various neural networks concepts, you have memory capacity notions. So what we mean by that, if we're working with a concrete setup of ESNs, so recurrent neural networks of a type I showed you with random weights, all I need to assume is stationarity. And what I can tell you is that once you are using the inputs which are stationary and you are working with a reservoir system which has the ESP, and eventually this property that you see over here means FMP, so this would imply the FMP ultimately in this case. For example, ESN, which satisfy the ESP properties, right, for the given activation function choice, and the norm of this connectivity matrix, which is sufficient to guarantee the ESP. In that case, I can say that the stationary input would imply stationary states, which is in principle not true, right? And which we definitely need. If you look at this conditional expectations over here, this is something that would present a problem for us once these people, the stationarity of those cannot be established. Okay, so this is just a cute fact. And then via this time delay operator, you may think of the memory of forecasting tasks as we introduced, right? Via shifting the inputs or shifting the states to the left or right and matching them. Okay, so what do we know about memory capacity and forecasting capacity and how we can use them in order to tune our ESN once we're given a concrete problem at hand? So what one can do is, for example, the following. I define for you the memory capacity, which is a conventional already object in the literature, as follows. So look at this definition of the memory capacity, which is a standard one, which tells me, well, in principle, I should put here the braces so that think of that. So the memory capacity at the leg tau, so how well I am able to reconstruct the tau back values of the input with my output of the reservoir computing system or with my states ultimately, it tells me the following. It's defined as follows. So this is 1 minus the variance of the input I'm handling. And well, basically for people who think of the statistics, it's going to be just simply the R squared, right? or it's going to be the mean squared error that I commit trying to recover my past values of the z with my given readout, which is affine, right, and which is given to me by the W and A. So this minimization problem will give you the mean square error. So this is basically what you are having over here, right? Okay, so very good. For forecasting, we will do analogous thing. This predictive capacity was already mentioned in some papers on recurrent neural networks. So here I need to mention Sarah Martin and her group that already were, I would say, the ones of the first to propose the predictive capacities for recurrent neural networks, though for linear serialization, which is crucial, but for non-independent inputs, because all the literature before that, it mainly had to do with the IID inputs, right? And obviously introducing some kind of a dependence, I think of types of weak dependence, will present the problem in this setting. Okay, the forecasting capacity is now, how am I able to reach with the current input, so how the current input is represented by the delayed back, tau delayed back inputs passed through the reservoir computing system, right? So this is to make everything in T and not to account for the T plus P. So you may just shift whoever you want. Here we're shifting the states, okay? And here we're shifting the input. Okay, so the total memory capacity means that we need to sum up all this memory capacity for all the taus, right? So in principle, up to minus infinity, right? And this will give us these two objects. Now you can think of, for example, in those cases when these will be closed form expression available, you can, for example, use them in order to tune some hyperparameters of your ESN. For example, spectral radius of your connectivity matrix, all these input scaling, right? Input shift scaling. So this object can be in principle used, and depending on the task, you can use either this one and this one. The problem is that closed form expression is, of course, a tough thing to get. And that is why the usual game takes place for IID inputs and for linear situations when the state itself is also given by the linear state equation, right? Okay, so what one can do is obviously to write down in a little bit more short fashion, just keeping in mind that you are solving here ultimately, right, a regression problem. So all I do is plugging in the solution of the regression problem over here, right? And I'm think of the R squared divided by the variance. So this is, if you want the standard, the normalized error, 1 minus the normalized error that you commit trying to recover the tau past values and trying to forecast tau future values, okay? So here there is some discussion on that. This is not the topic of this lecture, but keep in mind that for linear and, for example, for IID and correlated also ones, you can have the closed form expressions available, provided that the gamma x, which is a covariance matrix of the states, is invertible, okay? So for that case, you can write this down and also make a couple of steps further, right, in that direction, and actually use that for optimization of your architecture of your ESN. What goes with the, obviously, if you have non-invertibility, there would be some ways. You have it in our paper, especially for linear situations. What is nice is that we have bounds also for nonlinear case for both these objects. So at least the bounds we know. So at least the upper bound, the bounds in terms of the largest value, right? Because obviously from below they're bounded by 0, but at least we have some idea about the upper bounds of these two objects. So the total memory capacity or the total forecasting capacity. How do we get those? Well, I just denote as gamma x the covariance of the states. I'm assuming to be non-singular, right? And what I can tell you immediately is the memory capacity for any tau will be bounded between 0 and 1, forecasting the same. This holds for any tau. Moreover, if I'm now thinking of the total one, so for all the taus, right, up to minus infinity, I can write down that for both those objects, the upper bound will look like in 3, where it is written down through the autocorrelation, autocovariance function of the input, these gammas, right? We are assuming the second order stationarity. And we have the H, which is simply the Toeplitz matrix, which contains all the autocovariance function values for different legs and defined as follows. Okay, so we are assuming that this H will be also invertible, and in that case, this bound holds. So you can see that this bound depends on the characteristics of the input we are treating, and the number of the neurons, virtual neurons, or the dimension of the state space that we have for our reservoir computing system, in this case, for example, for eco-state network, okay? So obviously, you can get something better here with this rho, which is just limiting behavior of the powers of this Toeplitz matrix, right? And the rho is the spectral radius of those for each L. So looking at the limiting behavior of the spectral radii of those Toeplitz matrices, right, powered, you can actually get something better. Nevertheless, this is much more convenient to lay hands on. And moreover, what we can do is, well, once you assume, for example, that these autocovariances are also absolute summable, right, then you can also come up with the expression of a similar type for spectral in terms of the spectral densities. Okay, this is to tell you that we can actually do tons of things here. We can talk about capacity, and actually I can forecast treating the task as a simple target, right? My shifted values of the inputs. Okay, so you can look into that paper. There we have different characterizations for different processes, and we have, especially for linear ones, we have well, these things worked out in detail. Okay, so let me now switch to the following one. So Julia, are there any questions?
No, till now, no.
Okay, so so the idea is that yeah, let me try to finish already this part, and then maybe we'll make a break before talking about realized velocity.
Ludmila, I have a question.
Yes.
Okay. I mean, in this case, okay, according to this result, we have that given some tau, we can study, according to this result, some, I don't know, optimality about the architecture of the reservoir computing. But this result can be used to say something on tau independently from the reservoir computing. I mean, tau in some sense is related to the memory of the input, right? So I don't know if we have the input Z, maybe, okay, we can say that tau is the memory of the process. For example, if Z are generated by some autoregressive process, I expect that tau is the order P of the process since it's related to that, right? So the question is, we can use this result to optimize tau independently from the reservoir computing, or not?
You see, there is here the twist of the game that you are talking about. So first of all, if you are thinking, for example, about the AR processes, so for MA, indeed, you can think of a tau as some kind of memory, if you want to think of the partial autocorrelation functions, for example, right? So there, the order of the MA part will give you actually the memory of a process, if you want to call it like that, right? So I would not see in which way you can turn the things here from what we try to do here, because you see, characterization of a memory of a process is the task by itself. So obviously, if you're thinking about the short-term memory processes, right, you have, or versus long memory processes, you have a whole literature on how you can actually set up the criteria to establish that your process is short-term memory or long memory, right? So these criteria are in many occasions non-trivial. So you have a whole literature on that. So I would not see why you need So I would not see how you can use the reservoir computing approach to study the memory of a process. Maybe I just don't see how this can be turned, but I would see how you can use the reflection of what actually comes from the reservoir computing of the input process as an idea about how much it can remember from the input. Okay. You can already see in this bound the reflection of this fact, because if your autocovariances obviously are behaving like for the long memory processes, right? So they're slowly decaying. You can immediately see that actually this sum over here, right, will be something which is nasty, right? So as in principle can be even unbounded, right? So this just tells you that it's going to be difficult to get to lay hands on the memory capacity or forecasting capacity as a measure once you are working with processes which have a weirdo behavior of in terms of the autocovariance. Okay, so it's more like that. Maybe I'm not seeing that right now, so maybe I will think about what you said, but I think this way to proceed that makes more sense. Otherwise, I just wouldn't see. Okay. So let us now, if there are no more questions, let us now move on towards the part that has to do with what do we do in the iterated situation, right? Because let me go back here, I did not repeat the slide, and let us look at the iterative multi-step and think how can we actually work in this situation. So if you think about this type of a filtration that we actually come up here with, and which comes basically from coming up with the sigma algebra generated by also the states that has in the estimated readout, is actually adds no information, right? So this is the information is contained already in the previous states. So what you will be doing as you move forward in your H equal to 2, 3, and 4, right? You will be actually learning just the deterministic object. Okay, so if you hope for learning a process and to recover indeed the forecasted value of your process, right, written down as in general for any H as such, right, then the problem is that exactly after the H equal to 1, actually you are just solving a deterministic task. So this presents a problem, and for that purpose, there is not much that we can do if we don't think about a very cute fact from, well, stochastic analysis, which tells you there does exist such a result, which is called the Doob decomposition theorem. So what this theorem tells you, and this will be an insight that we will be using for multi-step forecasting. So the Doob decomposition tells you that, well, you have a probability space, you have a filtration of F, and then you can start looking at some process Z, which needs to be an adapted one, with a condition that, well, basically the L1 has to be, in L1 it has to be finite for any T. Then we can say by this Doob decomposition famous result that there exists a martingale, right, and an integrable and predictable process, correspondingly M and A, with A starting from 0, such that, well, actually your Z, T can be represented as a sum of those, right, for all T's. So this process is decomposable into basically a deterministic, right, or integrable and predictable part, and into a martingale part. So something that comes in our head immediately that maybe this will be a way to fix our iterative forecasting. So let us see what kind of a justification of what we're going to be doing next we have from this Doob decomposition theorem. So obviously these AT and MT, and this is what actually you use in order to, in your proof, right, to verify the statement, are given as in this 5 and 6. So let us take a look what these people are, just for those who maybe are not comfortable with that, just to keep that these two objects in our hands. So the AT for any T will be just what? It will be the sum up to T, right, with the A starting from 0, of the conditional expectation, so the forecast of the J, right, provided all the information up to the J minus 1, and actually the previous real value z j minus 1, right? So this is a difference between the forecast and the previous value, out of which you construct the forecast, right? So the MT, what you have is, well, actually, that's a forecast that you constructed on the previous j, and its difference with the true value at j, right? So these two things we will keep now a track of, because this is what we will be using in our reservoir computing setup, okay? Very good. So this is the definition, which is something that one is used to. And now let us see how we can lay our hands on this. So let me take a training sample. So training sample are the ZTs with T from 1 up to T, capital T. Let me denote it by the end of the training set. Okay, so this is the length of training sample. And let me give you the FT, which is the sigma algebra generated by the states up to T, and denote by this ZT hat, well, nothing else but the optimal mean square error predictor of my ZT, provided the information from my states up to T, right? So here, a word of caution, if one will be changing the loss, right, then obviously this will not hold anymore true. And then if I'm thinking, for example, not about the quadratic loss, but the L1 norm-based loss, then I will be here modeling, for example, a conditional median, right? So this is intrinsic, this way of seeing the forecast is defined uniquely only for the case of the squared error, right? And this is nothing else, if you think for a minute, will be our base function. So this will be the one that guarantees for us the smallest statistical risk with respect to the quadratic loss, which obviously we will be modeling as the readout function, which is estimated already on the same T's, transforming the states, okay? Very good. So in the end of the fitting and training phase, what I can do, I can write down who these ATs and MTs are, actually. So let us take a look. So these ATs will be simply, according to the definition, sorry, before, not difficult to see, will be just the difference between the forecast and ZTs, right, minus 1. And here I will have simply the sum up to T of ZTs and ZT hats. What I can immediately see, well, if you're thinking a little bit about this is during the training phase, the discrepancy between the forecast that in sample I construct with my reservoir system and the true value itself. So this constitutes simply the differences between the two values. And you can think of that as, for example, residuals during your training phase, right? So these are just the differences or errors that you commit up to T. So let us denote this ZT minus ZT hat as epsilon T hats, right? And here you may think, for example, about the increments, right? And thinking of their marking in progress. Okay, so these epsilon T's denote in-sample residuals produced by the trained sands during the fitting phase. And we can also come up with its empirical distribution, right? Because what I can do, I can also say how these people are distributed. So this is all in sample. Everybody is seen. Okay, what do I do now? So I come up with this empirical distribution. Let me denote it as FT hat. This is quite standard, right? So here there is nothing to, let's say, talk about. So first step ahead, what I do. The ZT plus 1 is the sum of these two people, where the ZT hat is the forecast provided by the reservoir computer, right? For example, ESN, somewhere I even explicitly write ESN, but it can be any system, right? And let us see what this AT plus 1 is. So AT is given to us during the training phase. It was all available. And now I have the forecast provided by the RC, or my conditional expectation, minus the ZT. The MT plus 1 is the MT, which again is explicitly available from the training phase, plus the true value at T plus 1 of my process, right? Minus the ZT plus 1 hat, which is the conditional expectation of T plus 1 given the FT. So what is the problem here? So AT plus 1 is available. This is a forecast. This is explicitly available. and I can compute who the A t plus 1 is. What is not available is the true series at time t plus 1. Okay, so now we think a little bit about this fact that we had before and use the following theorems. So this is the residual, right, at t plus 1, which is not available this time around because the true one is not given to us. And let us think about these two theorems, which will allow us to push things through. So the reasonable idea is now to think about these epsilons that we will be observing in the out of sample, right, the residuals, the true residuals, as the ones that should behave in some fashion similar to the ones that we observed during the training. So this we can obtain in a standard, let's say, with a standard approach, doing the following thing. Let me introduce the Mallows metric, or sometimes people, obviously it's more popular to call it Wasserstein, for any R larger or equal than 1. So in principle, this is a R metric, right? Let F denote the set of distribution functions, satisfying, well, this property that you see. And then for the two distribution functions from this class, the Wasserstein metric will be defined as follows. And this is something that you have already seen in Christa's lecture yesterday. These were also the metrics that she was working with and showing the results with respect to. Okay, so this metric is something given to us. And now let us look at the theorem, which tells us how the asymptotic behavior for our bootstrap, because what we will be doing now, we will be applying the bootstrap technique, meaning that I will be picking via sampling with replacement the residuals from my training phase in order to use them as true innovations in my t plus 1, t plus 2, and so on forecasting steps, right? So this is what we call the bootstrapping. And there are a couple of facts for the bootstrapping that we need to respect. So for example, for that to hold, reasonable to work with stationary processes. This is something that we have. And then to hope for at least uncorrelatedness, but better for IID of the residual behavior of innovations during our training phase, right? So this you can achieve ultimately empirically via just testing, right? And looking at the behavior of them. But theoretically, let us look what that amounts to. Why do I have the tools actually to replace my innovations by the residuals from the training and use this bootstrap technique? Well, I give you the true distribution of innovations, whatever that is, and I'm giving you the empirical distribution of residuals, FT hat. So it holds that in probability as t goes to infinity, well, this Mallows metric or 2 Wasserstein metric in probability goes to 0 between the two distributions, okay? The empirical one that we have from the residuals and the one which is theoretical or the true distribution of the innovations. Okay, this is something that one can prove, and this gives us now the means to actually lay our hands on the thing and now to do the bootstrapping. We'll look at this and then we make a break, okay? Because we are 1 hour into before the end. So I give you the NB, the number of bootstrap replications. I'm collecting these epsilons will be NB number of these sets of P long residuals from my training. So I'm sampling them with the with just the replacement, okay? And I'm coming up with these collections of the epsilons from the training. And now what I'm doing here, for the one step ahead, I can do the following. So I'm replacing now the term that was missing. So the innovation that we didn't have available for the T plus 1, I'm replacing it from the one that comes, one denotes the corresponding forecasting step for the residual, right? So this is truly, if you want, decorative, because I can label them the way I want. They're sampled with replacement in any case. So I'm adding these residuals from the training phase, following, well, the justification that I showed you before, and showing that if T goes to infinity, well, these two distributions will be actually close to each other. Well, in terms of the criteria that I showed you, right? So in probability, we can show that. Okay, so now the ZT plus 1, J, will be simply the sum of the one that is explicitly available and the one which is contaminated by the residual from the training. and we denote it by tilde, z tilde. So now I can construct the mean forecast over all the NB replications of my Bootstrap. And let us take a look what I get. So for the one step ahead, if I'm just undoing the thing using the definitions before, and I'm just ending up, that's not very difficult to see, with a true ZT plus 1. Okay, this is the forecast by the reservoir computing system at the time 1, plus the average of my residuals over the NB replications. So I here put approximately, but actually what you can do, you can show that as NB goes to infinity, right, with that theorem that we respect the closeness of the distributions in the sense of 2 Wasserstein metric, right? I can show that this will go in probability to just simply ZT plus 1 half. So here you can see that doing it this way or doing it direct for one step ahead, asymptotically is the same, right? So, however, you can do now something better because for the 2 steps ahead, you will not be able to do this because already now this one, which is contaminated by the residual, will be injected into the state equation as an input. So you will have a nonlinear function of it. So obviously this will not hold anymore, and you will have to sweat to actually show that in some sense this converges to something. Okay, let us see that in action. And well, bear with these tildes and hats. All you need to see is that now the J tilde 1 that I have constructed in 9 gets injected as an input into the state equation. And I'm reading out now the output, basically ZT plus 2, which is J labeled to correspond to the number of the path, right? Index of the path. And here, if I do the same trick, I will be able to see that I can indeed construct the mean forecast, whose asymptotic behavior I cannot show you now, right? But the mean forecast we are able to compute. And this way I can do over the whatever horizon forecasting horizon I'm interested in, and with respect to any number of the bootstrapping replications I'm coming up with, right? So the more the better, due to the asymptotic behavior that we actually want to reproduce, right? Okay, so we are doing that for P, and let me finish now on the last thing, and then we make a break, a short one. Now that all that I did tells you that is not only that I can give you now the mean. So for the, okay, let me put it like this. For the direct multi-step, the only thing that is available to us is I'm standing on the P, and each time I need to train my reservoir computing system for the P steps ahead. So if I'm interested in 5 steps ahead, then all I need to do is to train for 5 steps ahead shifted inputs. If I'm interested in 10 steps ahead, only you need to change now and to retrain, right? Or for example, to come up with this linear map that, for example, solves a couple of problems at a time. However, aiming at 5 steps ahead into the future, you have no access to the 1 steps ahead, 2 steps ahead, 3 and 4. Doing that iteratively, you will have them all, right? So moreover, you will, in the P steps ahead, you get just the mean forecast. What you get out of this is also density of the forecast, which is a big thing. If you're thinking of that for a minute, in terms of the reliability of your forecast, one is hunting for obviously forecast intervals. So one wants this. If I know the true distribution for any P forecasting horizon of my Z, right, of my forecast, I can come up with a forecasting interval, which is given to me just simply by the inverse of my CDS, right? So here, alpha, the significance level, if I'm interested in alpha 0.5, this is what I'm going to come up with, okay? Very good. Now, having said this, for the bootstrapped one, I can actually prove that if I'm constructing the forecasting interval through the bootstrapped ones, and I denote by tildes, these ones that come from the distribution of the forecasted disease, and I'm coming up with the Monte Carlo approximation of those, or if you want the empirical distribution of this forecast, I can also prove a theorem for you that, well, the mallows distance, or the 2 Wasserstein metric between the distribution of the forecast for each P step and the one that comes from the Bootstrap in distribution goes to 0 as the t goes to infinity. Okay, so this gives us a justification for our densities, also for forecasts, and now we can have the full picture in our head. Okay, so now goes the part 2, and let me start here, and then we continue maybe in 5 minutes.
Okay, perfect, Ludmila. See you again in 5 minutes, yes.
Okay, so at 10:42, something like that.
Okay, something like that.
Very good. Okay, we start.
Perfect.
You can hear me?
Sure. Yes.
Okay. So here we are with the second part, where what we will be trying to do now is to put all this work that we've done for a particular application for forecasting of realized volatility time series. So what is motivation for that? Well, it presents an interest both from the econometrics point of view, but mainly, okay, let me tell you that the interest that we had behind that was twofold. First, in terms of econometrics, we've been working for a while with multivariate covariance models. And the problem there, for example, for dynamic conditional correlation models, DCCs and VEX and so on, for those who know that literature, for others, just think of the multivariate, let's say, non-parsimoniously parameterized models. The complication was always that it's only for extremely simple specifications that we can actually solve the estimation problem. And putting those models to work at forecasting was giving us troubles in empirics. So one interest of using reservoir computing systems for that was coming from that, if you want idea. And the second one is that we were looking for a time series where we can show off the power of reservoir computing for something which is non-straightforward, presumably difficult, that is difficult also for econometricians, is known to be difficult to handle due to stylized features, to the short available training samples, right? And this is one of the big advantages of reservoir computing systems that we try to advertise, right? Because all you need to do is actually tune just the readout, unlike what you need to do for recurrent neural networks, LSTMs, and so on, where you need to estimate all the weights of your neural network, right? So where obviously the availability of a long sample size plays a huge role, here we try to go for the situation where we don't have it. Okay, and then we realized quickly that it was not as simple as that, because it turns out that the benchmark models, which happen to be linear models and constructed in some way, in some ad hoc manner, in most of the cases work very, very well. So, we spent some time even a little bit regretting about trying to go for that kind of a time series before actually we figured out that there are ways in which you can beat the benchmarks, which we're very happy about. And we did it for univariate and multivariate situations. And these are papers, again, with Lucas von Pablo, myself, and there is one more co-author, Alexander Kukharenko, who actually helped us with computing all the covariance matrices, the realized covariance matrices for multiple assets, which is by itself a heavy work, right, to do. Okay, so very good. And let me make an outline here. I don't want to spend much time on this because for people who know what the realized variance of volatility is, it will bring no information. For those who see it for the first time, it will be quite difficult to grasp the 3 slides that I have. All you need to keep in mind is that you're modeling, so having some risky asset, you are observing, you are assuming that the observed log price of this asset is driven by some latent log asset price Y, and then which is usually modeled as what you see in front of you. So you have a predictable drift process of finite variation. You have sigma, which is a Cadillac process that already Joseph was talking about in his lecture, strictly positive square integrable process. And then this W is a standard Brownian motion. So if you think of that and you're assuming that your observed log price is just the latent one contaminated by some noise. So for example, microstructure noise or any other kinds of noises present in the markets, then obviously you can, using that kind of a specification, and sometimes even relaxing it to using that the absence of microstructure noise, everything is even simpler. You, for example, can come up like in 11 with this continuously compounded return, which just looks at the return. Think of this K as a day, right? And think of dividing the observations within the day in J pieces, right? So you're observing, you're sampling with J, 1 divided by J frequency, the returns, the prices within your day, and then you are coming up with the returns as just the differences of the following one with the preceding one, and obviously depending on how fine is your frequency of sampling, the more compounded returns you will have during the day. This is only to keep the notation in place, and there are good features. For example, you can come up with a definition of quadratic variation, integrated variance. All we need for that now is only to keep in mind that there would be an estimator of the realized variance that is in this formula 12, which is nothing else but you're taking 1 day. Let me already show you for 1 day. This is the case for 1 day. So I'm sampling the prices within 1 day J times. So for example, if you separate with a frequency 1 divided by J, which is 5 minutes, you will have 78 observations during the day. So you will have 78 compounded returns during the day, if I remember well. And then you can come up with an estimator of the realized variance simply via, let's go back over here, computing the sums of those compounded returns during the day squared. So this will give you the estimator of a realized variance, right? For covariance, you will have to do the same thing, but then this time around you will have the, well, RR transpose, right? The usual covariance, sample covariance estimator. You have tons of those covariances. All you need to preserve is that they will behave in terms of their convergence to quadratic variation, and then even in many occasions their behavior in terms of their distribution is known, right? So asymptotic information we have about, for example, this object, the difference with the quadratic variation and divided by this integrated IQ. Okay, very good. So this is to tell you that there are tons of estimators. We are not talking about that. For those who are not in the literature, just keep in mind that there will be some time series which we try to forecast, right? And this will be a particular one. Okay, so these estimators, we know that they're sometimes difficult to compute. However, the values are available. So for example, you can univariate ones are available, multivariate you have to sweat to compute, but nevertheless, this is the data that you can lay your hands on. Okay, so this is what we are hunting for. This is mainly for people who have seen it for the first time, which I think will be a minority, but nevertheless, we have people also coming from dynamical systems. So this is simply a realized variance, right? Computed within the day using the 5-minute sampling frequency and plotted for all the days between the 2000 and 2018. And obviously, we can see sharply the crisis between 2008 and 2010. This is the series that we would like to focus. So you can immediately imagine that, okay, stationarity is one thing, but we have tons of extreme events which are present in this time series, right? Finite samples, and we will need to cope with that somehow. Okay, so what we need know how difficult is to find the ESN, because we talked about existence, we talked about the direct multi-step where I could possibly use, for example, the memory capacity to tune it. The problem is that we would like also to put it to work for iterative forecasts, which is something that works better. So in that case, can we hope that the ESN will work better than the benchmarks? All we need for that is a piece of information about what are those people, right? So for example, going back to Piero's question about the memory of a process, right? Here there would be some criteria looking at which you can actually establish that your realized variance behaves as a long memory process. So here you have a collection of these facts, which I just browse you through, and this you can find in the book by Jan Beran. He has there a collection of different tests, and if you want empirical criteria to conclude that the process with which you are working is likely to be the observation of a long memory process, okay? So doing this, repeating this for realized variance series, obviously will give you a signs of a long memory behavior. So what you can do in this case, you can, for example, this is how your sample autocorrelation function of logged realized variances will look like, right? So this gives you an indication that actually the decay of your autocovariance function values obviously is not what you would expect for short time processes, right? So obviously you don't have here a cumulative. Okay, so having said this, partial autocorrelation function looks like this. This is all explorative and descriptive. This just gives you a sign that maybe you should work with long memory processes and already figure out the theory for that kind of an input process behavior. So what do we know about long memory and short memory processes is that we can either characterize them as such using autocovariance function or, for example, spectral density functions. There are these technical details here, which, for example, Jan Berendt, who is a colleague of mine here in Constance, by the way, who is an author of all these books on long memory processes, he is the one who figured out all these different equivalence relations and the different links between different ways to characterize long memory processes in terms of the spectral density and autocovariance functions. And even though he's working always in frequency domain, he finds it much more convenient. He also figured out all these things for autocovariance simulation as well, which is much more, I would say, applicable once you want to work in the application, right? A concrete application for time series forecasting. Okay, so roughly that if you want to get the story short, and you want to think of the autocovariance functions, all you need to look at is this 13, right? So if you work in the setting of a stationary process, you can call it long memory, long range dependence, or strong dependence, if there exists a constant, some C gamma, such that the limiting behavior of your autocovariance functions for legs as they go to infinity, right, is given to you by this C gamma H in the power minus alpha, where alpha needs to be smaller than 1. So all these criteria that we have seen before is actually comes down to asserting this, right, or trying to recover some empirical signs that actually this 13 is likely to. Okay, so benchmarks. Obviously, one benchmark will be the long memory model itself, time series model itself, which is the so-called ARFIMA, where what you can do, you can simply write down your processes. You can it is given here, where simply you are introducing the fractional difference operator, which is written through the gamma functions, summed up to infinity in the relation over here, and you're writing down basically your backshift operator as a fractional difference one, and then you're applying to your innovations, well, basically the lag polynomial theta L, which is a standard one, for example, for MA processes, right? This is nothing here to, so this is quite standard part. All that is new here in this ARFIMA is actually this fractional difference operator over here. Estimating this model presents a problem. So if we want to use this ARFIMA for realized variance processes, there are all these techniques which go back to Hosking, 1981. So Granger also worried about estimating these models. The problem is that once extending them to multivariate setting, they are the estimators that you can come up with for these kind of processes. They depend unfavorably on length of a sample that you have, right? So actually, they're very sensitive to the finite sample situation where the sample length is short. Okay, so this is something that one can think of a benchmark. Another benchmark, and with a given time that I have, I would spend little time, but so I'm not sure if Corsi is still in Pisa. This is Julia who has to tell me, but since the last time that we talked, he was still in Pisa. Hello, nice to see you. So we never, I mean, I saw you in the conferences, but we never talked to each other. So I was not sure that you were in the audience. So this is actually the author that you see in front of you of this model, which happened to be a very fruitful model, I would say, allowing for tons of extensions, modifications. So it has become an industry, or as Joseph said about the JL lemma here, the HAR is an example when one model can make a career. So it's really great. So to see that there are results like this was also empirically work very well. Okay, so having said this, there is tons of modification, but the idea is simple. You are coming up with a hierarchical model where you assume that there are three underlying processes which drive the behavior of the monthly, weekly, and daily realized variances. So, and you are just setting up AR models for those, right? Assuming that on the daily level, the observed variance behaves basically according to the usual daily return process relation that you see in front of you. And then via just combining them or aggregating these AR processes, you're obtaining the so-called HAR model. What we are doing here. So the daily observed realized volatility is the one that you have available. The weekly one is computed as RV, means the observed ones, is computed as an average over the week of the values of the realized volatility or variance. And then the monthly one denotes over the working days in a month. So people go crazy about figuring out different legs, maybe not 22, maybe 20. Here I'm showing to you just the classical, let's say, the Fulvio's invention, right, in 2009. So, okay, what is the idea behind is that if you're thinking of aggregating AR processes, and this is an exercise that I show sometimes to students, if you generate the two AR processes with two different coefficients, which both need to be close to 1, you can actually obtain that kind of a behavior of autocovariance functions that I showed you, which looks like a long memory process. So the idea is exactly that, trying to aggregate the AR processes in order to obtain a process which, even though is not formally a long memory one, behaves as such, or at least shows empirically the signs of long memory process. So if I just aggregate these latent, if you want, a vola that we have over here into one model, what we're getting is just summing up those people. We're getting this model in 14, or in a more short way in this 15, where this is as simple as such. So even for people who are not coming from econometrics, it's easy to understand what this model is doing. You're looking at the value for the next day of your time series, which is realized volatility, daily one, and you're giving it as simply the linear combination of the daily one on today, you're interested in tomorrow, the weekly one of this week, and the monthly one of the current month, right? So all the days, working days, up to time t over 22 working days prior, right? And then what you do, you just add an innovation, and then one has to be careful, right? Because, for example, setting up in the previous models, you need that they're, for example, left tail truncated. So there are all these things that you need to be careful. However, empirically, well, nobody actually worries much about that. And you can, looking at this model, which has now only 4 parameters to estimate, right? You can do it also with least squares. And formally, technically, this is the same as AR22 models, because I remind you that we had the aggregation of all these models, right? And if you're thinking of all these people over here with different coefficients, this is actually the AR22 model formally, but very parsimonious, because it's parameterized only with 4 parameters instead of 22 plus an intercept, right? Okay, so this is a benchmark which is tough to beat, right? So good for Fulvio, but for us, that was not as easy, right? So, so what we did, right? We are using the ESN now for that purpose, and let me go for just single ESN for that task. I want to forecast this time series with that concrete model. So what I'm doing here, I'm estimating my W and my A with respect to the squared loss. So I'm solving least squares right? I eventually will regularize it because my states will be, the covariance matrix of the states will be ill conditioned. However, all the ingredients other, I will try to remain randomly generated. So A is randomly generated sparse matrix with some connectivity degree. Jaeger proposed this kind of an ad hoc criterion for picking the connectivity degree of a matrix, which, as you may imagine, as n goes to a couple of thousands, tells you that this matrix is extremely sparse, right? So the sparsity degrees is 1 minus the connectivity. Okay, so we are generating the C, for example, from uniform law. So how to generate those? Here I need to refer to all our colleagues from Reservoir Computing community, because there is a massive work that has been done concerning how exactly to construct those A's and what laws to use once you randomly draw the entries of the connectivity matrix and this input matrix C in order for a better empirical performance of reservoirs, right? So I did not tell you how to generate, right? So, and this, even though indeed you can generate them randomly, there is a massive work on that in that direction. So, for example, Peter Tino, who was yesterday and who was mentioned by Boumediene, by the answer of Juan Pablo to Boumediene's question, he worked on circular reservoirs. So, for example, the connectivity matrices, which allow some cycles, right? Or, for example, just 0-1 binary elements in the reservoir elements of a reservoir matrix. So you have tons of plenty of different versions. In this particular application, the performance didn't gain anything from just, so what I did, I just used the Gaussian law, and then also with co-authors we tried other distributions, and actually this didn't lead to anything, right? So any improvement. And then I'm taking a uniform for the C, and also whether you are making it between 0 and 1, and then you apply some scaling and between -1 and 1. So this actually does not improve or worsen the performance. Okay, so is this model better? So it is, first of all, more flexible. This I need to bring up because, well, in this hard situation, for example, the usual strategy that you may want to use, and this is why this model is actually makes sense to use, is to apply the least squares criteria, right? When you estimate. So you're coming up with the betas as the least squares estimates, right? Solving the linear regression. So you're just solving the linear regression, taking the specification 15, and you're getting those parameter values. Okay, here we may play the same game. We can use the least squares here, or for example, we can use other losses. So for example, asymmetric losses, where we will not have the closed form solution, unfortunately, but running a gradient descent on only the readout is not expensive, so that you can still do. We did not do that. We still were obsessed with keeping the readout as simple as possible and estimation technique as simple as possible. So we were using the least squares. Okay, we have this availability of this bootstrapping for multi-step iterative forecasting, which we just prepared the grounds for. And there are a couple of comments here that I would like to make, and this talks to the paper by Anastasis, who was also in the audience. I'm not sure if he is now, and which we try to hello, which we try to think on how to put together with what we're doing, because as you will see in a minute, even in such a simple case as forecasting the realized volus, you have a problem. Whatever comes out of the reservoir through an affine map from the states, it needs to be non-negative. Okay, so if you're thinking of simple least squares, non-constrained one, there is no guarantee that whatever comes out of that model will be non-negative. If you're thinking for a minute about this hard model, this actually will be also the case, right? But due to the specification, this actually rarely happens, that via this truncation of the left tail of these innovations, and simply on empirical level, via estimating just with least squares, you will never get actually the RVT+1 as a negative one. Okay, So, however, for us, it's not the case. You can get the negative outputs because the states are just transformed through the affine map, right? Taken by the affine map, so to the output. So actually, no one gives you the guarantee that these people will be non-negative. Talking about Anastasi's work, the same problem remains put about the structure preserving for working in multi-dimensional simulation when you want, for example, to forecast the covariance matrices. So you're working with objects which basically live in a cone of positive semi-definite matrices. And here what we're doing, we're just going for the transforms that actually preserve the positive semi-definiteness. However, one step beyond that is this non-Euclidean learning setup that Anastasis, for example, is working out, where what they try to do, and this is something that we're trying to find the relations with, is to show that once you're working with a universal approximating concept, there are ways in which actually via transforming in some way your initial object and having this universal approximator in between, you can actually obtain the structure preserving machine learning paradigms. So for example, neural networks. So this could be a great thing for us, just to see how the semi-positive semi-definiteness may be preserved via the sense. So I think that Juan Pablo will talk about that a little bit more, but this is just to put a relation with this ongoing work. The same applies for neural networks, as you may imagine. So structure preserving is a problem. Okay, so let me go now for something interesting in this remaining time of 20 minutes. And let us see how we're doing that. So, okay, we're going for least squares regression for our readout. And all we're doing, we're training our ESN on the one step ahead forward version of our inputs. And well, for Tikhonov regularized version of least squares, you have an explicit closed form solution, which is great. Moreover, something that we rarely use, but which is in line with online learning techniques, which we will talk about now, is also the fact that this estimator that you see in front of you can be actually online updated. So you can compute it without having the need of computing the inverse of this monster here. You can actually update this estimate as the new observations are coming in an online fashion, keeping the same properties of an estimator OLS kept, okay? Very good. So in principle, online is not a problem, and also for big data is not very popular now terminology. Let me put high volume, high dimension settings. This estimator is something that one can use efficiently. Okay, so this is what we have. And now we're doing the forecast. So this slide is very short because all I want to tell you is that we're constructing our forecast using this dupe decomposition inspired technique, right? Where whatever comes out of the reservoir gets injected, contaminated by the residuals from the training phase, right? Keeping in mind those theoretical guarantees that we had about the empirical distribution convergence to the true one in the Mallows metric, okay? Okay, very good. So this is what we're doing. We're constructing now the forecast. So this is completely mimicking what we did in the first part. And let me make one more comment before I go to the more interesting part, which has to do with the fact that the way we actually fight this structure preserving deficiency of our ESNs is actually by doing it in a very straightforward fashion, very similar to what people are using for realized walls in general. So what you do, you're not modeling the RVs, so realized walls, but you're modeling the log transformed series of those, right? So automatically what happens is that taking the exponential of whatever the ESN gives you as an output will give you something non-negative, right? So this is an easy trick in which you can actually guarantee the non-negativity of your outputs of your ESN when you're treating a series with some constraints, right? Just transform it. So power transforms are very popular in treating various time series, not only coming from financial applications, but many others, which are used or common to use when you're working with time series, which exhibits non-Gaussian behavior. And what you want to do, that's also a good reason to transform it with power transform when you want to use a linear model, right? Because when you take the logs, then, well, think of any nonlinear multiplicative model, taking the logs makes the process linear. So this is one more motivation for using, for example, the log transform as one of the family of the box-Cox transforms. So you're taking whatever series you are handling, and you're transforming it with a given lambda. When lambda is up to you to choose 0, you're just log transforming. And now this is what you feed into the ESN. So the ZT using our convention is something that we're feeding. The problem is the following. Once you want to get back the true forecast of a true series, and this is standard known in that literature, is that you cannot just go with a naive approach. Naive approach would be what? I get my forecast, H plus T plus H, and I just compute an inverse of my transform, right? And I'm getting an approximation of my forecast out of that. So this is a naive approach. So for linear models, you can already think that maybe that could be something plausible one could do, because you're not expecting for, let's say, your process to be basically something extreme happening, right? However, for nonlinear ones like the ESN that we have, obviously this problem will be present much more and will be more pronounced, for example, for hard. But even there, this is standard to do. So the problem is that once you're working with power transforms and you're thinking of convex functions, immediately what comes to your head is Jensen, right? So what happens is that you will get with a downward biased predictor, with respect to the one that you are hunting for due to the Jensen, right? So all these transforms obviously are convex, so you are in trouble. Okay, so how to fix that? And obviously for nonlinear simulations, this will be more pronounced for obvious reasons. What you want to do is to bias correct. So bias corrections, vast literature. So you can think of, there are these papers that I edited, I guess, somewhere here. So you will have the references in the end. I will show them to you so they are recorded and you can take a look. So all the way to 2017, there are even more recent 2019, 20 papers where people worry about the need of this bias correction. We don't question that. And all you do, you just expand conditional expectation as a Taylor series. And here you're coming up with a particular correction for a particular choice of power transform. So here for people who are using any machine learning techniques for time series, this is very good to know that actually in many occasions one hunts for figuring out the representation of your features so that the learning task is solved easier. However, one needs to be careful with respect to inverse transforms, which can lead to this, for example, behavior like here, in terms of the, well, using the classical Jensen code. Okay, so this is what we do for the log transform for all the models we compete with. And finally, let me move towards the application. So we analyzed all these different variations of univariate, multivariate cases. Let me not get you tired with that. All you need to keep in mind is that this has been done for univariate and multivariate situations. For multivariate, you are computing just matrices instead of, so covariance matrices instead of just realized variances or volas, right? However, everything in terms of the scheme remains put. And okay, this is what you get out of the HAR. So the HAR, and this is thanks a lot to my master student who helped me with coming up with these tons of different figures for various forecasting horizons and so on. To Lucas, nice to mention him here. And so here you have 1 step ahead, 2 steps ahead, 5 steps ahead, 10 steps ahead prediction with HAR. Let us take a look what we get out of one ESN, right? So out of one ESN, I'm getting something like this. For people who are new to econometric field, they can say that the problem is solved. This looks more alike to what we were observing there. We are done. Well, actually, it's not enough, right? You need to show that in terms of some performance measures, this behaves better, and also the significance can be established. The problem is that this one is obtained and something hidden under the rack, also optimizing for hyperparameters. So we needed to optimize either via grid search or for basically using the usual optimization techniques for spectral values of connectivity matrix, the input shift scaling, and the input scaling itself, right? So this, as you may imagine, ruins the magic of ESN for this kind of a series, because you need to choose it very well. So we are working with universal families, but this just tells you existence. And also, if you have the approximation errors, it just tells you that, well, actually, the error is under control, but go and find one, right? That does the job good. Okay, so what do we do about that? If you don't want to make the story long, and one can tell you, well, in terms of the error, already let me tell you that the HAR here and ESN are, in terms of statistical significance, are indistinguishable. So the heavy optimization for hyperparameters, tuning, choosing ESN, going higher dimension is not beaten by a simple linear HAR model. So practitioner would say, why would you bother going for neural networks, right? Or ESNs. Okay, what kind of way we use? So something that we played a lot, and this is just for those who are into this literature. Also, you have these consistent loss functions, which respect the ranking between the models, and consistent ones, symmetric. So we have like 15 of those, and we managed to show that actually, once you tune your readout with respect to quadratic error, nevertheless, you can show that you are superior in performance with respect to other measures. Okay, and this is something that you would like to have. So you're estimating your readout, solving least squares, but then at the same time, you can show that you are superior to HAR or to Arfima with respect to Q-like error, to mean absolute error, and all the other asymmetric consistent losses proposed by Patton. Okay, let me now, in this remaining time that we have, stop on something which we think constitutes the main contribution, if you want, of this part, because it will be short to explain, but it is heavy in terms of the notation. So what I will try to do is not really to drive you through all the symbols that we have in the slides, but more to give you an idea. So what is the magic of the essence that we try to explore? Without tuning the hyperparameters of the network, what we would like to do is to remain in the setting where I can draw my connectivity matrix for any, let's say, given to me spectral radius according to some law, well, arbitrarily, and then to use that for forecasting, right? That's the magic of the essence. So we would like to have those state maps randomly generated, fixed, and not to worry about the spectral radius, for example, of that connectivity matrix much, as long as it is smaller than 1, for example, right? The singular value is smaller than 1. Okay, so what one can do, if I want to do it like that, let me go for the experts technique. So what this technique is doing, I will generate many ESNs with random choice of spectral radii, randomly drawn input masks, or these input matrices C, which transform the input, right? And I will just put them in a pool. So this can be done in a matter of milliseconds, right? The whole training, because what you do, you just solve the linear squares for all these, let's say, 10 ESNs, 20, you can think of many of those. You don't need to train anything much because it's just these squares. And this talks a lot to this talk that we had yesterday in one of the contributed talks, where I think it was Luigi was the name of a person, Longo, I think. He was presenting the same approach, but for LSTMs, right? When he tried to average the LSTM with, for example, gas models or other factor models. So what we're doing here, we're using this method of experts, which is the so-called boosting or online technique. The idea is very simple. a player or a forecaster is looking at the forecast produced by experts. So K experts, and what you would like to do is to construct as a player a forecast based on those. So people use that in policy making, in weather forecasting, and you can think about the simple toy examples of that situation. There are good guarantees for that, which tell you that a player now will use the H-step forecast from K experts. For us, experts will be ESNs, randomly drawn, right? Think of this K, for example, 5 ESNs. And what I did, I took the spectral radius 0.1, 0.2, 0.3, so I sampled, right? So I did not worry about choosing the right one. And then what I'm doing is once the true observation is revealed during the online, let's say, proceeding through the time series, I'm looking at the loss that each expert incurs with respect to the true time series value. And I'm looking at the loss that the player occurs once he used all these K forecasts and came up with his forecast using those K with respect to the true value. So these experts techniques, there's a huge literature on those, is mainly Shapir and all these big names. So I think Bianchi, and there are many people who worried about that. I will give you some references also. The problem is the following. So now after K steps, so now after the T steps, so here this TOS means T out of sample, in which I'm proceeding with this H step forecast, we want to see what is the cumulative loss of the player over all the T steps when on each T I was using the K experts to construct the forecast. So this cumulative loss is not under control because it becomes available only as you move over the T, right? So the goal here is the following. We want for all the forecasts to minimize the cumulative loss of a player. So we want to have a loss, which is a minimum over all the experts for all the forecasting horizons. So you may think that this is something that is very natural to do, and yes. And what one can also say is there are great results in terms of the learning theory, which can provide you with the results in terms of the regrets, uniform vanishing of these regrets over the choice of the outcome sequence, right? The forecast and the choice of the expert's advice. So there are uniform guarantees for these regrets to be under control. And actually you can show that by a simple scheme, you can come up with a technique which actually gives you a minimizer of this problem via iterative scheme, such that discrepancy between the solution of this problem and the one that provided by this strategy is of the order of OT. So this is a great uniform convergence results. Okay, so families of successful strategies. So how can I come up with an iterative strategy which would give me something which is close to the solution of this problem, which is a tough one, as you may see? Well, it turns out that simply weighting, and that's why weighting forecast, for example, is important, gives you already the strategy with which you can actually suggest the solution for such a problem. Not any weighting would go. And here goes the hedge algorithm, which is an invention of Shapiro and Freund, where they propose the so-called exponential weighting, which automatically gives you the nice statistical guarantees in terms of not only the mean behavior, right, the closeness to the solution in mean, but also the uniform over different choices of experts and choice of the forecasts that they provide. So let us look at that. So don't look at this notation. This is heavy. You will have this talk recorded, so you can just stop, and then also our preprint will be soon available where you can find all these details. All we will be doing, let's say I'm taking the experts as ESNs, I will be just correcting the weighting for the forecasts that are provided by the ESN according to the exponential weighting, which penalizes those ESN instances that did bad on the previous step. So if my ESN did bad on the previous step, I will give you a smaller weight, and the way I penalize that weight will be according to the exponential scheme. So if you want, this is just putting people together through the weighting scheme, coming up with a linear combination of those, such that the weights sum up to 1, and correcting those weights in an iterative manner as you move. What that leads to, let us take a look. And something that I would like to point out, there would be some experts that will be doing for short term and some that will be doing for long term. So you will be able to penalize them independently. So one can get a higher weight for some forecasting horizon and smaller for another. So what are the statistical learning guarantees that we will enjoy? Well, these are the results that tell you that actually you can control. So keep in mind that this is in terms of the sum. So if you want to get an average error, you need to divide both parts by the t plus 1, okay? So this tells you that this will be upper bounded, so the regret, the cumulative regret, or the solution that you come up with your iterative scheme, in terms of this solution of that minimization problem that I showed you, the discrepancy between the two will be upper bounded by this right-hand side, which is a function of the number of experts, so how many ESNs we had, learning rate, and how many steps out of sample we were exploring. And obviously, you can even come up with the optimal learning rate, and then your bound becomes this, divided by the t plus 1, and you will get a very nice and neat bound, which can guarantee you the performance, right? In terms of the, let's say, the probabilistic guarantees. Okay, let me show you how it looks, and then I will take maybe 5 more minutes, if the organizers allow me, just to give you an outline of this third part, and maybe next time when I present, or maybe my co-authors present, they will spend more time on that. So this is when we use, so we have, let's 1, 2, 3, I don't remember how many, 4, 5, 6, 7, 8, 9, 10 experts. So these are 10 different ESNs with state maps randomly drawn. So connectivity matrices randomly drawn. And the only thing that we change is by going via grid with respect to the spectral radius. Keep in mind that we don't violate here we violate here in some occasions the ESP, but the condition which is sufficient for the ESP, right? But keep in mind that that condition that they showed you was only sufficient, so it's not necessary. So empirically, even some reservoir computing systems which violate that that condition actually perform very well. Okay, so we do it like that, and something that is natural to imagine is that the higher the spectral radius is, the more importance, the more the current state will remember what happened in the previous states, right? Because the connectivity matrix will have a spectral radius, which is, for example, close to 1. Think of AR processes, right? So the higher is the phi parameter for AR processes, the more you remember what happened before, right? So in that sense, what we want is that for the crisis periods, we want to see that the ESNs with a smaller spectral radius catch up. And for calm periods, actually, the more you remember from the past, the better you forecast into the future. And that's actually the case. Because here we are having this simple non-exponentially weighting scheme. And here you can see that actually for faraway forecasts, this is the one, this is actually the two extreme cases that take over. The one with the highest spectral radius and the smallest, this is the evolution of your weights, which are given to your ESNs, right? So here you can see that actually there are only two extremes that do the job. For shorter forecasting horizons, for 2, for example, you can see that here there is a peak and there is the one that takes over, and there are others that get the lower weight. So you can see that these weights are distributed according to the dynamics of the time series. Okay, this makes a lot of sense, especially if you use the exponential weighting, because in that case, things become even more apparent, even for the long-term forecasting periods. And if you can see here, for example, in the end of the series, there is this dynamics that changes there is like a switch of the dynamics of a time series, and you can see that even for the faraway forecasting horizons, there are the weighting, the ESNs that get more weight actually switch, right? So one takes over the other, and others actually get the zero weight. Okay, so this is to tell you that there is a way to put those people together, and unlike the trained neural network or aggregating estimated models, this is much stronger because we generated the state map randomly, and we just put them together. So this is very cheap. Okay, and now, well, we have these extensions. This is statistically significant. Let me not stop on that for different measures. Let me just browse through that so that you have all these slides recorded, and you may want to stop that on the video just to explore a little bit for different indices, for IBM, for FTSE, for S&P 500, we have the same behavior in comparison. So even though the eco-state network sometimes standalone does better, we can show that actually these are the experts, this boosted hedging that does always the best and is statistically significant. And here you have the Fulvio's model in blue for different forecasting horizons. And here we have these this Bauer and working model. Okay, in this 5 minutes, just let me quickly tell you what is this third part about. And I was expecting that I will not have time for that. But let me remind you, and there I will finish this picture that I started the discussion with. So what we talked about is that the approximation error was under control. However, I did not tell you anything about the estimation error. And actually this part tries to control this estimation error once you are picking the functional within this class using the empirical risk minimization. And having a control on both, you can talk about the trade-off of the estimation and approximation error. And then you can go either for the higher complexity of the class at the price of higher estimation error, but lower approximation error, or you can go for a longer sample size and a smaller complexity of a class at the price of higher approximation error. So this trade-off will reappear, right? So we don't have the trade-off itself for explicitly available, right? But we have the two things separately already treated in these papers that I mentioned. And the last paper, which goes with this third part, is called Risk Bounds for Reservoir Computing. And it is a paper with Lucas and Juan Pablo, and it has been, well, this week accepted to Journal of Machine Learning Research, which we're very happy about. So just to give you an idea, let me go down all the way because you have all the components available. And those you can see in the paper. And as you can see, I would need 1 more hour to cover that. These objects you have already seen. So let us look, for example, at this relation over here. What we want is to control the estimation error, what I showed you in this trade-off of approximation and estimation. And actually, this is achieved via uniformly bounding the difference between the training error and generalization error in probability, okay, in terms of the characteristics of the input. So these coefficients have to do with the weak dependence assumptions for the input and output processes that we have. Also, they incorporate the structure of the reservoir computing, because in these constants, there are hidden the complexities of the reservoir computing families, which you can actually evaluate using, for example, the concept of Rademacher complexities, which I did not introduce, but for those who know, that will say something. And here we can say that in terms of the probabilistic guarantees, we can start talking about reliable machine learning, because if you can control that the difference between the quality of your training and the behavior of your functional out of sample in probability will be under control up to this accuracy that you have here given as a function of, let's say, features of the reservoir computing and the input-output processes, then you can talk about reliable machine learning paradigm. So here I would like to stop. Thank you very much, and sorry for taking a little bit more time. And I advise you to look into those papers and references that I brought up. And in order so that it's recorded and you have them, let me just browse through them like this, so that you have them in the recording and you can go back to these slides if you need to later on.
Thank you, Ludmila, for your talk, for your clarity. And there are some questions. Someone that want to ask something?
The improvement you obtain versus R, can you show again just the
You mean the empirical performance or the
performance? Yes. Yeah, exactly. So I mean, it's clear that it's difficult, right? I mean, so the model is especially well performing on a short forecasting horizon. So it appears that it becomes the overperformance becomes more significant. Maybe in this example, I don't know if it's something systematic over a really long forecasting horizon.
So I got your question.
Did you try to go even beyond, despite the fact that it doesn't make a lot of sense, of course, to forecast beyond 30 days, but I mean, still.
So here I need to make a remark, and that's a very good question. What you see here, this is an average performance, 1 step ahead, 2 steps ahead, 3 steps ahead, and so on, up to 30 steps ahead, over an out of sample period, which is around 1,500 observations. So what we're doing, we're moving and we're just collecting the errors all for 1 step, 2 steps, and so on. So the thing is that when you're doing, for example, the model confidence stat test, where you're trying to compare, so Diebold-Mariano test, where you're trying to compare the predictive performance of two models, this test, it loses its power the farther into the future you go. So actually, having here them so distant doesn't mean visually it looks very good, but it doesn't mean that actually in terms of the statistical significance, that you are gaining something in comparison to what you have over here. So from the picture, indeed, this looks like it behaves better as you go further into the forecasting horizon, and that's indeed the case. But this gives, I would say, a bit wrong picture in what is the gain here in comparison to what gain we are getting here. So both this and this are statistically significant, but I would say that one has more trouble showing statistical significance here in comparison to what we have, for example, for step 2. But you are right, one can go further into the future. The problem is that my fear is that if you go further and further into the future, the best forecast, it will be the unconditional mean that will give you the best forecast.
Yeah, absolutely.
Which you can see already from this asymptotic behavior of these errors, right? So at some point, they will not grow anymore and they will be just constant, right? So our ESN, the best that it can do is to learn the mean, right?
Mean, yeah.
But you see, this will take a while with this bootstrap technique. While if you're doing that for direct multi-step, you will not get anything like this because you are forecasting too much into the future. So you are assuming that in 50 days, you will be able to forecast something. While in this iterative scheme, you're injecting the residuals from the training, which tells you that it will remember the dependent structure in the residuals. So they are not correlated, but they are non-independent. So they will bring something. So this happening of just going to the mean will happen much later.
Another question still this one is really very practical and I mean a bit naive. Of course, it would be especially good to be able to have a medium-long forecasting horizon which is reliable for example, after peaks, right? I mean, after moments of high volatility. I mean, if you could.
Yeah.
So, I mean, for example, I mean, you may ask a certain moment this year, it wasn't clear whether there was a bump in volatility. It wasn't clear whether it was just going to be the beginning of another burst or just some normal decay. So if you don't make the average over the all conditions, but you make it conditional on, I don't know, the highest quartile or quintile of the distribution of the volatility, is the performance the same?
I don't know. It's a simple answer to, but it's a very good question. I don't know.
It's especially a question which makes economical sense. I mean, for example, is it really in that case?
You're right. I mean, we could possibly look into that, right? Because
okay, just curious.
No, that's a very good remark. So this is something that we will have to worry about, because for us, first we thought of this application as one, if you want something that we felt comfortable with, instead of going for signals of voice recognition or voice recordings or time series that coming from usual computer science benchmarks, right? So we thought that maybe it makes sense to work with series we already know how to handle, but this is tough one to forecast, obviously. So, and now if we want to present it as a tool which obviously works very well, then we need, of course, to add all these economic reasoning, right? For example, for multivariate setting, we're using those for portfolio analysis, right? Construction, and we're looking at all these, Sharpe ratios, and because otherwise we cannot convince, let's say, econometrics community, and this is that this makes sense. So this is a very good remark. This makes sense to think about that. Thank you.
Thank you for your lecture. It was wonderful.
Thank you, Stefano.
Lyudmila, Gabjut is asking if you have some notebook to share, maybe with slides later, with the empirical analysis that you show.
One more time, could you please again say?
I mean, do you have this empirical result in some notebook or similar to share later with the applicants, with participants?
Yeah. So I will put things on GitHub, right? So this will be something that, and then I will distribute the link. So I will send you the link.
Perfect.
Yeah.
Thank you, Lyudmila.
So maybe, we need to wait like maybe 2 weeks before the preprint shows up, and then I make it public, and then I post it, and then I distribute it. Yeah.
Sure. Maybe there is a question by Fulvio.
Yes, thanks. Well, first of all, thanks a lot for a very nice talk, really nice.
Thank you.
Just a curiosity, how robust is the reservoir computing in respect to the noise in the input? I mean, we know realized volatility is not a perfect proxy for the volatility. It's a good approximation, but it's not perfect. So when there is noise in the input, how much is robust the reservoir?
You see, it depends on what you mean by robustness, right? So how you define the robustness? So robustness in what sense? In the sense how much the performance deteriorates when the noise increases in the inputs. So for that, you see, theoretically, I cannot tell you that I can immediately say, but what one can possibly do is to simulate, let's say, the time series out of Arfima or out of HAR, and then to contaminate that with some, for example, Gaussian noise, right? Or let's say chi-squared, right? So that we are not, so we are still left tail truncated, right? So Okay, so for that case, one could possibly explore that empirically. That is true. What I know for sure is that if you're thinking of types of a noise which are like white noise, so uncorrelated but not independent, there are works that have been done by people from computer science community and physicists where they were using these benchmarks. So for example, for voice recognition, these pronounced digits, where it is conventional to have those benchmarks contaminated with different types of noise. And this, I would say that in terms of, artificial contamination with some noise with structure, this has been already empirically verified. What I cannot tell you is on the level of theoretical derivations. So one should look into that, right? But I hope that then the same conclusion will hold for realized vola, because there is no difference between, let's say,
sure, no, it was.
Yeah.
Because I was curious about your forecast. It seems that the forecast of your model seems more noisy than the forecast of the HAR. So I was wondering if this is due to some amplification of the noise in the inputs.
Okay, I see.
By the nonlinear box of the reservoir, in a sense.
Yeah. So I can answer to that question. So you see these figures that you see here. Let me go back to the one single ESN. So this is what you refer to.
Yeah.
So you see, this is in purpose that I showed that you actually are overfitting here. So what you're doing here, if you would enlarge this series, you will see that what ESN is doing after the massive tuning of hyperparameters and perfect training is that it just remembers what happened yesterday. So it's basically a deterministic behavior of a forecast, right? And this talks a lot to this dupe decomposition story that I was presenting before, because all you're learning here is basically a deterministic function, right? So a conditional expectation as a function. So after a very fine-tuned ESN, it produces something like this. If I don't fine-tune it, and I just generate it the way we hope for the reservoir computing as a concept to work, then you can immediately see that I will observe something like this. So forget about that this is an aggregated a couple of ESNs. Even if I take one and I generate just one randomly, I will see that something that you have for HAR, right? For 2 steps ahead, this actually behaves more and more mean-like, and then it becomes smoother and smoother and smoother. So actually, this would be something that you would expect to see, right? This is what. So this would be the case for ESN, not perfectly trained, and this is what actually we want, right? So indeed, that's the case. Okay. The problem is that you see, if I take any ESN and I just create it randomly out of the blue, it's very difficult to hope that it's going to be exactly the one, despite its universality, that will solve a task for a particular time series. So that is why putting them into this online iterative, if you want, aggregated scheme makes sense, right? Otherwise, I would need to do some kind of pseudo out of sample. This could be done. We also tried that. So you take a training, you leave a part, then you optimize there the hyperparameters. But you see, the problem is that then crisis, after crisis, when do you take this? So we didn't want to do that. So, but that's a very good question. I would be surprised with that kind of behavior as well. Thank you.
Thank you very much again. Thank you.
May I also ask a question?
Yeah.
Do you hear me?
Yes, I do.
Yes, because I moved to the countryside and I'm in the Alps now. So it's just a reflection on the question before. Robustness actually means continuity with respect to perturbation. And we know for reservoir computers with respect to which perturbations one has continuity.
Well, for example, almost surely uniformly bounded, right?
Something which is close in a certain norm, then we know that the output does not change much. And this is how I interpret robustness. And I would say this is relatively well understood, right?
Yeah, well, if you, for example, think of the case when you have your noise which is uniformly almost surely bounded, for example, right? Or cases like that, then of course we know how to treat that.
Yeah,
but I
so
think
this
this is
type
not
of robustness. I know that this was not asked, but this type of robustness one knows. So if you have
Yes.
a perturbation of such a type, then it is clear that.
Yes.
Yeah.
Yes. I think that the problem is, since Fulvio is working with situations where I guess assuming the uniformly almost surely bounded noise is not really something that one wants to get a robustness with respect to, right? Or because
no, I just wanted to add.
But
this,
you're right, Joseph.
Have continuity properties.
Yes,
with respect to perturbation.
Joseph, that's a very good point. Indeed, yeah. You're right. That this would be a way to phrase it. Yes, indeed.
Yeah,
that's a very good point. I didn't somehow think of that, but you're right.
Thanks.
Okay, it was just this remark.
You're right. Yeah, that's a very good one.
Thank you for your talk.
Thanks a lot, Joseph, for being here, despite being in the Alps.
In the middle of the Alps, I hear these great talks. That's good.
Okay, I mean, I think everybody now envies you.
Okay, thank you, Ludmila. Maybe, okay, we are a bit late, but we can start again with the contributed talk session at 10 past 12, just to have 15 minutes of break. So, okay, thank you again. Let's take a break of 15 minutes and see you later. See you soon.
Thank you.
Thank you very much. Bye. See you.
Welcome back, everybody. Let's start again with this contributed talk session of this second day of the school. It's a pleasure to present Daniel Ollek, that's right?
Yeah.
That is going to present a work on the unit-root test combination via random forest. So thank you, Daniel, and let's go.
All right. Yeah, so I'm Daniel Ollek from the Deutsche Bundesbank, that is the German central bank. This is joint work with my colleague Carsten Webel, also Deutsche Bundesbank, and then Luca Nocciola, who moved on to the ECB. We are very much practitioners. Carsten and me, we are working in the seasonal adjustment department of the Deutsche Bundesbank, so we are mostly concerned with seasonal adjustment of time series and related to that, understanding some of the characteristics of time series in general. Today I want to talk about how out of a set of unit root tests, we can find out which tests are the most reliable or most trustworthy, how we can combine unit root tests, and all of this will be done with the workhorse random forests. And first, some idea. I guess most of you will know what a unit root is, but let's assume we have a time series yt, which is made up of a combination of a deterministic component and then xt, where xt depends on past observations via some parameter alpha in. If this alpha now is equal to 1, we say that xt is a unit root process and yt inherits that property. And this would be a regular unit root. Given that we are working in seasonal adjustment, we of course also are interested in seasonal unit roots. That is now xt depends on xt minus tau. And tau is a seasonal frequency, so it would be 12 for monthly observations. And both of them are of concern to us. Now, assume we have some time series here as an example, the industrial production in Germany is calendar and seasonally adjusted, and we want to know, does it contain a unit root, yes or no? And we run a few tests, some for regular unit root tests, some for the seasonal unit root. And what we see now, if you look at the regular unit root, is that the tests don't concur. There's some tests saying there is no unit root, then there's some which definitely assess that there's a unit root, and then there's one test where it depends on the chosen significance level. whether we would say there's a unit root, yes or no. And in this situation, the question arises, which test is the most reliable test, or which combination of tests should we trust? In the second case, where we now look at the seasonal unit roots, obviously, or not surprisingly, given that we are looking at a seasonally adjusted time series, all of the tests find that there is no unit root. But still, in this situation, why would we need 6 different tests? Wouldn't 1 or maybe 2 tests suffice? And this is our motivation for trying to find out, okay, which tests are the most important ones, which tests are the ones that we can trust, and maybe can we combine tests to make it more robust. And the first one is the idea that just like forecast combination, we think that combining statistical tests will probably also be more robust and maybe improve the classification accuracy. Random forest, that is like one machine learning algorithm that allows us to which can give us an idea of how to combine tests. And I will talk about how we can do that. They come with something that's called variable importance measure. It has been adapted for many other machine learning algorithms as well. But as we'll see, for one particular version of random forest, the variable importance measures take into account the specific structure of the features of interest, here the unit root tests. And then I'll show you how we would go about to find out which tests to combine, how to find out how many tests we need for a robust classification. So, and due to the time restrictions, I just mentioned that our study is a simulation study. Our goal is to simulate data that are somewhat representative of reality. And because you could, of course, do something like power analysis and size tests and so on. But what we want to understand is, in reality, which tests are the most reliable. And basically what we do is we start with the data or the time series from the M4 competition, a very large prediction competition done, I think, 1 or 2 years ago. We automatically fit ARIMA models, a class particularly well designed for economic time series. And then we combine the log-spline density estimation for the coefficients with a normal to anything algorithm to then simulate time series that are somewhat representative of the time series that we observe in the M4 competition. What we generate is series with a unit root, series without a unit root, and the same for the seasonal case. We look at 3 time series lengths, 5, 10, and 20 years of data. And for each subclass, we simulate 10,000 series, yielding a complete set of 120,000 time series. And then on this time series, we run the unit root tests and the seasonal unit root tests. And our features in the next step will be the p-values of the tests, and the response, that is our target variable, will be whether the series contains a unit root, yes or no. And as we simulated the series, we know the reality. I guess most of the tests are well known. Basically, the ADF test employs the first formula where I said that the unit root is given if alpha is equal to 1, and the augmented Dickey-Fuller test is basically just a test for this parameter after some transformations. And then the ERS, PP, and ZA tests are just variants of this simple unit root test. KPSS test is somewhat like a perfect complement to the ADF test, in the sense that the ADF test has the null hypothesis that there is a unit root, while the KPSS test assumes there's no unit root. So in practice, often we find that, or we just from a theoretical point of view, it seems like a good idea to combine a KPSS test with one of the ADF family. And then finally, a completely different kind of test is the Gomez-Maraval algorithm that tries to identify unit roots in an ARMA model or two types of ARMA models. And for the seasonal unit root test, we basically just use the seasonal variants of the test that I just presented to you. As a side note, the Canova-Hansen test is not going to be part of the results that I'm going to show you today, because either it is a very, very bad test, or the implementation that we are using is bad, and we're currently trying to find out what the problem is. So if any of you have some experience with the Canova-Hansen test, I'd be happy to hear about that. Okay, and then we apply all of these tests to the simulated time series, and the most important column here is this. So this is the accuracy overall time series that we simulated, and you can, I highlighted the best tests column-wise, and you see the GM test, the Gomez-Maraval algorithm, and the PP test achieves the highest accuracy overall simulated time series. If we break it down a little bit, and I've broken it out, here's all length, and then 5 and 10 and 20 years of data, but I've also broken it down by series only not containing a unit root and series containing a unit root. And what we find is that some of the tests are really unbalanced in the sense that they are only good for either in the case where there is no unit root or there's no unit root. The most balanced tests are also the tests that are perform the best overall. Still, we feel like that some of these tests may have some value when we want to combine several tests. If we look at the seasonal unit root test, the Gomez-Maraval algorithm clearly outperforms all of the other tests, achieving an accuracy of close to 93%, while none of the other tests are higher than 70%. So this may point to a situation where basically we don't need anything else but the Gomez-Maraval algorithm. This is just what I told you. Okay, now we've given this setting, how can we use random forest? So just as a kind of summing up just the idea of random forest, a classification tree basically tries to find out, given a simple set of simple rules, how to split down a given sample comprising, in our case, of series with a unit root and series without a unit root, finding simple decision rules to guide us through based on the test, is there a unit root, yes or no? And random forest, let's skip here. Random forest is just a set of different classification trees. The randomness comes in two parts. First, we always draw for each tree, we draw a new sample with replacement, and at each node, we only consider a subsample of all tests. The idea is that there's no test dominating our results, and we get something like a result that takes into account all of the information available. Now, we don't use classical random forest, we use conditional random forest, and the reason they are the same in what I just described, but they are different. There are minor differences when it comes to how a feature is selected when we stop growing the tree. But in our case, the most important difference is with respects to the variable importance. That is how it measures the impact or the contribution of a given feature. While for classical random forest, it's unconditional, it's obviously conditional for conditional random forest, and conditional now means that it takes into account the correlational structure of our features. This is just like some notation for how variable importance is measured, but the idea is that we measure the improvement at each node for a given variable, summed up over all nodes where this variable is selected. This is like the raw variable importance, and contrast it with the improvement in classification that we would have achieved if we would have used a completely random variable that is unrelated to anything. And this completely random variable, we get that by permutating or permuting all of the values of the given feature. So the idea is that we have a random variable, but that has the same structure as the variable of interest. But one can show, when Strobel and al. Does that, that in random forest, basically the null hypothesis is that the feature that we're interested in is unrelated to our target variable, but it's also unrelated to all other features, that is all other variables. And this, of course, is not a good idea in the case of unit root tests that try to measure the same thing, and those are obviously highly correlated. And we could show that they have correlations of above 0.8. And so this assumption is heavily broken. In contrast, conditional random forest just states that null hypothesis states that x1, the variable of interest, and our target variable are unrelated given any other variable, any other feature. Okay, so we want to take advantage of these variable importances and use them to identify the most important tests and then combine tests. And of course, random forest, though the rules themselves are quite easy to understand, if we have, say, 100 trees and each of these trees have 50 decision rules, then they become quite intractable. So there will be some trade-off between having interpretable results and having a combination of tests that give us a low misclassification rate. In the first step, we'll do a recursive feature elimination. I'll show you in a second what that means. And then based on this, we will try to derive a final classification rule for practitioners. So the random feature, the recursive feature elimination, we start out with calculating conditional random forests on a set of unit root tests, estimate the variable importance, and then throw out the least informative test. And then we start again until basically no tests are over. Here you see the results. On the x-axis, you see the test that is thrown out after that round. And on the y-axis, you see the accuracy. And what we find is that, and this is typical, in the beginning, because we have a large set of tests, we throw out features that basically don't yield anything extra, but kind of make it harder for the random forest to find the perfect combination. We improve the accuracy until then some point for which we say, okay, probably a combination of these 6 tests here may yield quite a good combination of tests. And so this would be our starting point. That is, we would try to find out how to best combine these 6 tests. And we'll start out with just building one simple classification tree. And then, of course, with different rules for how large we grow the tree, how much pruning we do, we get different results. And I'll show you in a second how that looks. Here, it's the same result for the seasonal unit root tests. And we see that there is you can probably increase the accuracy of the single GMS test, which was close to 93% to maybe a little bit above, 93.5, but from a practical point of view, maybe it's not worth it. Because for the regular unit roots, we are able to improve from 85 to at least 90%. So this is what a single tree could look like, just for people who want to understand it. We start out with a GM test. Depending on the p-value of the GM test, we then look at the KPSS test with the trend and then the PP alpha trend. And here at the end, you see how it classifies the result. And the classification is always done for the majority class. So here it would classify it as 0, that is no seasonal unit root, no regular unit root. Here, interestingly, in both cases, depending on the split, it would classify it as having a unit root. And this gives us some means to further simplify this this combination of tests. So the simple tree would in the end just comprise of 1, 2, 3, these 3 tests. Because you could grow a full tree just for comparison, and this just one tree would make it probably quite hard to understand, though, as I showed you before, we can do some manual pruning as well. And these are the results. So with a simple conditional random forest here, we could achieve an overall accuracy of 91%. But just with a simple tree, we already can achieve something close to 89%. While with the full tree, it's something closer to 90%. So these are preliminary results, but we are quite confident that with a simple rule for combining tests, we can devise an overall unit root test and maybe also a unit root and seasonal unit root test that give an answer for practitioners whether or not there is a unit root, yes or no. And our idea will then be to investigate whether this leads to better predictions. That is, if we take into account that there is a unit root or that there is no unit root, and we take this into account for predictions, is this an improvement compared to using the best available unit root test? But this is something for future research. So as a takeaway, and I didn't talk too much about it, but use representative simulated data if you want to find out how something performs in reality, because of course you can talk about the theoretical advantages of your tests, but I think that data are really important. We use variable importance and a recursive feature elimination based on conditional random forest. And then the main finding is that we are confident that a combination of only a few tests will improve the accuracy for practitioners. All right, then just briefly, some references. All right.
Thank you very much, Daniel. There are questions about the talk. Someone wanted to ask something. I have just a curiosity. What is the typical time length of the time series that you used? Because probably I missed, but...
No, I didn't say that. I like, for when we simulate it, it's 5, 10, and 20 years. It's because, I mean, we have our seasonal adjustment background in the mind, and that's the kind of series that we are usually working with, and it's a monthly series.
Okay.
But in the future, probably it would be worthwhile to do that again for, say, daily time series with a longer length.
Exactly, because I expect that with longer length of the time series, you should improve the accuracy of the method, right?
Yeah, for sure.
This is for sure expected, but anyway.
Yeah, you're right.
Okay.
Okay.
Thank you very much. Again, now it's the time for the second talk of the contributed session that is given by George Wine. Is correct?
Win, but I won't hold it against you.
Win. Oh, sorry.
It's no worries.
All right. Okay, the title of the talk is Kernel to Sample Test for Functional Data. So thank you, George, and please.
Sure, let me just connect my iPad.
Sure. Perfect.
Okay, nice. All right, let's get this show on the road. So first of all, thank you for letting me speak. It's been a really cool event. I just wish I was able to be there in person. So the title of my talk is a kernel 2 sample test for functional data, and it's going to be joint work with Andrew Duncan, who's also at Imperial College. Due to the time limitations, I'm going to try and make this talk light on the maths and heavy on the morals, like the main takeaways and the main ideas of what's going on here. So the main moral, if any of you need to dash for some reason in the next 2 minutes is that we're using a statistical procedure called kernel-based tests that have been very widely successful in machine learning for about the past 10 years. We're applying them to functional data, which is related to dynamical systems. Simple as that. Okay, so first of all, what is a two-sample test? I imagine many of you are familiar with it, but I'm just going to talk it through here to establish some notation. So we're going to have some set X, which our random variables are going to be on, and we're going to have two probability measures, P and Q. And we're going to have some samples from each one. So I'm going to use X to denote samples from P and Y to denote samples from Q. And we want to perform a test. The null hypothesis is that P is equal to Q, and the alternative is that P is not equal to Q. I'm going to do this test with some controlled error. So this is what we want to do. And in our example, our X here is going to be some function space. So two-sample tests are classically studied for decades and decades and decades. And the classical examples are like Hotelling and Kolmogorov-Smirnov. And there are some specific instances of two-sample testing. So the setup I just talked about is the most general case, where P and Q can be arbitrarily different. But perhaps you want to be doing two-sample testing where you're just testing difference of mean or difference of covariance structure. And it's also related to model fit tests as well. So these are really kind of widely used, widely studied things. So now what's the catch? The catch is that we're dealing with what's called functional data. So each xi and yi, ideally, or in the pure sense, are going to be functions or trajectories of functions. So we're thinking perhaps SDEs, trajectories of SDEs, or random surfaces. In practice, they're going to be discretized because we collect data discretely, right? So they're going to be discretized. So we're going to have some input-output pairs, and perhaps even the discretization scheme itself will be random. So one thing to bear in mind is that if our observations are somehow dense, like we have loads of observation points, then later down the line, if we need to compute things like integrals, we can just whack it into our favorite numerical procedure and not worry. But if our sampling is not dense somehow, we're going to have to fit curves. So one of the main morals here is that we need to consider both the infinite dimensional nature of X and what is the statistical impact of fitting these curves later down the line in our testing procedure. Quick point, which I won't dwell on too much, is why not just treat it as a vector data? So if we happen to have some regular observation grid of, let's say, capital N points per function sample xi, then we could treat it as a vector in Rn. Issue there, it's already a non-trivial assumption to assume we have such a regular grid, and we can't incorporate, we're throwing away the first half of this story here because we're not actually using the information we know about these random functions. For example, maybe we have some ideas of smoothness, periodicity, perhaps knowledge of the Kahunen-Loewe expansion, and things like this, and we're just throwing that away. Also, if you do this, then you have a question of, well, how fine a discretization should I really take? Because potentially some tests which are inherently finite dimensional don't behave well in high dimensional if they're not incorporating proper knowledge of functional data. So a quick note on existing approaches within the functional data analysis literature. The vast majority of them can be summarized in these first 2 points. They often do some kind of finite dimensional representation, potentially using functional principal components, and then employ finite dimensional tests. So for example, Pohmann et al. In 2016 did something using a functional version of the Anderson-Darling, and you have like chi-square tests and things like this. But the main thing here is reduce dimension, then do finite dimensional test, which one can look at that and have the worry that, are you throwing away too much there, perhaps? Okay, so now we're going to talk about the main tool, maximum mean discrepancy. Boumediene talked about this a bit yesterday, so I won't talk about it too much, but I will give a bit of context just so you have the kind of main arc of the story here. So this is really first studied in the mid-2000s and has been really successful the past 10 years. Some of the main contributors to the theory, amongst others, but I don't have enough time to talk about them now. We have Arthur Gretton, Alex Smola, Bernhard Schulkopf, and the main kind of papers you'll see is there's a large summary paper in 2012 that was in the Journal of Machine Learning Research with Gretton et al. And another summary more recently by Mwanda. And this testing has been applied to different kinds of data, not just vector data. So it's applied to images, text data, graph data, and high dimensional vector data. In particular, one of the most kind of successful applications of maximum mean discrepancy is on training GANs, so using images in your kernels. but there's been very little work done on functional data. And I feel this is because the machine learning community literature, however you want to phrase it, hasn't really looked at functional data so much in comparison to other data types. Since only in the past couple of years, we've really had such an acceleration in identifying the applications of theory within functional analysis to machine learning techniques. So there's two main exceptions. So Harold Oberhauser and Ilya Cheverev in 2018 did very similar work here, but they were using a kernel based on signatures, as they've been discussing some of the talks, but didn't go too much into the theory of them. It did almost like a proof of concept with them somehow. And very recently, in the past week or so, Hayati and some co-authors also studied the same problem here, that functional data using kernels, but they focused only on the Gaussian case, where P and Q are Gaussian measures, i.e. Gaussian processes. Whereas our scope is a bit broader. We're trying to create the theoretical foundations to have arbitrary difference. So the main idea of MMD is you want to express it as an integral probability metric. So MMD is going to be a distance, as long as the kernel has some properties I'll talk about later, between your P and Q. And we're going to express it like this. So it's going to be an integral probability metric here. And the main idea, make a distance, compute it using empirical quantities, and reject the null if the distance is large. That's the main idea here. And why is this a reasonable thing to do? Why is this a reasonable distance to look at for some set of functions here? Because quite a few of the classically studied distances on probability distributions, such as the Dudley, Wasserstein, and total variation, are all kind of this form. This isn't an outrageous thing to suggest to do. So kernels, finally. A kernel is going to be a symmetric positive definite function. Main two ideas we're looking at is a Gauss kernel and an inverse multi-project kernel. But the main thing to keep in mind is that it's a notion of similarity between the inputs. So in our setup, X and Y are both going to be functions, and it's going to be a measure of similarity between the two functions, like that. And maximum discrepancy, the idea is we take a integral probability metric, as we had before, which is the distant difference of these two supremum over differences of integrals. If you use an RKHS corresponding to some kernel, I won't get into the details now, but you can do a trick where you can actually rewrite that difference, that integral probability metric, as this set of double integrals here. So why this is super important and helpful is because this guy you can compute really easily using a Monte Carlo sum. Whereas the form of the integral probability metric, where you have this supremum, a priori, it's really going to be difficult to compute that somehow. Okay, so as I said, this can be computed using a Monte Carlo estimate here, which is of this form. So this looks at the interdistance between samples of P. This is the interdistance between two samples of Q. And this is the intra distance. Or is it the inter and intra? Whatever, you get what I'm saying. Like it has the, it measures similarity between P, similarity between Q, and difference between P and Q. And this statistic here that you use to estimate this guy is a U statistic. So it has lots of nice properties, and you can do a simple permutation bootstrap to estimate the null distribution. One thing I should mention here is that's important, is that for an arbitrary K, this is not necessarily an actual metric. It's only a semi-metric. It's only a metric, therefore the test is only going to be valid because it can only tell the difference between distributions if K is what's called characteristic. Simple test procedure. I'll just talk about this quickly. You get your samples, you calculate your empirical estimate and call it star here. And then what you do is your permutation bootstrap. You pull the samples, randomly permute them, split them into two different samples. You're going to be simulating the null, recalculate the statistic. This gives you a, a sort of distribution, and then you're going to choose some point as your threshold. And if your guy lies outside, then you reject the null. Okay, so now we're going to talk about so that's the setup. What are the contributions of our work? So the main difficulty with kernel-based tests is actually having kernels which are characteristic, meaning that this distance is actually a metric, not just a semi-metric. Okay, so this hasn't been done so far for infinite dimensional spaces. So that was our main theoretical contribution. And then we assessed the actual impact of fitting curves. We looked at numerical comparison between ours and existing methods, which, as I said, mentioned before, are primarily projection-based methods where they project to finite dimensions and use some finite dimensional test. And given MMD is an actual metric. You can look at topological properties about how convergence of measures. And then we looked at what happens if you actually treat it as vector data in there. So I'm only going to try and touch upon these three with the 10 minutes I have remaining, which might be a bit ambitious, but we'll give it a go. So let's talk about characteristic kernels. The easiest proof to show a kernel's characteristic is pulling kind of a yet another different representation of MMD out the hat. So this one comes from if your kernel here, KXY, can be expressed as the Fourier transform of some distribution. So main example to think about, the Gaussian kernel is the Fourier transform of a Gaussian distribution. Okay, so that holds on RD, and that was how, that's the easiest way to show that the Gauss kernel is characteristic. Because what you do is that you show MMD is equal to this weighted L2 distance between the between the characteristic functions of P and Q. Okay, well, here's the moral of the story for how we adapted this to infinite dimensions. Rather than immediately changing the kernel here, you say, what's the infinite dimensional generalization of the measure? So we have Gaussian measures on RD, but we also have Gaussian measures on infinite dimensional Hilbert spaces, i.e. Gaussian processes, as they're potentially more familiar to some. So we know we actually have the maths have been worked out for the characteristic function of a Gaussian process. And it looks a little bit like this. This is probably the nastiest maths in here, so forgive me. And it looks a bit like this, where C, rather than being a matrix, is now an operator. Okay, so that's the move from finite dimensions to infinite dimensions. And the moral of the story is here is that if C is injective, then the distribution will have full support. And if the distribution has full support, then you can quite easily see here that if this expression equals 0, and if this guy has full support, then these two have to equal each other everywhere, almost everywhere. And that's enough to deduce that P equals Q, because these are the characteristic functions. Using this technique on its own is a bit limiting, because you have to have some assumptions on this C here. So that doesn't give you a wide class of kernels. But this is the start point of the theory, and then we extended it using some limit arguments, which doesn't matter for the time being. And this gets us to the main theorem of our paper, and this is defining a broad class of kernels on infinite dimensional Hilbert spaces, which are characteristic. So the difference here between the finite dimensional version theory is that we now have a hyperparameter T, which is now a map between two infinite dimensional spaces. Whereas in finite dimensions, most hyperparameters of kernels are just like a scaling of your data or something like this. Because a priori with finite dimensional data, you don't have enough structure to know what to do with it. Whereas for infinite dimensional data, for functional data, you have a bit more structure at your disposal. And here are some examples. So as I said, if you pick this to be some operator, you recover the first argument. If you pick it to the identity, you get a Gauss-like kernel. But then you can do a bit more fancy things. So in this example, if you pick T to be this integral operator here for something that looks like this, this is what this guy will be doing is taking your function and then emphasizing the first F Fourier frequencies and then smoothly decaying the rest of them. So if you, for some reason, think that you're only doing like a mean shift test, for example, you might want to use something like this because you think, well, my mean's probably going to have most of its mass in the lower Fourier frequencies. I'm going to use a kernel which use a hyperparameter which kind of emphasizes that. And this relates to a numerical experiment. I've got an example of a bit later. Okay, so moral of the story, wide class of kernels that are characteristic on function spaces, therefore MMD is valid. And now the hyperparameters let you incorporate a bit more knowledge about your actual structure of your problem into things. Now we're going to talk about the impact of curve fitting. So there's a bit of notation here, but I'm going to try and elucidate why. The idea is that when you have functional data, you can, when you have this discrete representation, it can be pointwise, but you could also perhaps have your information in a different way. Perhaps you get information about its Fourier transform or something like this. So our setup here is that we're going to have I, it's going to be some information operator, and we're going to have some N bits of information. I don't mean bits in the literal information theory sense. Obviously, it just means it's going to be some N dimensional representation. So for example, pointwise evaluation, a set of n points. R is going to be a reconstruction map, for example, like a spline or piecewise linear interpolant. And then what we're going to do is perform our test on the reconstructed data. So if we're going to have an asymptotic result in little n, the number of samples, then we're going to have a condition that says how many like information evaluations you get per sample, and then the quality of the information you get and the quality of your reconstruction. These need to unite somehow to make sure that when you run your test on your reconstructed data, you get the same statistics as if you had the true perfect data. So here's the theorem. It's technically a bit of a sketch of a theorem because I'm not writing things out fully, but it should delay the moral of the story. Your kernel needs to be Lipschitz, which for the two kernels I presented in the earlier theorem holds. And your information, reconstruction, a number of bits of information per sample needs to combine such that you have a decay rate of root n, essentially, for your data. So that's, and then if that holds, your asymptotic of your empirical of your estimator here satisfies this equation. And this equation is the same limiting distribution as if you had the actual true data. Okay, so it's if you didn't actually have the information and reconstruction. So that's where this guy kind of comes from. Okay, so this looks a bit weird. We got quite a lot of symbols. Let's give a very basic thing. Bear in mind, we need convergence of root n. So here's a real simple example. We're going to do piecewise linear interpolation. So we're going to have I being pointwise evaluation on a set of capital N grid points, where we're going to have this depending on the number of samples we have. We're essentially going to work out how much does this have to grow, how fast does this have to grow in terms of the number of function samples. It's going to have some equally spaced grid points. That's our information. Our reconstruction is going to be piecewise linear interpolant. Now we assume some regularity of our underlying functions. Then it's a classic result that in expectation, we have decay as being 1 over the number of points squared. So if we needed this guy to decay as n to the half, where n is the number of data samples, then it means that the number of points per sample we need needs to be at least n to the quarter. So that's a kind of, this is a worked example of how many points per curve you need to kind of get a good kind of feeling, or more than feeling, but be safe in the knowledge that your test is still going to be behaving as it should be behaving. Okay. So last couple of minutes, we're going to look at a numerical example. I only have time for one, but hopefully it will illuminate some things and why this is a potentially good thing to do. So in this example, it's going to be a mean shift test. And here the shift is characterized as this thing here. So delta is a coefficient, and it will determine how different from the null we are. So if delta is 0, and this guy's gone, and we have the same distributions here, and the randomness occurs in the coefficients of a Fourier expansion. Okay, so we've got random variables here. So what does this graph tell us? Well, first of all, what the hell is all this meaning here? These are different parameters, different choices of t, essentially. So this is t is the identity, and t is, of course, to be interpreted as a hyperparameter here. But it's a hyperparameter where we're choosing it based on some knowledge we have about our functional data. This is Cx, is the one I mentioned earlier, which emphasizes lower Fourier information. This is one which emphasizes covariant structure, principal components, covariant structure. And this is the existing test that is projects to finite dimensions and then does a finite dimensional test statistic based on the Anderson-Darling. And we see, first of all, the existing one has very low power compared to any of these kernel methods, really, except the two which only look at difference of covariance. Because in this example, they have the same covariant structure. So of course, those would do badly. And the main reason for this is that our procedure does not involve this finite dimensional projection. You just put it into the kernel does all the work. And we see that the one which actually emphasizes a kind of low order Fourier information does by far the best, because it's getting rid of the information we don't care about. That doesn't actually have a difference. Okay, I know it was quite brief, but there's a much more extensive numerical comparison in our paper, which we put a lot of effort into to make sure we're looking at a different range of scenarios. Okay, so to wrap up, because I'm slightly over time, kernel-based tests found a lot of success in machine learning for the past decade, but they haven't really been applied to functional data. So we're establishing the theory for their use on functional data. It avoids some of the issues associated with functional data analysis approaches. Again, no finite dimensional representation, and we have consistency with this fitting of curves when you have discretized observations. And in our opinion, there's great potential for their use in a dynamical systems context. And one of the reasons is this, in a kind of vague sense, is that you can incorporate more theory of your dynamical systems, whether it's SDEs or something like this, into your choice of kernel. I'm just showing these references for the recording. So yeah, there's Oberhauser's, which was one of the first works in this area, and the Gretton et al. Sample test in JMLR. And that wraps up my talk. And if there's any questions, I'll be happy to take them. Thank you very much.
Thank you very much, George. There are some questions. Maybe lunch is too close.
Yeah.
Anyway, okay, thank you again, George.
No worries.
Now is the time for the last talk of the contributed session by Alessio Brini. He's going to talk about dynamic trading with the reinforcement learning. Alessio, are you here? Yes?
Do you hear me?
Yes.
Okay. Now you should see my screen, right? Okay.
Okay.
Thank you. Thank you, Piero. Good morning to everyone. Today I'm going to present my joint work with Professor Tantari, which was a former researcher at Scuola Normale and is currently at the University of Bologna. Our work is about dynamic trading with deep reinforcement learning, and will be about methodological approach in order to see if reinforcement learning algorithms are able to retrieve the underlying dynamics of financial assets. First of all, I would like to frame the problem we are going to see in this presentation. Usually, asset managers construct some models in order to predict asset returns and then trade according to the signals provided by their model. But this task is known to be very hard because there is a lot of noise and the signal to noise ratio is very low in financial data. And also this task is focused only on to find the best fitting model to the data available. And there are no details, no modeling about the investor preferences. And in this context, we would like to introduce reinforcement learning, which is a machine learning paradigm, which is able to model sequential decision making, in which in your specific problem, decision can have long-term consequences and also eventually sparse feedback. At this point, one should ask, why do we need to apply reinforcement learning specifically to a financial trading problem? First of all, because we would like to bypass the forecasting step, which usually asset managers need to do, and instead focusing on optimizing an objective function, which could reflect the investor preferences. Moreover, it's a convenient framework in order to model intertemporal choices, because it's inside the way reinforcement learning problem is constructed. And also, those kind of algorithms should be more flexible with respect to classical optimal control approach like dynamic programming. In our work, we will simulate asset returns with a known dynamic in order to assess if the RL agent is able to detect profitable trades that are inside the dynamic of the asset. In doing that, we will be helped by the financial trading environment as described by Garleano and Pedersen in their work. And this will allow us to do controlled experiment, because at any time we will know the dynamics of the variables involved in the problem. This will allow us also to establish a link between reinforcement learning, which is relatively recently applied to finance with respect to optimal control, such as dynamic programming, optimal control techniques. And also we could use the analytical solution provided by Garleano and Pedersen as our target benchmark for data-driven algorithms like reinforcement learning algorithms. Here we are going to briefly describe the financial framework as in Garleano and Pedersen, in which there is a discrete time market in which there are S securities, and the return of these S securities is Y, and is driven by some factors F plus some noise. Each return predicting factor evolves according to an autoregressive process, which in this case is a discretization of an Ornstein-Uhlenbeck process, where phi are the speed of mean reversion of the factor. So you can have as many factors as you want, describing your returns, and possibly those factors have different speed of mean reversion. Moreover, trading in this environment is costly, so whenever you trade a quantity delta H, you incur a quadratic cost in which the capital lambda matrices is proportional by some factor lambda, which is called cost multiplier, is proportional by the risk covariance matrix. The optimal solution provided by Garleano and Pedersen consists in a trade-off between holding the portfolio at the previous time, so don't trade at all, and moving towards a named portfolio which resembles the optimal Markowitz solutions, with this likely difference that the factors are scaled down by their speed of mean reversion, as you can see from the second factor on the right-hand side of the equation 4. So we will use such solution as a benchmark for our reinforcement learning algorithm. But before dealing with the numerical experiments, we want to give a little bit of background underlying reinforcement learning. Usually, the most simple reinforcement learning problem is modeled as a Markov decision process. And a Markov decision process is composed by some elements, so it's a tuple. Such tuple is composed by calligraphic S, which is a finite set of states in which the agent, the reinforcement learning agent, can be at any time. The calligraphic K is instead a finite set of actions that the reinforcement learning agent can do. So in our specific case, since the agent will be a financial trading agent, calligraphic A will be composed by the finite set of quantities that the agent can trade, the finite set of financial assets that you can buy or sell. Then there is a transition probability matrix, which describe whenever you are in a current state S and you perform an action A, we describe the movement from to the next state, which is denoted by S prime. Then there is a set of values, which are real values that the reward function can assume. The reward function, which specifically depend by the current state in which the agent is and the action that he decided to perform, knowing that he's in the current state. Then gamma is a classical discount factor for discounting future rewards. Now, looking at the picture here, you can have a look at how basically our reinforcement learning algorithm works. Usually there is an agent and an environment, and the agent sees a current state representation, which is ST at an initial time. Then he decided to do some actions, AT, and he receives an answer from the environment, which is usually composed by two scalar signals. First scalar signal is the next state, according to probability transition, described as before, and the other scalar signal is the reward function. So the value, the reward that the agent has obtained by being in the state S and doing the action A. And this is a potentially infinite feedback loop, which will bring the agent to interact with the environment and acquiring knowledge on how to behave in such given environment. So the goal of the agent will be learn an optimal policy, which is the optimal way of behaving, and usually is described as a distribution of the action given the states. In order to guarantee the ordering of policies, so in order to be able to choose among different policies, different ways of behaving, we need to define the total return function, which will be the sum, the infinite sum of discounted reward function over time. And this will allow the agent to search for the policy that maximize the expectation in equation 6. So it maximize the total return, the expectation of the total return. In doing that, there is a lot of underlying theory, but mainly the main element that you have to have in mind are the value functions. Value function represents how good is to be in a given state has in terms of the expected future cumulative sum of rewards. So in terms of G. There are two kinds of value function. The V in equation 7 is called the state value function, and it depends just on the current state in which the agent can be. And the action value function Q in equation 8 depends instead on the state in which the agent is and the action that he decided to do in that state. Those two value functions satisfy a recursive relationship, which is called Bellman equation, from the work of the known scientist Richard Bellman, and they are tied by the relationship in equation 9. So basically, the state value function is the sum over the action space of the action value functions. Here a little bit of background about the reinforcement learning algorithm we are going to test in our simulated financial environment. So usually when the problem is relatively simple and the set of states and the set of actions is limited in size, you can use tabular reinforcement learning approach. So classical reinforcement learning as Q-learning, which is one of the most known reinforcement learning algorithm. And you can approximate the Q star, so the action value function, as a table. It's a table which has an entry for every state action pair. And you can iteratively update such table according to the update rule in 10. So basically, you update according to a learning rate alpha, which is the step of the update. And you have here the target, which is composed by the reward of the agent and the maximized value of the action value function over the set of action, which is also discounted by gamma, while QSTAT is the current value of the action value function. But those kind of algorithm has some drawbacks, because usually you're not able to properly discretize the variable that are represented in the states in order to make some real experiments. So there are some other algorithms. There is a family of algorithms which is called deep Q network, which are exactly a natural extension of the tabular approach, in which instead of using a table to approximate the optimal action value function, you use some parametric approximator like a neural network. So basically, the deep Q network is a multi-layered neural network that takes as input some state has and output some action values, which allows you to compute the maximum of the action value function over the action space. Here there is the update rule of the parameters of the neural network in the reinforcement learning, in this deep reinforcement learning algorithm, but basically many details can be found in the original paper of Mni et al. Because there are some slight nuances in understanding how this reinforcement learning algorithm works. There is a lot of material more than what I'm explaining here. Now moving to the simulated experiment part, we are going to have one risk-averse agent, which will trade just one single asset at a time, and try to solve the dynamic trading problem by the means of reinforcement learning algorithms that I described above. Having a controlled environment, so working in the environment of Garleano and Pedersen, allows us to, as I said, simulate known dynamics and evaluate the reinforcement learning algorithm against some benchmark. We will train over some n in sample iteration, and we will evaluate over some out of sample iteration at many intermediate steps during the runtime of the algorithm. All the agents will share the same reward function, and state representation will be composed just by the current return of the asset and the holding of the previous time of the asset. So the amount of shares that the reinforcement learning agent has from the previous time. So the reinforcement learning agent will take an action A and causes some movement in the holding portfolio, producing also a reward signal, which is exactly described in equation 13, in which you have exactly the objective function that Garliano and Pedersen were using to solve their dynamic programming problem, excepting for the fact that here there is no discount. Here are some results. We have results for Q-learning. In this picture, you have the profit and loss, the net profit and loss, and the holding. So you have a pair of picture for each kind of out of sample intermediate steps. And as a title, you have the number of in-sample iterations at which we stop the runtime of the algorithm and we do the evaluation out of sample. You see that Q-learning starts very badly, but with going on with the runtime of the algorithm, at the end is able to approach the results obtained by the benchmark, which is in orange and is exactly the Garliano and Pedersen solution. In this case, we see that Q-learning is able to obtain a similar portfolio holding representation as Garliano and Pedersen, but it takes much time. It takes many iterations of the algorithm. So it is not very sample efficient, and we will see how DeepQ network will solve this problem. But in order to be sure that Q-learning has learned the underlying behavior of the data we are simulating, we can have a look at those two pictures. On the left, you have the value of the action value function estimated by Q-learning for different level of returns, being fixed h equal to 0. And you see that for level of returns which are lower than 0, the value function, the action with the higher value function are the short action, so selling action, while the opposite holds when the return are positive. So that means that the algorithm has approximated the action value function in a sense that is able to understand that it needs to buy low and selling high, which is exactly the way of reasoning when you have to do with mean reverting process, when mean reverting assets. On the right hand side, on the right picture, you have more or less the same information presented from a different perspective, because you have the best action for different level of returns. As you see that when the returns are negative, the best action is short and vice versa. So that is exactly the same we were seeing on the left. But now moving to look into the same kind of picture for the DeepQ network, which uses a neural network to approximate the action value function. You see that DeepQ network essentially obtain the same results of tabular Q-learning approach, but it takes less time. So we can say that is sample efficient, is more sample efficient because it makes proper use of the sample while updating its parameter. So it's an improving over the result obtained by Q-learning. And you can see the equivalent of the picture we were looking before for DeepQ network. Now the action space in DeepQ network become continuous, is not discretized anymore, so that value function for different action are curves now instead of cloud of points. But if you look at for different level of returns, you still have the same reasoning as before. Also the same holds when looking at the best action performed by the DeepQ network. So in some sense, we can say that neural network helps in improving the estimation of the action value function and being more sample efficient when you deal with this kind of simulated data. Here is our results of DQN, the performance of DQN on average. You have the red dashed line, which represent the percentage reference net profit and loss or the solution of Garliano and Pedersen. So it is fixed to 100 because it's our target benchmark. And then you have the cloud of points, which are represented by many different experiments, net PNL for our DQN agents. So the points are many DQN agents, and the blue line is the average of such agents. So you see that the percentage reference net PNL is always track the optimal solution by Garliano and Pedersen. And at this point, we should move further, and we can think about changing the underlying dynamics, because in this simulated experiment, we know the dynamics, we know that the solution of Garliano and Pedersen we use as a benchmark know the underlying dynamics. So what could happen if we change the way we simulate data, and instead we use some Garch type models? So we insert some heteroscedasticity. What could happen in that sense? And it should be line of research we should pursue. Then we can think about repeating the same experiment on shorter simulated series. So that would help thinking about real applications, because usually you cannot have very long time series. Usually you have, especially at the daily frequency, you have very short time series. So we would like to see what could happen if we have a shorter time series and we pass many times over the same time series, and see what how the presented reinforcement learning algorithm performs. And at the end, the final extension will be moved to multi-asset tradings using DPQ network, and also using real financial data. Here is some references of what I presented today, and I think it's all, and I would like to thank you for your attention.
Thank you, Alessio, for your talk. There are questions. Okay, I have a curiosity. For the moment, these kind of experiments are taught like with daily data, I think, right?
Yeah.
No, I mean the time scale is that one. I don't know, or larger, I think. Okay, my point is this: that is, if I well understand, that some kind of benchmark is the Markov chain, the Markov decision chain. That is at discrete time, but in principle, if I don't know, if you think to move to high frequency data, another possibility is considering continuous time with something related to the activity of trading, for example. My curiosity is about your method with the reinforcement learning. There is the possibility to account also for something that is at continuous time to describe the activity of the trader, or with the method you need to use only discrete time? Okay,
thank you, Piero, for the question. No, I think this kind of setup, so the reinforcement learning setup, is very flexible in the sense that we could absolutely move to high frequency perspective. And I don't really get what do you mean if we can insert like some information about the activity. If you sorry. If you're referring to some features, so some characteristics of that could track the activity of the trader, if we are able to represent such, if you're able to represent the activity of the trader as a features that the reinforcement learning algorithm can take in their state, so in the state space, we are totally fine. We can absolutely do that.
Okay. Maybe, I don't know, maybe some regressor about related to the occurrence of news, or
yeah, for sure, for sure.
Okay.
As I say, it's very free, so we can compose our state space as we want. So there is no problem in moving to high frequency reasoning.
Okay, thank you, Alessio. There are some questions.
Can I ask a question?
Sure.
I'm Stefano Herzl. Very nice talk, thank you. I wanted to ask you, I think this it is very important that the choice of the reward function, and you are considering the model by Garliano and Pedersen. I think they are trying to optimize the mean variance kind of utility, right? While what you do is, I mean, what is your reward function? I wanted to ask you to go there and then to explain if you did you try also with other possibilities, and do you have other? I mean, why did you choose that one, and what is the relation to that and Garleano and Pedersen, and if you made any other choice of that reward function? Thank you.
Okay, thank you for the question. The choice was mainly motivated by the fact that starting from Garleano and Pedersen, we had like the optimal solution obtained through dynamic programming to the problem. So we took the same environment, we took the same reward function, which is exactly the one here in equation 13. So mean variance plus quadratic cost is the one they Garleano and Pedersen used. And this was mainly for having a target and knowing if the reinforcement learning agent is behaving well in such a knowing environment. But surely I haven't tried for the moment, but surely we can modify the reward function, not considering Garleano and Pedersen at all in that case, because that wouldn't be valid anymore. But we can, reinforcement learning also allows for modifying reward function and seeing what are the results.
Thank you.
Thank you. You're welcome.
Thank you.
Can I ask a question, please?
Sure.
Hi, Alex. Thank you for your talks. It's very interesting. So I have a curiosity. Do you think that this technique also work in the energy market? I don't know if you know the energy markets, but are illiquid, are inefficient. So do you think that we can apply this type of technique also in this type of market?
Okay, thank you for the question. I think there is no obstacle in trying to setting up an reinforcement learning agent to trade in the energy market. I don't have too much experience on that, so I don't know what could be the problems related to the fact that the market is illiquid. But for sure that there is no problem in setting up a reinforcement learning approach in that sense, as long as you know what are the state variables to be included. So mainly, maybe you can also model the reward function in the sense that the agent should know that the market is illiquid. I don't know, probably that there is some way to model that if we look at the literature. I'm not an expert, but surely that will be about the modeling the reward function and the state space, changing those two parts.
And the last question, but I don't know if you can do this. Do you have a notebook, an example with an application of your techniques? If you can share, I don't know if it is possible.
I didn't get the question because I didn't hear that. Can you please repeat?
No, if it's possible to share with us an application example of with a notebook, just an example of this type of application.
Okay, so oh yeah, for sure, the code that produced those kind of experiments, for sure. Well, write me if you write to me, and I will send you an example for sure.
Okay, thank you very much.
Oh, thank you. You're welcome.
So it's a great pleasure to introduce Juan Pablo Ortega from University of St. Gallen and CNRS France, who is going to talk us about reservoir computing and learning of dynamic process. Juan Pablo, the floor is yours, and thank you for accepting the invitation.
Thanks a lot. Thanks to you. And I join the other speakers in thanking the organizers, because, well, these days organizing a conference is you need to be a hero to do it. So yeah, so thanks a lot for putting this together and for making sure that you know, things keep going, not like normal, but at least we have chances to interact and to meet and to discuss, because well, this was going to be a short thing, but it looks like we are in this for a while. and God knows how long this will take. So it's very pleasant to have a chance to talk to people, to see you, and again, it's a pity that we couldn't be there all together, because it would have been truly great. So one thing, you see my screen. If I move it, it moves. The screen.
Yes, it's perfect. You can even put full screen if you want.
That's what I did. It says here sharing is paused. So you didn't pause anything, right?
We see the window, let's say, but you know,
so
you see and everything. Yes.
Okay, very good.
Not the full screen setting.
That's funny. Let me do something. 1 second.
Sure.
So now I go to full screen mode. Is better like this?
No, actually, it doesn't work.
It doesn't work. Look, what I'm going to do, I'm going to share the entire screen.
Okay.
And then that's it. So, share the entire desktop.
Yeah, now we see your screen.
Okay, very good. And now if I full screen.
Yes.
Now it's good?
Yes, yes.
Okay, very good. Look, so let me start by telling you a bit about what the talk will contain. And well, one of the good at the same time bad things of being the last one is that, well, there are many things that I thought that they had to say, but actually they were already explained. So I will avoid repetitions, and if I introduce concepts that you already saw this morning or yesterday, then I will try to give them a twist so that you can get something new out of what I'm going to tell you. So there is this disclosure that I have here at the end. So, well, I decided not to give credit to every single result that I will be talking about, because, yeah, this is not my work. This is the work that we have all done for, yeah, by now many years, and then here there are bits and pieces of discussions, conversations, and also work that published work that we have together with some of the people that are here. Others, otherwise the list would be too long. And well, it's the end of the school. It's Friday afternoon. By the way, thanks a lot to the audience for being there, because I know it's not trivial. And so what I will try to do here is instead of telling you about 3 papers, I will try to put in plain English, well, what is at the same time my, if you want, research agenda, and the agenda of some people who are either close to me or that we have shared interest. And I will try to do it in, to put it as simply as possible, to try not to be too technical. I mean, this morning you saw a lot of technical details. You saw these bounds, those things. Each of those require a lot of preparation when you introduce them. So today I will try to simplify it as much as I can. And one of the points that I will try to convey to you is that there are actually very venerable theories, and here we are in the Scuola Normale Superiore. Is one of these temples of dynamical systems, so I don't need to tell you about classical results in dynamical systems. But one of the points that I will try to make is that there are very well established parts of various theories, in particular dynamical systems theory and systems theory and control theory, that actually are able to help us in the questions. In the main question that I want to answer here is what characterizes, or what is what we need in order to make the dynamic processes learnable. So so usually is right is the other way around, the way things are presented. So we start with a dynamical system, and then we study its properties, and the same thing happens with control theory, right? They give you a control system, and then, well, we have all these reachability questions, controllability questions, finite time controllability. So we formulate all these criteria that for a given system allow us to formulate some of the qualitative features that they have. Here is going to be different. So we are going to have temporal traces of what I call dynamic processes. I will tell you in a second what I mean by the term. And then via supervised learning, as we have been doing for the last 2 days, we will learn that system. So what is what we need in order to do that? And then the point that I will try to make is that actually most of the ingredients that we need are already there and are part of very venerable and well-established theoretical bodies, okay? So there will be 2 parts mainly. The first one will have to do with dynamical systems, and so there you will see very basic and very well-known results for those of you who know about dynamical systems. And then there will be a part, it will be closer to what you saw this morning. It will be more related to input-output systems, and there I will tell you a bit about this universality results that Ludmila was discussing. So let me start by just in one slide to tell you what we want, right? So what we want is to learn dynamic processes. Dynamic processes for me is a collective name for autonomous dynamical systems, very important, autonomous. So it's the simplest case that you can have, and I know that it can get very complicated, or input-output systems. There is something in the middle. It will be a stochastic processes, because actually, you can think of a stochastic process as an input-output system if it is generated by an SDE, right? You have this forcing noise, and then the SDE is actually the functor, the input-output system that takes you from this input noise, from these innovations, typically Brownian motion, to these solutions, right? So, and then very important, we are going to do it all in discrete time. So this is an added difficulty, but actually, since we wanted to have to do with real applications, with the actual learning, and we want to put it in the computer, we have to do it in discrete time, and this makes it technically more convoluted, and if you want, mathematically less beautiful, admittedly. So that is what we want to learn. And then, as usual, this is going to be supervised learning. So what we will use as ingredients is going to be, in general, low-dimensional discrete time observations. So if we have a dynamical system, in general, what usually happens is that you don't have full access to the space, the full state space, the full phase space of your dynamical system. Okay, so it's just lower dimensional observations of it. So, and then it comes the reservoir computing bit is, we don't want to learn it, we want to learn it in this style, in this specific way that you saw in the last 2 days. So we are going to be using state space systems. And then if you want, what makes this new terminology reservoir computing legitimate is that there are these features, specific features that were previously mentioned, that are part of our agenda. So we don't want any state space system. We would like it to be randomly or pseudo-randomly generated. I want to have access only to a few hyperparameters that need to be tuned. And then I want, if possible, extremely simple readouts, so that if I need a lot of neurons, if this readout needs to be, or this state space needs to be high dimensional, actually I can just find it via a linear regression. So and then there is a part of this reservoir computing story, because you see, reservoir computing, apart from this technology in this philosophy, is also a community, and part of this community is these physicists, these engineers, who, as was said previously, work very hard in finding this high performance realizations with dedicated hardware. It's a very interesting field. I work with some of them, and it's fascinating work and fascinating people. So so this is in a nutshell what we want to do. So then let me tell you some of the challenges that I am interested in. I will tell you about this for 2 minutes. Some bits and pieces of this discussion will show up later on. But you see, there are these things I'm interested in. So whoever I cross paths with, I tell them what I want, and then from time to time, people come with very good ideas. So that's in my philosophy of how science advances. So you have to interact with people, and we are so many, and there are so many talented people out there that chances are that what you want to do has been done already before by somebody in some shape or form. So the first challenge is what I said before, is this discrete time. So some of the results that you are going to see today, especially at the end when it comes to universality, if you go continuous time, they are actually trivial, so or extremely simple. And I will give you examples of that. Discrete time, and I know that there are many econometricians in the audience, as you well know, is complicated, is dirty, and well, you don't have all these wonderful tools that when you are doing things in continuous time, you have at hand. So functional analysis, the theory of either differential or stochastic differential equations in continuous time, in discrete time, we typically do not have those things. And then I have this past in mechanics. So you see, when you do mechanics, when you do robotics, when you do control, there are two things that happen. So the first one is that your configuration or your phase spaces, they are never Euclidean. So just think of our robotic arm, for example. So well, this is going to be a product of either spheres or circles, depending on how these arms are articulated. If you are doing mechanics, well, your phase space is going to be the cotangent bundle of it. So these are sophisticated geometric structures that are by no means these Euclidean inputs and outputs that we are used to when we are doing all these neural stuff, right? So how to tackle these things is something that I am very interested, especially if you add to it pre-existing dynamical constraints. So if you are doing mechanics, usually you work on a symplectic manifold, then the flows that you obtain out of Lagrangian or Hamiltonian mechanics, they have all these conservation properties. They have this, is not any flow that you are going to obtain in there. So how to make compatible what you are going to see with this pre-existing structure is very important in my opinion. I think that we still don't know how to do it. It could be that I missed something in the literature, because the literature is truly huge. But in any case, if you know of something like this, please let me know, because I'm interested. And then again, I have been doing symmetries for a long time, and that's something that we should be able to encode in these paradigms that we are building. So so I will show to you an example, not from me, but from a paper by Ed Odd, where these symmetries are actually very important, and actually they pose a problem, right? So I will give you an example of what I mean by pre-existing symmetries in this slide. So look, enough words. Let me start with something very simple, and which goes straight to the point of what I told you and I announced to you that I wanted to do. We want to learn dynamical systems, right? So it's time that I talk about this reservoir computing. People ask me, okay, but can you learn any dynamical system with this reservoir computing of yours, right? So this is what I will try to answer in these first 20 minutes. And then let me start with two trivialities. So the first one is, let's suppose that you have a dynamical system, and then since I am in discrete time, I'm going to think of a dynamical system as a map that takes you from a topological space to another topological space, and out of that, you define this time evolution that you see here. So just by applying subsequently to a point this map, then you get this time evolution. If this is invertible, it would be a group, a flow group. Otherwise, just a semi-group. But in any case, this is what we characterize, or what we define as a dynamical system in this setup. And in a supervised learning situation, what we would have access, what we would think of data, is orbits like this, right? What I would have at hand, I would observe this time evolution that starts out of a given initial condition, right? So, but in this case, we are seeing the entire evolution on the phase space n, okay? So question, can we learn phi out of the observations? Because phi is the dynamical system, right? So, well, if suppose that this is a Euclidean space and that the sampling is what I call decent. So you see, if this point is an equilibrium, this orbit reduces to a point, right? So needless to say that, well, machine learning or no machine learning, at some point you will need to estimate something. So if your sample reduces to a point, there will be not much that we can do, right? So, so that's why here you have a first indication that not any dynamical system is going to be easy to learn, right? So that's why you want to have generic points. If we are in a compact manifold, you would like this phi to be ergodic, for example. So anyway, we already see that there are constraints in what we want to do. But in any case, let's be naive. Let's suppose that we have that feature and that my phase space is Rm, right? In that case, we automatically could use one of these universality theorems for neural networks, and we could learn this dynamical system with a neural network, right? So, we haven't seen it in these 2 days, but in all these conferences, at least this one of these statements shows up, since we are doing things in Rn. Here you have one of the Hornik theorems. I could also have cited Sibenko. I like this Hornik statement because he does it globally for Rn, or Rm in this case, using and making explicit how to go from a compact set to the entire Euclidean space by using this topology that has to do with the uniform convergence on compact, okay? So what this theorem tells you is that, well, whenever I give you a function which is defined on the entire Rm, well, actually, for any compact subset of Rm that you will find me, well, I can find a sequence of neural networks, right? It could be that they all have different number of neurons, such that I will uniformly approximate only on that compact set this given dynamical system. That's what phi is for us. Something very important is that you change the compact set K on me, and then this limit that you see here would go to 0 faster or slower, okay? So here you see another manifestation of the importance of the good sampling, because if you are using a compact set that is not very much visited by our orbit, then obviously, both from the point of view of approximation and estimation, we are going to commit a higher error. In any case, so these are super classical theorems. Actually, you can improve them if you have sufficient regularity, and you can formulate them in order to approximate also for the UCC topology, not only the function, but also the derivatives. And moreover, if you have a finite measure, then you can do it also for Sobolev. So these are all things that are classical. You have bounds for them. So Joseph, the first day, he showed to us this barren bounds in the form of Moore. We know these things, and actually we even know them these days for deep convolutional neural networks. Here you have a recent reference that reproduces what you saw in Joseph's talk in this specific context. So you see, if we have our dynamical system defined on a Euclidean space, modulo this sampling that I told you about, we are all set, right? So what about the non-Euclidean setup. Suppose that you have a dynamical system on the sphere, right? What do you do there? Because then you cannot use these neural networks that we talked about before, right? Because what comes out of that is something that lives in Rn. It doesn't live on a sphere, right? So you saw that also this morning in this discussion with the covariance matrices. So the image, the outputs of these things.
Juan Pablo?
Yes.
There is a question.
Go ahead.
Stefano, sorry, Juan Pablo, just to understand, because that is something geometric, right? You are not saying anything about learning from the orbit. Are you? Because I don't understand how is it possible if you don't put a minimum assumption, I don't know, topological transitivity, something. I think it's purely geometric, right? You're saying that.
Absolutely. So if you want, this is a functional analytic statement, period.
Okay, but it doesn't tell you anything about concretely. I give you a chunk of orbit, how to build the approximations, right?
Well, in principle, if you have sufficient regularity and ergodicity.
Yeah, but it wasn't in the, no, because it wasn't in the statement, ergodicity. So I was wondering, I mean, it seemed a purely geometric thing.
I would agree with that. I would agree with that. Yeah. What I want to do is to build a proxy of the dynamical system with a neural network. It's as simple as that, right?
Okay.
So which will approximate, and then the way in which this proxy for the dynamical system and the original dynamical system will converge, and then they will coincide, is with respect to this topology. Okay,
okay, but you're not. It's more as a map or as a system. It's a space of systems, and not so much in terms of learning from the orbit. Not yet, at least, right?
I could agree with that. Yeah, I could agree with that.
Okay, thank you.
So,
sorry for the interruption.
No, more questions about what I said.
Yeah, Juan Pablo, maybe I can ask a question. I don't know why you say ergodicity. You do topological dynamics and suddenly you say ergodicity. Well, where does that come in?
I know. This is just to say that, yeah, I would need a measure. This, of course, would not work for RM. I am mixing things. All I wanted to say with that small remark is that, you see, there are two parts of the problem here. One has to do with the approximation problem, which is apparently solved by one of these universality theorems for neural networks, right? But then there is also another statistical learning problem, which has to do with how we will sample, what we will feed to the estimator at the time of finding the parameters of this neural paradigm, right? So all I wanted to say with that is that if the orbits that we are looking at, they are very specific. They are either periodic orbits, or they are just heteroclinic orbits, or they are just equilibria, then this will never work, right? Because we will not have enough enough structure, or if you want, we will not be able to. We are not giving to the neural network enough information to reconstruct the full dynamical system out of it. That's all I'm saying. But I'm not formulating a theorem or a result here.
Okay, I think this could be the start of a long discussion, but I will leave it here. Yeah, thank you.
Okay, but I hope that we have the discussion, Jeroen. So anyway, so if you just if we just follow the philosophy of what I just said, well, what happens with what I told you before? So suppose that we are not Euclidean, and that we have to accommodate dynamic structures on manifolds. So in that respect, there is a very recent paper by Anastasis Kratsios who intervened yesterday, and then he has this paper that was accepted recently in this NIPS conference. And then what he does, he's able to formulate a universality theorem for manifold valued, or if you want, with neural networks or that have as domain and codomain manifolds, right? And then the way you do it is, well, if you have a map that goes from a manifold M to another manifold M, so what you do is first you embed this manifold in a Euclidean space, and then, well, you run it through the neural network, and then you project it into this other manifold, right? This M and M in his theorem, they could be different. And there he has hypotheses that guarantee that universality here, which we have because of these Hornik-Sibenko theorems, guarantees to you the universality of this type of functions that you see in here. But there are hypotheses. So having injectivity here is not a problem, because we have all these Whitney, Nash embedding theorems. But when it comes to this projection, that is a true hypothesis, in the sense that, for example, in one of the possibilities that he proposes, you would need a covering projection, and not every manifold is covered by a Euclidean space, right? So there are topological abstractions for that. A classical theorem is that, for example, the homotopy group would have to be finitely generated, right? If of this manifold M, in order for that to be true. So so anyway, that's to tell you that something as simple as that is already not innocent. It's something that needs to be worked out, and to my knowledge, and as far as I can see, is only using Anastasis's theorem that could be done, right? So, but this is just for the case, unrealistic case, in which you have full access to the phase space. In general, what we have is lower dimensional observations. So so here now I'm going to be in a much more specific setup. I'm going to be on a compact manifold. The dynamical system is not going to be just a continuous map. It's going to be a diff2 map. So it's going to be C2, and it's going to be invertible with differentiable inverse, okay? So and the reason why I do that is because I want to show to you how Takens does something for us. And in order to do that, we need to have this regularity. So now I'm not observing, I'm not observing any more orbits in phase space. All I'm doing is I'm observing just one-dimensional. I have access only to one-dimensional observations of this dynamical system. So so then the question is, can we learn? Can we reconstruct a potentially high-dimensional dynamical system just out of that? Because if you just look at what first Joseph said the first day, or what Ludmila showed to you this morning, that all these Mackie glass forecasting tasks that we are always talking about, and all these classical papers by Jega and so on, where he was able to learn the attractor of this time delay differential equation, there what you are seeing is just observations of a high dimensional object, right? In the particular case of this TDD is an infinite dimensional object, because it's a functional differential equation, it's a time delay differential equation. So in that case, it is legitimate to pose the question, is this hopeless, or is this something that has a potential of being solved? So a positive answer in that sense would be what we obtain out of Takens' embedding theorem. So sorry for the dynamical systems people who know this code, but for those of you who are not in the field, so what Takens tells you is that if you have a dynamical system of the type that I just told you, so, and this compact manifold is finite dimensional, is q-dimensional, so actually just by using this, what we call now Takens delay map, which consists basically of taking assigning to a point in phase space, you assign to it, you just basically q+1 delayed observations of it. So you just run it to q+1 time steps, and then you just observe it. So this gives you an element of R q+1. So this map, we know that it is an embedding. Okay, embedding means that this thing is injective, and at the same time, the image of this map, when you look at it with the topology that you inherit from this M, and at the same time, when you look at it with the topology inherited from M, what you inherit in the image is going to coincide with the relative topology with respect to R2Q+1. Okay, so if you want, is a nice injection. So the topology that you obtain in the image is compatible with the topology, with the Euclidean topology that you have. We will see what are the dynamical implications that this has, but this is just an embedding, in the sense that you have this injection, the derivative is injective, you have this nice feature with the topology. But you see, if we can just take a compact manifold, which could be complicated, could be a Klein battle, right? Well, you end up with something which is Euclidean. This thing that we are seeing here is much better adapted to these neural networks that we have been seeing these days, for example, right? So why is this important from the point of view of learning? Is because, look, if you just undo, if you just look at the dynamics of this system on the compact manifold, and you just translate it to this Euclidean space, actually, this theorem gives you learnability, in the sense that we could use a neural network or polynomials or any universal approximating machine learning paradigm in order to learn it. And why is that so? Well, you see, if instead of looking at the dynamics of DM, we look at the dynamics of the embedded system, we see that just by the functional form of this delay embedding, actually the dynamics of the M, it gets translated into the dynamics of the Z's, right? So, well, if you just embed it with this delay, you just phi it, and then you just bring it back, as you see here in this F, well, what you see is that the dynamics in those Euclidean coordinates is basically just a shift, and then it's only the last term in this embedded coordinates that is going to have a dependence that we don't know of, right? As a function of the other coordinates in this of this embedded system. So, but you see, this is a function that in a Euclidean space, and at the same time is well behaved, because the dynamical system is differentiable. This embedding is an inversion, is differentiable too. The inverse is also differentiable. So actually, this little f that you see here is something that could be learned with a neural network. Okay, so this tells you that if you're in the particular situation of differentiable dynamics on a compact manifold, actually you could learn the dynamics of a dynamical system just by using a neural network. Is as simple as that. So if you want doing this Mackie glass task, then there is hope. This is all I'm trying to say with this little discussion. There are questions about what I just said.
No, in the chat, no.
Yeah, there are no questions in the chat.
Okay, very good. So let me tell you a couple of things, because you see, are we done, right? So I'm telling you, all we have to do is, well, there is this Takens delay embedding. So actually, all we need is a neural network in order to learn this little f. Okay. So and actually, this idea has been used for decades for forecasting, and well, you saw yesterday in Joseph's talk, there was the abstract that you will see in my talk too, in Jaeger's paper, where he talks about improving forecasting by I don't know how many orders of magnitude with respect to traditional techniques. The traditional techniques that Jaeger is talking about is nearest neckpurs on a Takens embedding. That's what he meant in his abstract, and that's how people have been doing these things for a long time. So, however, so if we want to learn the dynamics of the observations is one thing. If we want to learn the dynamical system itself, there is a problem, an added problem, which has to do with the fact that this embedding that you saw is just a topological conjugacy. It doesn't respect, in principle, any metric unless you do something else. So therefore, well, this embedding, it deforms things, so which is problematic for forecasting. Okay, so that's one thing. And then the second question is, what happens when you add noise in here? Because, well, we are doing dynamical systems. Ultimately, we want to do also stochastic processes. But even when you do dynamical systems, in realistic situations, there is noise, right? Either coming from the measurements or from the system itself. So, so in general, yeah, this complicates things, and it's not that the statement that you saw in here is not robust to noise, and actually the statement that the way I formulated in here, it would be false for a system in which you have noise, basically because the statement that we get out of tokens gives you a function that depends on the past. And well, as we saw this morning with this decomposition, if what we want to get out of it is say a stochastic process, there would be this martingale term that we are not able to get out of such a thing. Okay, so in principle, in a noisy situation, there is something else that needs to be done, and that can be either, well, you use a functional in there which is going to have noise by itself, so it's going to be a random system, or you need to add it ad hoc, either by doing bootstrapping like this morning, or a different trick, but just the way you formulated it is not true. And then the other thing that they wanted to bring up is the fact that here we have compactness. Tokens tells us something very important, and is that just by looking at the finite past of the observations, we are always able to account for the dynamics of these observations, right? So we only, this tokens map it maps into a finite Euclidean space, right? So this finite memory is something that has to do much with the compactness, and but in general it does not hold true, right? So you need an infinite memory in order to properly describe this dynamics. So here you have a very simple example in which, well, just take a linear system, right? And then could not be simpler. And then you just look at the time evolution of one of the coordinates, right? So if you want to give the evolution of one of the coordinates as a function of their past, unless you have this condition that you see here, linear algebraic condition, then in order to describe that, you will need to have information about the infinite past of the time evolution of these coordinates, right? So this is to motivate something that you have been seeing for 2 days now, which is the fact that we always work in this formalism that has to do with semi-infinite inputs, okay? So we are not working as we usually do in dynamical systems with flows, understanding the properties of flows. Here, we need to work with these semi-infinite inputs for the reason that I just told you, but also in order to be able to formulate some of the results that you saw this morning. So you see, there were this morning you had these consistency results that had to do with these concentration inequalities that give you bounds. So there, in order to formulate consistency, well, basically you need to take the sample size going to infinity, and that means going all the way to minus infinity. And therefore you need to be able to formulate your paradigms in such a way so that you can actually talk like that. And then we systematically work in a stationary regime. So we need to be able to to handle systems that are invariant with respect to these time shifts for any shift. So that's why, in any case, we need to be able to work with these semi-infinite inputs, and that creates dynamic difficulties, and at the same time functional analytical difficulties, because all of a sudden you are in the presence of an infinite dimensional input space, and well, you have to be careful with whatever shows up in there. So one of the things that one of the goals that we will have in here, and one of the reasons why we try to do things with this reservoir computing, is to come up with easily learnable paradigms that do this embedding better than tokens, right? And by better, what we mean is closer to a Nash embedding. So something that would respect the distances better, and therefore it would be more amenable to good performance in forecasting. So this is what we want. And then the two parts in this sentence are important. So easily learnable. That's why we get into this reservoir computing, in which you only want to have linear readouts, you only want to solve linear regressions, and then to corner all this basically non-linearity in the reservoir map. And then for the second part, we will see how we go about it. So, right. And then here goes what you saw already, which is these state space systems. So what we are going to be doing is just state space systems, which give you an input-output relationship. And then the only thing that makes this special and not super classical is that this F is going to be randomly generated, and that we impose, or in most cases, we will impose this H to be just linear. So then from the point of view of terminology, by now you are used to it. Here, instead of calling this XT state, we will call it reservoir state. That's why sometimes you will hear that term. The state equation will be the reservoir equation. But in any case, this is just terminology for something which is extremely well known. Something that was not mentioned up until now, and that I think is important, especially for people working on hardware, is the fact that you see, if you have this reservoir, you create it and it has certain universality properties. I'm not going to talk here about the strong and weak universality. That's something that would be for a different talk. But one of if this F is good for a whole family of applications, something that you could do, or that you could envision doing, is to run your inputs once through the reservoir, and then to train several outputs in order to achieve different tasks. So suppose that it's not how it was done this morning, but suppose that you want to have forecast of a given time series for tomorrow in 1 month, and of a combination of some of the inputs that you have in here, right? So something that you could do is, well, you run your inputs, your covariates, through this reservoir equation, and then you could train different linear readouts in order to obtain answers to those different questions that you may have about coded in the form of these different outputs, okay? So the reason why I say that this is important for people in hardware is because if you want to devise basically hardware which is energetically efficient, what is very expensive in hardware is non-linearities. So that's why if you can run your input through this reservoir equation only once, and then out of these states that you get that are coming out of this energetically expensive hardware, then it is much better than if you have to do it several times, right? So this multitasking is, I'm telling you, is very important for hardware purposes. So then once you just saw the equation, so there are two modalities of use that I will be telling you about, and that correspond to these two characterizations of dynamic processes that I gave you. So the first one is dynamical systems, and then the other one is going to be just input-output systems. So for dynamical systems is what we will call this modality of use number one. What you do is to come up with a autonomous system out of this state space system, which you want to work as a proxy of the dynamical system that you want to learn. And then the way you do it in practice is by following this recipe. And here I took the terminology of this paper by Verzelli, who I think was in the audience these days. So I say hi to him. And so they came up with this nice terminology. So first, what you do is you take your dynamical system, or if you want the observations of it, you run it through your state equation, through the reservoir equation, and then, well, what you do is you just solve a linear regression problem that, in general, non-linear, but usually, typically, is a linear regression that gives you an age that minimizes the mean square error between what you would obtain as t+1 values for this observation and what you obtain as the readout, okay? And then once you have done that, you can close the loop. That is, well, you just use that readout that you obtain in the second part. And then, well, whatever you obtain out of that readout, you re-inject it into the state equation in order to come up with an autonomous dynamical system that you hope will coincide with, in some form or fashion, with the dynamical system that you are trying to learn. So how reasonable is that? Is that working? Is because we have seen that in practice it works, or at least you were told that it works. So from the point of view of theoretical results, as far as I know, the most advanced result that we have so far is this paper that appeared this year in Neural Networks by Alan Hart and his supervisors in Bath. And then what they formulated is the so-called ESN approximation and training theorems. So I'm going to tell you how it goes. And then once I will introduce some terminology, we will revisit it and I will tell you more details on how it works. But what this theorem tells you is that by following this procedure that I just told you, if I give you a dynamical system that has these properties that you see in the hypothesis, that is, well, it has to be diff1, of course you have to be compact, then what they say is that there exists is not truly randomly generated, it's pseudo-randomly generated. I will tell you later what the hypothesis on how you construct this thing, but in any case, you can morally construct a randomly generated equistate network of the type that was used this morning, such that by the time that you close the loop and you come up, you construct with it a autonomous dynamical system. So it turns out that these two dynamical systems, that is the one that you want to learn, and then the one that you proxied with this equistate network, well, this equistate network, the autonomous dynamical system associated to it is going to have a normally hyperbolic attracting submanifold, and then you are going to have topological conjugacy between the one in phi and the one that comes with the CSN. Okay, so that's what they prove in that theorem, and if you want, that would be the closest that we have to a universality theorem within the realm of invertible dynamical systems on compact manifolds using reservoir computing, because even though this is not totally random, it's almost random. I will tell you later on what the restrictions here are. So and let me point out something, this ESN is driven by a generic observation of the dynamical system. So like in tokens, you take a generic one-dimensional observation of this dynamical system. Generic means generic in the C1 topology, okay? And in this, well, they need to be C2, but you take generic in the C1 topology, and then you drive this ESN with observations, okay? So it's very similar to tokens. You are driving this gentleman with one-dimensional observations. And nevertheless, you are able to construct a normally hyperbolic attracting submanifold, which is topologically conjugate to the phi that you are given. Okay, so this is truly learning, like we saw it in action in these applications that were pioneered by Herbert Jega and by Peter Tigno, and anyway, all these applications that we have heard these days. Okay, so let me give you examples of it, because you see we have been talking about these examples, but we haven't seen them so far in the school. So this is the system that Jega and Haas used in this 2004 paper in Science. So what they took is this time delay differential equation with a Mackey glass kernel, and then they chose parameters eta, gamma, and p, so that you would have chaos somehow. So they massage them so that the Lyapunov exponents would give you chaos. Okay, so and then they did exactly the program that I just told you. So the one that with this listening, this estimation, and then you run it autonomously, and that's how he forecasted the solutions of this differential equation. And well, this is something that I did on my MATLAB, just following the prescription of in Herbert's paper. So you see, what I do is I come up with a state space system like the one that you just saw, randomly generated and so on. And then what you see here is the superposition of what comes out of a very expensive Runge-Kutta 32 discretization of the differential equation, and the ESN the way you saw it before. So in this case, the error is practically zero all the way up to, I think, 3 Lyapunov times, something like that. So which corresponds in this particular discretization to 400 time steps. Then you see that, of course, this is chaotic. So at some point they are going to separate. And the other example that became very famous recently are this Kuramoto-Sivashinsky application. So what Ed Ott and his group did is they took this highly nonlinear PDE, right? And then they use the same program, right? So here you need to have the way in which it is discretized is explained in their paper, so I invite you to look at there, and then the same. So they were able to make it work well up to 8 Lyapunov times in their case. But what they have is really impressive in several ways. So let me show you pictures from their paper, and so what you have in there is what you have in here is in A and B. Again, is, I don't know, A is the actual solution using, again, a very expensive finite elements or whatever discretization. And then what you have downstairs in B is what comes out of the ESN. So you see, before it was ultimately Runge-Kutta is no big deal, but here, in order to simulate this PTE is relatively expensive. And you see, in order to do what you have in B, is much simpler because all you have to do is just a linear regression, right? So in the case of Mackie Glass, it was in dimension 1000. Here it may be 2,000 or 3,000, but still it's a linear regression. You press enter and the result comes out if you properly regularize. And in C and D, you see one minus the other. So you see that the approximation is very good. So something that I have heard Ed Art emphasize many times is that, you see, if you do forecasting for this PDE using the usual Taken stuff with nearest neighbors, what usually happens is that you forecast this thing, and at some point, well, the chaotic nature of the equation kicks in, and then of course the prediction is not good anymore, like it happens here too. However, notice that even when the error is already sizable, the approximation is not good anymore, something which is good is the fact that even though, for example, if you look at B, which is coming from the ESN, there is an error in here, this still looks like a solution of the PDE, you see? So of course, the prediction cannot go on well forever, but what this is telling you is that this has truly captured the dynamics that goes with the PDE. Okay, so that's something that for generative algorithms is extremely important, because actually you can mimic the qualitative behavior of the PDE. This does not just give you point forecast of what the PDE or the differential equation is going to do in the future. So, and here, this is another picture that comes from one of their papers, which is, I find, extremely impressive. So this is basically the Lyapunov spectrum of the PDE and of the original dynamical system, together with what is the spectrum of the ESM proxy that we built for it. So and the reason why I brought this up is because it links very well with what you saw before, what I told you before about symmetry preserving algorithms. You see, actually, this graph that you see here is not the Lyapunov spectrum of the original PDE, but of a small perturbation of it that breaks the underlying symmetries of this Kuramoto-Sivashinsky equation. What I'm trying to say is the following. Kuramoto-Sivashinsky is a physical equation, so it's Galilean invariant, all right? However, you construct at random an ESN, and this guy is not Galilean invariant, okay? It would be, generically is going to be false, right? So what they did in order to have the right fitting between one spectrum and the other is to perturb Kuramoto-Sivashinsky so that this symmetry that we cannot reproduce with the ESN disappears. However, what would be desirable is that, since we know that we are trying to model something which has this invariant, is to come up with an ESN that has these invariance properties by fiat, by construction, and then based on that, we keep going, right? So, but of course, that's an open problem, and that's something that I truly would like to study in detail and to work out. And then this is a movie that I truly find fascinating. So it's basically the ESN doing flames, right? So this is an animation that was done by Quantum Magazine because they publicized a lot these papers by Art. I find it beautiful, and I wanted to show it to you just in case you didn't see it before. Anyway, so let's go back to so modality 1 is for dynamical systems. Modality 2 is just input-output systems, right? So it's much closer to what you saw in the previous courses. So so here the C's, I'm not going to make this into an autonomous system. And what you have to think of this is like if it was a dynamical regression problem, right? So the C's, they are going to be dynamical covariates. So if you think of a macroeconomic GDP forecasting, right, in macroeconomics, so you could think of the C's as the time evolution of financial variables, inflation or whatever, and then the YT is well, how GDP evolves in time. That would be a typical that would be a typical situation in which you apply this paradigm in that sense. Another example is what you saw this morning with realized variance. Okay, and there is another possibility of in which this could be used in this modality is when you think of this as, say, time series model whose specification you don't have. So these CTs, for those of you who are into time series, this could be the innovations of a time series model. And then the YT could be just the output. So you could think of this as a calibration problem, right? If that's how you could encapsulate the functional that goes with this. So when we talk about that setup, again, before we were touching dynamical systems, of course, there are hundreds of years of science behind. Here is not hundreds of years, but at least 70 or 80. This is a state space system. So you see, trying to learn, trying to characterize an input-output system as something like this is by definition the central problem, one of the central problems in systems theory, right? This is the realization problem. So this is as classical as you can get in control theory and in systems theory, or also in filtering theory. So for those of you who are into volatility modeling in the audience, you know very well what I'm talking about. This XT is not just a state; it could be just an internal variable that you do not observe. And you are ultimately encoding unobservable factors that you may want or may not want to filter, depending on the complexity of this equation that you are using. So that's something that we have techniques for, and that's something that you may worry about. This is not the central problem that we are interested in. What we want is, I will have an input-output system. I will have input sequences, output sequences, and out of that, I want to learn using an object like this as an approximant, the relation between the inputs and the outputs. Totally empirical in the sense that I give you the inputs, the outputs, and then using these randomly generated Fs and these very simple readouts, I want to learn this input-output relation, this functional that links them both, okay? So a byproduct, if you want, a contribution of what we do in this context is some of the implications that you will see in these universality theorems that we will discuss in the second part, because we are going to be working all the time in this fading memory category that we already saw, and then you will see that as a byproduct of these universality theorems that we have, well, we cannot solve the realization problem in more generality than was that before, in the sense that you say, I give you an input-output problem, an input-output system, the realization problem is find me the functional that links them both, and tell me if there is a state space system that realizes, right? So that is something that we cannot improve, but with these universality theorems, something that we can say is that in the fading memory category, actually, well, maybe I will not be able to fully realize this input-output system that you are giving me, but at least I will be able to approximate it in the L infinity norm as accurately as I want, right? So these approximating theorems give you approximate solutions to the realization problem. So examples for this, I'm not going to stop in this because I don't know how much you are into empirics, but so you see this approach to things in the sense that you use either equistate networks, usually equistate networks, or well, after the work after the work that has been done on deep reservoir structures. And then I'm thinking of Claudio Gallicchio and your colleagues in Pisa. Well, there are many other applications that have been able to tackle that up until now. Well, the performance was not that impressive. So here you see a bunch of early applications. look, at the end, you will see that I have tons of references here. For those of you who are into empirics, I will flash them. They will get recorded and you can go there. I put these ones in here because of, well, for historical reasons, basically. There are applications to classification. Some of them are good, some of them are not so good. But in any case, all I'm trying to say with this different applications is that this is a technology that works. It's become part of the usual toolbox when it comes to forecasting. I am in the editorial board of one of these forecasting journals, and we regularly receive submissions that have to do with these techniques in order to improve various benchmarks that have been used for whatever problem you can imagine in engineering, in climate, in medical and physiological signal treatment. So here the sky is the limit. So this is just to tell you that this approach empirically works. So at least from the applied point of view is something that deserves to be studied. Anyway, so now before I tell you about a few theoretical results that I wanted to discuss with you, I need to recall for you these two properties that you saw this morning. So the first one is the equostate property, and the second one is this FMP, a fading memory property. So the way I'm going to present it, there is no universal way to present this. And I will tell you in a second what I mean by this. So the way I'm going to present it to you is that this equostate property is an existence property, in the sense that, you see, since we are working in this semi-infinite inputs situation, this is not anymore a forward-looking non-autonomous dynamical system in which I give you an initial state and an initial input, and then you can just run it and you will give me a time series of xt's. No, I'm going to give you a semi-infinite input towards minus infinity, and then it is not for sure that there will be a semi-infinite sequence of states that will satisfy this equation that you see here. When that happens is when we say that we have the equostate property. Okay, the importance of that situation is that in such a case, a state equation defines a filter. So you truly define an input-output system in this infinite dimensional setup. So which is going to be by construction causal and time invariant. So and then the other point that I wanted to make, because I have brought up the term non-autonomous dynamical systems. So you see, these filters that you have in here, they are time dependent. So this time invariance that you see here, since this state equation is time independent, the only non-autonomous feature that you have in here is coming from the dynamical nature of the inputs. But the system itself is first time invariant. It doesn't move in time, and second is deterministic. So here the C's, they could be realizations of stochastic processes, but so the only randomness that you would obtain in the outputs, it would come from the inputs, but not from the F. So this is not a random, non-autonomous dynamical system. So these are deterministic state space system, and so that's why I emphasize, I put the accent on this. So the other one is the fading memory property. So suppose that you have a system, this system has the ESP, and therefore you have a filter, right? So this filter, let's suppose that we get lucky, and then it maps inputs in L infinity to inputs in L infinity. So these are people with finite supremum, and what we do in order to define this fading memory property is we create a norm, right, which is this weighted norm. So the first thing that you need to choose is this weighting sequence, and what we define as this fading memory property is just continuity with respect to this space of inputs endowed with this norm. This norm, in which because of the presence of this waiting sequence, the inputs far in the past, they count less than those that just happened, right? So when you are fading memory property, when you are continuous with respect to this, with respect to the topology induced by this norm, then that means that well, that you behave like most econometric models behave, right? So all these models that we have seen this morning and others that we saw yesterday in Christa's presentation, they have that feature, right? When you are modeling the market, well, for sure that what happened in terms of volatility and returns yesterday and before is much more important as far as the volatility today as what happened 50 years ago, right? So this is one way to encode this feature. So, right, so this is the fading memory property. One easy way, well, actually the only easy way that we have to guarantee it is by requiring this contractivity property. So you assume that you have at least locally subsets in which this state equation is contractive on the state variable, right? So if you happen to be in such a situation, if you have closed subsets that are preserved by the state equation, well, you can prove that there are compact subsets of it such that in there you will have both the ESP and the FMP. Okay, so that's why in all these applications in the previous days you had all this and in some of the invited talks you had all these constraints on the spectral radius of the matrix of the equostate network and so on. That's in order to guarantee basically this equation or something related to it. This condition is sufficient but not necessary. Okay, and so that's something very important. That's something that has been studied by many people. So and then at the end you have several references on this fact. And then I wanted to make a link with a recent paper by these authors that you see here. So Cheney Ashwin, Peter Ashwin, Lorenzo Levy, and Ostelweide. And what they do is, well, they talk about multi-stability and what they call the eco index. And so here they have extremely nice examples in which what you just saw in the previous slide happens locally. So you have these different basins in which you have contractivity, and that gives you basically different solutions that are localized in this, basically let's call it like this, basin of contractivity of these state maps. So that's important for classification applications, as they point out in their paper. And then there is another link that I wanted to establish here that has to do with different ways to introduce ESP and FMP, because you see here I followed a definition that as it was given historically in the paper by Boyd and Chua in 1985, in which you start with a filter and then you impose continuity. However, you will see other papers in which actually they talk about this fading memory property as if it was the definition of the equostate property, right? So they use exchangeably these two terms, and it's because if you take a global approach to this, well, instead of going through filters, you go through what Gandhi Manjunath denominates input representing maps. And then there you don't need actually the existence of a filter, and nevertheless you can talk about the fading memory property, right? And there you are able to somehow establish some form of equivalence between these two types of behaviors. So so it is in this paper by Gandhi Manjunath, and then previously to that, actually this denomination that I just talked to you was introduced by him, by Peter Tigno and Herbert Jäger, in a proceedings paper where they make a very nice connection with non-autonomous dynamical systems, and which in my opinion deserves to be further explored. I know that Manjunath is working actively on it, and I follow very closely his papers, but still, I mean, yeah, more people coming from the non-autonomous dynamical systems arena should get involved, because I'm sure that there are interesting things that could be said in there. So, and then one more property that shows up in the literature as equivalent to what I just told you is this input forgetting property. So in other papers, you will see that this equostate property is defined as this feature that you see here. So you see, you take what this input forgetting property tells you is that, well, you start with two semi-infinite inputs, let's call it U and V, right? That takes you to two different points in this state space. And then, well, in this theorem, we assume that we are uniformly fading memory. And then if you have that property as I formulated it in my definition, then, well, if you keep feeding to these two different states the same input, at some point they start converging, right? Basically, because since you have this fading memory property, the filter forgets that it's coming from these two different inputs, U and V. Okay, so that's what we call the input forgetting property. So again, these three things, they're very much intertwined. From the mathematical point of view, this property appears as crucial in order to be able to prove some of the facts that you will see in a minute. And in particular, when we will be doing compactness, when we will be doing universality, is what gives you the compactness that you need in many situations, in many infinite dimensional situations where compactness is a rare commodity, in order to prove theorems. So right. So once I have given you this these ingredients, let me use it in order to show to you how another super classical concept in dynamical systems can help us understand how learnability is related, how learnability can be achieved. And that has to do with this notion of synchronization. So, okay. Again, there is a huge literature going back to the 80s, coming from both physicists and dynamical systems people, and this has to do with the interplay between state space systems and dynamical systems. So what these synchronizations are the following. Suppose that you take a dynamical system again on a compact manifold, right? And then you take its observations, so you create a CT, a sequence of inputs, out of observations of the orbits of this dynamical system, okay? So you use that as an input in a state space system, capital F, of exactly the same type as you saw before, okay? So we say that we have a generalized synchronization between this dynamical system and this state space system whenever there is a map such that actually the state that comes out of this state space system actually is a function not of the observations of the dynamical system, but of the state of the dynamical system. You see? So by definition, so this is the definition of generalized synchronization, is a map that takes me from the phase space of the dynamical system such that I can write the xt, which in principle is a function of the infinite past of the input, the CTs, that is the observations. Well, actually, there is a map that tells me that I can make it as a function not of the infinite past of the observations, but actually of the state of the dynamical system at that point in time. Okay, that's what I call a generalized synchronization. So in engineering terms, you say that you have a generalized synchronization when the state becomes a slave of the dynamical system that acts as a master. So this is a master-slave system, okay? So why is that important? Why am I telling you about this? Because in the same way in which we suspected before that out of tokens we could have learnability, actually the presence of injective synchronizations imply learnability. So that's something that there are two recent papers. One is by Suxin Lee and Lu and Bassett, and then the same paper by Verzelli, Alippi, and Lorenzo Livi that I cited before. So there are these two brand new papers that put the accent on this fact, which is in my opinion very important, because it's not only that implies learnability, as we discussed in the case of tokens, implies learnability in the reservoir computing sense. So you see, if you happen to have a generalized synchronization in the sense that I told you before, well, let's suppose that you inject the temporal trace coming from the observations of the dynamical system into this state space system, into this reservoir system, right? Well, just by the definition of what the generalized synchronization is, if you have injectivity, as I imposed as a hypothesis, then I can invert it, I can phi it, and then if you look at the observations of it, what you are going to obtain is exactly the value of this observation one time step into the future. So you see, by learning this function, I will have learned the dynamics of the observation of this dynamical system. But for that, I need two things. I need to be able to write the inverse. So that's why injectivity is so important. And then the other feature is that this needs to be sufficiently regular, because if this is a crazy map that is difficult to be approximated with most of the paradigms that we saw before, then we haven't gotten anywhere. So, and as you will see in a second, both points are an issue. So it's very beautiful to write this down and to say, well, we solved it, but you're going to see that there are major troubles to be overcome in order to apply what I just told you. But again, so that you see that this is extremely classical, let me show you one more connection with something that you already saw. So actually, we can write what we saw with tokens in the form of learning a dynamical system through a generalized synchronization. So just consider this linear system. It cannot get simpler than this, in which A is a lower shift matrix. So this is something, is all zeros with a bunch of ones under the main diagonal, right? And if you take that particular dynamical system, well, it turns out that the tokens map happens to be a generalized synchronization between the dynamical system that created it and this state space system that I gave you here. So here it's just like that. It's just a matter of sitting down and doing it. If you unwind the definitions that I gave you, it's just like that. So the tokens map is a synchronization for this little linear system. In this case, all these hypotheses that I told you that I need here in order to have learnability, I have them be out of tokens, right? Because I told you that I need to be able to talk about inverses, and I need this map to be sufficiently regular. Well, tokens tells me exactly that this map is an embedding, therefore is invertible as a map from the image into the into the phase space. And since it is an embedding, it's a differentiable embedding, I can write that map, and of course I will be able to learn it out of neural network again, or your favorite universal family. Okay, so so you see here, you see tokens written under the form of a learnability problem using reservoir computing. Here, not really reservoir computing because A is not randomly generated, but in any case, it's a state space system. And so if you want, the goal here would be, and actually that's what seems to happen, and actually that's what Hart et al. Seem to have proved with this theorem that I showed to you, is that, you see, by making the state equation more complicated, you can make the H much simpler. You see, in order to learn Maki glass or this Kuramoto-Sivashinsky, we didn't have to learn a neural network or to find a complicated function H. All we had to do was to run a linear regression. Why? Because all the nonlinearities of the system, they were cornered in the state equation. Here is not the same because, well, we want to use Takens map, but the idea that, or if you want, the reason why this seems to be working is because we have swapped the nonlinearities in the H, which even though they are static, they could be complicated, to nonlinearities in the state equation. So that's what this important sentence means. Right. So this, well, for the experts in the audience, they already know this, but I want to put some emphasis in something that I said before, and it's the fact that, you see, now we did this little example with Takens, in which by theorem, Takens is a difficult theorem, we had differentiability and we had invertibility. So that's something that you do not always have. Okay, so well, historically, as I told you before, this was introduced by these physicists, these generalized synchronizations. These are all papers in PRL, so in Physical Review Letters, and or Physical Review E. That's where these people, they mostly publish. And then these generalized synchronizations, they appear here in this Kokarev-Parlitz paper, where for the first time they made the link between the existence of these generalized synchronizations and this input forgetting property. So in their language, they call it asymptotic stability. But as I told you before, so very quickly, people realized, because people simulated the object, and then they saw that these generalized synchronizations that appear in these papers, they are actually fractal maps. And that's when they introduced this difference between weak synchronizations, when you don't have regularity, and strong synchronizations, when eventually you would have either continuity or differentiability. So Hunt and Ott, they wrote this paper, this one that you have in here, HOY 97, in which they give criteria under which you would have differentiability, and therefore you would not have these, between quotes, pathological behaviors. For those of us who think of fractal maps as non-desirable, even though there are many people who just think the opposite, they just love them, right? But from the point of learnability, is a handicap, right? Because it's going to be a challenge to tackle those. So, right. So we want regularity and we want injectivity. So let me address with you at least the regularity part, right? So injectivity is an issue. That's something that I'm telling you, in the case of Takens' theorem, it requires several pages of proofs. It involves very strongly compactness, and it's very complicated. It's truly quite something, that proof. So so in this particular case, what we can do is to prove that at least in the compact situation, first, the existence is always guaranteed by DCSP. So this is, if you want, nothing else but this Kokarev-Parlitz remark reformulated in our language with filters and so on. But then regularity, actually, if the manifold is compact and your dynamical systems are either homeomorphisms or diffeomorphisms, then you are going to have it, these synchronizations, they are going to be either continuous or C1 basically for free. you have to prove it, but they are always there. So who are these? The reason why I introduced these filters and this equal state property and so on is because I wanted to tell you who these synchronizations are, right? So how do you write synchronizations? Why do they exist? Well, because if you have a state space system that has the equal state property, I know that if I feed it with a temporal trace coming out of the semi-infinite observations of your dynamical system, I can associate to it a using the filter that comes with this ESP property, I can associate to it a filter value, right? Well, that filter value, which basically comes down to looking at the image by this functional of all the past of these observations, is actually the value that this synchronization would be, right? So if you have the ESP, this guy does exist, right? This synchronization does exist. And something that from the technical point of view is important is that this map, it satisfies a recursive equation. So actually you can use the state map in order to map your proposed synchronization map into another map. Actually, if this guy is a synchronization, well, this happens to be this synchronization actually happens to be a fixed point of this functional between maps. Okay, that's important because this existence, there are two existence theorems that you're going to see in a second, and then they follow out of basically Banach fixed point type theorems, and that's why this observation is important. So so let me give you a couple of results that tells you exactly what I told you before, right? So if your dynamical system is on a homeomorphism on a compact manifold, then this gentleman is going to be continuous. So you have continuous synchronizations. And then when you go to the differentiable case, you need to impose basically you need to satisfy a constraint. The first one is that you want that the operator norms of the partial derivatives with respect to the states are bounded by 1. So that's to impose basically local contractivity. And the other one, they need to be smaller than actually the operator norm of the derivative of the basically of the diffeomorphism that is giving you this dynamical system, right? So if you want this condition is so that the functional between synchronizations between functions whose fixed points are going to be the synchronizations, this is the condition that makes that into a contraction, and therefore that allows you to use Banach. Okay, so it's technically more complicated than the previous one. That's why we called it theorem and not just proposition, but is the way it is. And once you realize how it goes, is ultimately not that surprising. So this is to tell you that you see, if from the point of view of learning dynamical systems, right? If you have these synchronizations and they are sufficiently regular, and then I gave you situations where this regularity you have it, and then they are invertible, and that I did not give it to you because I don't know how to do it yet, then you have learnability just because you can do this trick that you saw before by fitting into a dynamical system that would satisfy this condition. And then that's it. You know that there is a readout that is going to give it to you. A third question that I didn't tell you is that if we are doing reservoir computing, this readout is supposed to be linear. So what would be the situation that would give us a readout that is linear? So that means, what is the situation which seems to be not that unrealistic, in which we could come up with a state equation such that this readout that we obtain out of the inverse of this synchronization composed with the phi and with the projection is actually linear. Because if we think of this Mackie glass forecasting task in this framework, that is what this is telling us. This complicated or supposedly complicated map, let me go back to it, that I need to learn is this H that you see here. This is what I need to learn. In the ESN case, this happens, this looks, if I take this H, if I take a linear approximation to this H, it does work. So somehow, somewhere, there is a theorem that should be telling us that by taking the F sufficiently rich, and that satisfies all these regularity hypotheses that you saw, we should be able to see that with linear H's, this either works or it almost works. Okay, because in practice that's what we are seeing. So so these are just thoughts that I throw at you. I hope that they are not trivial, right? But if they are, I can tell you. I don't know how to prove that, right? But to me, I'm telling you, to me, it looks like surprising. It looks like a mystery. And in the same way in which for input-output systems, we have ways to tackle the problem you saw during Joseph's talk, very inspiring reasons, very deep, both geometric and functional theoretical reasons why this is supposed to work. In this dynamical system situation, I still don't see it. So that's why, for those of you who are into dynamical systems in the audience, please have a look at this. And if it is trivial, just tell me. I will be able to sleep better. And if it is not, let's look at it together, because I think it's an important problem. So, right. And then let me conclude this part by revisiting this Hart et al. Theorem that I told you about. Because you see, I gave a statement, is sort of vague, but then I tell you how this theorem is formulated. And so the way they do it is you start with your dynamical system on a compact manifold. It's invertible, right? That's why you have this div1 here. And then what they do is the following thing. So they start with an ESN. It's a God-given ESN, which they assume has what they call a C1 embedding equistate map. So what they are assuming is that this ESN has a invertible embedding synchronization, right? So this is a big hypothesis that if you give me an ESN, I don't know how to test, okay? And they don't know either, because we work with Alan, and that's a question that haunts us all, because we don't know how to truly solve it. So and then the other condition that they impose is this condition that you saw in this theorem for C1 synchronizations that I showed to you before, right? So this is the main ingredient. This is the big hypothesis in their theorem. So they start with somebody who is already giving you this synchronization with the nice properties that we need. What this theorem does, it tells you how to randomize it, how to complete it with something random, such that first you still have an embedding, right? Generically on omega, on the observations that you are using to run this state space system, and then second, that has this property of this normally hyperbolic attractor that coincides with the one of the original system. Okay, so so it's a very nice theorem, but with a big hypothesis. Okay, but well, it's all that we can do so far. But in my opinion, at some point, yeah, we should be able to formulate or to have a better statement. But this is, in my opinion, well, with what we have with today's technology, this is the best we have.
I have a little question.
Stefan, yes.
So you mentioned the fact that in some sense for this approach, fractal functions are especially nasty somehow to learn. At the same time, in many cases, they just have the best possible self-similarity features that you want. So it's either you win or you lose. But if you win big in those cases. So maybe it's a matter of it's difficult to imagine that you have one approach that fits all, right? Even in this case, I mean, so this was a little bit of the comment. I mean, if you start aiming at something which I don't know. I mean, perhaps well, it was just this comment. I mean, that perhaps it depends more on the. I have the feeling that it may depend a lot on the approach that you take, that on what are the tools that you deploy. But because again, for example, iterative function systems. Iterative function systems should be something that you can learn in a relatively speedy way if you take the right approach. At least simple ones.
I may be too optimistic here, but I mean, let me ask you a question. So would it be too optimistic to think that by making this state equation very complicated, I can make this readout very simple? That's because you see, that's what we can do for input-output systems. You will see it in the second part when we do universality. There, by making the state equation complicated, I can manage to make always this H linear, right? Is that something that one could envision for in the dynamical system setup that I am telling you here about, or is just too naive? I mean, that's one more question that I ask everybody I find. So difficult to say, right?
Yeah, difficult to say. We among our participants, we have Jérôme Lam. But right. Jérôme, are you with us? Any opinion?
Please answer in emails.
Yeah, of course.
Very good. More questions?
I have a small question. But unfortunately, I missed this certain section, so my question may be silly. So when I joined, at one point shortly after, you mentioned learning, I think it was either H or phi with neural networks. But I had so actually I was thinking about a very related question, but by chance. But I think if you need the map to be an embedding, I'm not sure the networks would still be universal, because you have to constrain. Yeah, you have to constrain the connections enough so that they become injective, and the activations to be constrained. In that case, I don't know. No.
Well, I had that. I don't know if you were in the beginning, but I cited your theorem. So,
okay, cool.
so the audience is aware of the limitations, right? So indeed, you are right. But here you see, in this particular case of the embedding that goes with the generalized synchronization, be aware that there we are embedding into Euclidean, right? And by embedding, we mean that your topology is the relative topology with respect to the, So there, that does not pose a problem. We are not in the general situation that you have in your theorems, right? So and then the domain of this embedding is compact, so this is mapping into a compact.
Then it's proper and everything.
I mean, in comparison to what you do in your paper, this is truly Disneyland. This is much easier. Okay.
I don't know. Okay. Cool. Sorry, I think I missed the first part.
Thanks, Anastasis.
So did you impose some constraint on the boundedness of the input or?
Of the input?
So if I remember well, in the paper, so the reservoir computer
yeah,
the inferentiable, there are some technicalities.
Here you have it by construction, because here the boundedness in the input is related to the compactness of M.
Ah, okay.
You see, since M is compact, omega is continuous, the image of
No, because I didn't see in the statement before, so
right. No, here you are feeding the here you are feeding something always bounded and closed. Okay. So anyway, so I keep going.
Sure. Yes.
Oh, fine.
Please.
So please tell me 5 minutes before, because I don't, because of the full screen thing, I don't have a clock. And then I realized that I've been talking for 2 hours and I didn't even realize it. So please tell me 5 minutes. I know that I only have half an hour. I thought that I had to at least
maybe we start 10 minutes later, so maybe you can have 40 minutes. I think it's okay.
Okay, that would help. That would help, because
I don't think it's a problem. So
anyway, so welcome back. And well, as Julia, there are other questions that you would like to pose to me, because now I'm going to shift gears and it's going to be.
No, it was only that I didn't see the.
Okay.
So I didn't realize this stuff.
No, very good, very good. So look, now what I want to do is to show you some universality theorems for input-output systems. So here there are no dynamical systems anymore. What you have is Z's, so these inputs, and these Y's outputs, right? So what we want is to find families such that in this fading memory category that I showed to you before, would be able to uniformly approximate any fading memory filter, not necessarily a state space filter that you throw at me. Right, so it's a huge category, this fading memory category. So whatever you throw at me, I want to have something that is a state space system with linear readouts, because I want to preserve this reservoir computing property, and that in any case, and then I want to do it in several setups. So what you are going to see here is the deterministic setup, in the sense that the inputs are going to be just sequences. They are not going to be stochastic processes, basically, because if I do it stochastic, it would take me longer. There are all these prerequisites that I need to introduce. So then there are two ways to go about this. One is extremely classical. In order to obtain density, you just go via Stone-Weierstrass. So if you want most of the technical work that you need to basically carry out in this setup, is to make sure that you are in the hypothesis of this theorem. And then the other approach that you will see here is this internal approximation principle. So this is a very nice feature of working with the state space systems, which we proved, and that allows you to use universality properties for maps in order to prove the universality of filters. So the map that we are going to approximate, it will be the state space map, and then we will be able to see that there are conditions under which approximation of the state space map gives you an approximant for the filter. Okay, so this is what we call internal approximation. So for those of you who don't remember your Stone-Weierstrass, what this gentleman tells you is that whenever you have well, it's a theorem that could be formulated for topological vector spaces. But what this tells you is that whenever you have polynomial algebras defined on compact spaces, then you automatically have density. So in order to make it, to write it down in our language, what I'm going to find in here is families of functionals which will be basically invariant, or which will be closed under multiplication. And here is where going from filters to functionals is important, because you see, filters, I cannot multiply them together because they map into this infinite dimensional space of sequences. And while these functionals, which is basically the zero value of these filters, they can be multiplied together, right? Because they are in Rn. Well, here I put R so that we can have just multiplication, but if this was Rn, this would be the Hadamard product, just component-wise multiplication. So if I find families that satisfy this, then automatically we'll have universality. The only tricky feature here is the fact that you see these need to be functions that are defined on compacta. So why this space of inputs should be compact? So that's something that I need to explain to you, and that's where these two, what I call important lemmas, are about. You see, we said before that if we want to work with this fading memory property, we need to work with basically this Banach space. So this is the space of semi-infinite sequences. This is going to be the input, which actually diverge not faster than 1 divided by this W being this weighting sequence. Okay, so this is a Banach space. It includes L infinity, right? And then what we can think of is the main hypothesis that we are going to have in here is this uniformly boundedness of the input sequences, right? Why do we do that? Because, well, you can prove that actually the topology, the relative topology in this space of uniformly bounded sequences induced by this Banach, by this weighted norm, is actually just the product topology. Okay, so and once you have the product topology in here, automatically, well, there are two things that happen. Is by Tikhonov, since this is the product of compacta, even though this is infinite dimensional, you have compactness, right, in the product topology. And then the other thing is that since the topology that you are inducing in here is just the product topology, this has somehow forgotten the W that it is coming from, in the sense that any weighting sequence that you would give me, it would always induce this product topology. So the fading memory property, when you are in the presence of these uniformly bounded inputs, it becomes a topological property. It's not a norm or a metric property anymore. Okay, so so that's but as far as these theorems that we want to use is concerned, is this compactness that is so important, because without it we would not be able to do Stone-Weierstrass. Right, so let me just start with something extremely silly. Well, actually, if I give you just fading memory state space systems, then these people, they do form a polynomial algebra. Why? Because, well, if I multiply two of them, I obtain another state space filter where the readouts would be just the product, and the state space system, it would be just the product of the two. And then when I take a linear combination, the same thing happens with the state map, and then in order to get the readout, then you just take the linear combination of these two readouts. So as a consequence of this is what I told you before. So here you have something which is an approximated version of a universal realization theorem. So if you give me an element in this fading memory category, which is a huge category, well, I with this theorem, I cannot tell you if we can truly realize it as a state space system, but what I can tell you is that for sure there is a state space system that will approximate it as well as you want in this norm. Okay, so but actually this is too much. I mean, here I can give you a very silly statement, and that also has important implications. So you don't need an entire family of state space systems. Just take linear systems with polynomial readouts, right? So these people, if you just take the combinations that you saw in the previous theorem that makes it into a polynomial algebra, well, you see that, yeah, they do form a polynomial algebra, and therefore they are also universal. So, and if you push me, you can do even better than that, because you don't even need full matrices A. You can take A either diagonal or nilpotent, okay? Any of those two families, they are universal. So the nilpotent one is particularly interesting because you see in that situation, when you solve this, the system, and you unwind it, and you write the solution, which always exists if you have nilpotency, then what happens in there is that the resulting filter is going to have finite memory. So the output is going to depend only on a finite number of previous inputs. So this tells you one more feature, is that any fading memory filter can actually be approximated by a linear finite memory filter, right? So these are interesting dynamical features that at some point when you develop other theoretical results are interesting to have in your toolbox, no matter how simple to prove they are. A different story is when you want to have linear readouts. So you see, I told you, if we want to do reservoir computing, and that's what the entirety of Joseph's course was about, you want to have linear readouts, right? However, all these theorems that I gave you so far, is polynomial readouts, or they are not necessarily linear, right? So how can you prove using Stonefire-Strass the existence of a family like that? So here you have a situation in which continuous time and discrete time, they differ enormously. So this statement, for continuous time, it would be trivial. So the first time it was proved, it was in this Voigt and Chua paper in 1985 that I told you about. And there, you need very simple systems. So you just need bilinear systems. Bilinear systems with linear readouts are universal in the fading memory category when you are in continuous time. If you go discrete time, it's a totally different story. You need to introduce this family that Ludmila and I introduced, as if you want, as a basically non-homogeneous variant of something that long time ago Michel Flies and Normand Sirot introduced in their forward-looking state space systems. So we just needed to introduce a non-homogeneous version of that. So it's these people that you need to consider if you want to have universality in the category, in the fading memory category with linear readouts, okay? So who are these state affine systems? Well, this is almost like a linear system. However, the matrix that is multiplying your state is actually a polynomial on the inputs with matrix coefficients. Okay, so the P is something like this. This is what gives you this universality. You have trigonometric versions of it, which are in the spirit similar to what Hornig had in his first universality paper. So in any case, these are things that talk to each other. You can formulate relations that or conditions that make it have this equistate property and fading memory property, and then you can actually integrate them. So if you have the ESP, you have a unique solution. This is the solution for that system that you saw before, right? And then the reason why we are interested in them is because they do form an algebra, these people. It's a complicated polynomial algebra, just showing to you how the multiplication rule looks like. It's a bit convoluted. It involves several tensor products. I invite you to look at the paper. There is explaining in full detail. But you have this polynomial algebra condition. You have compactness because of this uniform boundedness in the inputs. Bingo, you just use Stonefire-Strass, you have a uniform approximation property with linear readouts, right? So you just take an arbitrary random, input-output system, fading memory, and then there is a SAS element that would give you that would be an approximant up to any epsilon that you give me. Let me bring a connection with Joseph's talk. So something that we proved in this paper that we wrote together is that Actually, these are the objects, these SAS objects, these randomly generated SAS objects are those that you obtain when basically you use as universal approximant Volterra series expansions, and then you just randomly project it with this Johnson-Lindenstrauss trick that he showed to us in his talk. So from the point of view, from that point of view, the one that you saw in Joseph's talk, this is a central object, this family. So here it appears just as a mere universal approximant. There it appears as a very canonical object that appears for these very nice geometric reasons as a random universal approximant in that category too. Right, so let me tell you about internal approximation. So forget about the first two parts because you already saw it, but this internal approximation is something extremely simple. Again, it works under contractivity hypothesis, and all you need to know is that if you give me an approximant for the state equation, right, then automatically you are approximating the corresponding filter, right? So then this gives us a strategy to come up with universality statements based on universality statements that we have for functions, in particular for neural networks, right? So if you remember the expression of the neural net of the equistate network, it looks like the cousin of a neural network, right? The only thing that differs from a neural network is the fact that you have this recurrent part. And but here actually you see it with your own hands that these are close relatives, because if you use this trick and you approximate a given state, any given state equation with a neural network, actually what you will get as an approximant at the end is an equistate network. It's not as simple as I tell you. Again, I invite you to look at the paper on how to fiddle around with the different parts of the neural network that show up in this approximation, because this is a map that depends on states and on inputs. So you have to be careful on how you do things, but that's how we achieve universality in that setup, okay? And that's the statement that we would get. And that's the one that Ludmila mentioned this morning, and the one that gives you this universality of equistate networks. So I'm not going to get into all these topics, and probably I will just mention things that we've done, and that well, I will put the emphasis, if you want, the things that I haven't said in here. So the first one is when it comes to universality with a stochastic input. So apart from what you saw, so there is these two papers, the one that I wrote with Ludmila and the other one that I wrote with Lucas, in which we do an extension of the statements that you just saw when the inputs would be basically stochastic processes, right? If you want to do things L infinity, then, well, there is no way around this uniform boundedness hypothesis that you saw. We have to replace it by this almost surely uniformly boundedness hypothesis, and then things basically work. There is a correspondence principle between the deterministic and the stochastic situation that works under extremely general hypothesis, and then you can formulate such a theorem with the same degree of basically generality that you saw in the previous results. When it comes to LP approximation, it's a different type of result. First is a different set of, it's different mathematics, right? So it's more stochastic calculus. And then the kind of universality that we obtain is weaker in the sense that I will explain to you now, which is in passing reminiscent of the situation with neural networks. So Hornig, he has this paper for LP approximation for neural networks. So if you want, again, this is a close relative of that result. And how is this different? You see, in the results that you saw so far, when we were talking about universality, well, you have this functional that links any uniformly bounded input and any uniformly bounded output, okay? And then if I give you an approximant, this approximant, it will be good for any input, right? However, when we go to LP approximation, the universality result is formulated with respect to the LP norm associated to the law of a given input. So if you want the universality result that you are going to obtain is associated to that particular stochastic process. So this is universality with respect to, I say it again, the norm determined by basically the law of the input. The advantage that this has is that, well, we don't need to have the fit-in memory property anymore. All we need is a p-integrability property, meaning that all you require is what comes out of this reservoir computer is p-integrable, so that we can talk about the LP norm. Okay, so that's all. Then you see, in all these results that you saw, is not truly reservoir computing, in the sense that I'm just telling you that there are ESNs and that there are SAS that behave as universal approximants, but I'm not telling you that they are randomly generated. If you want that, you need to go to these other papers that you have in front of you, and which do exactly that. They do that from two points of view. First, there is the part that has to do with the approximation error. So you honestly show that they are universal approximants, but it's more than that. Especially this one that you have in this preprint in the archive, this approximation bounds for random neural networks. This gives you actual bounds reminiscent of these Maury bounds that Joseph showed to us in the first day, but for reservoir computing, right? And this time around, these are randomly generated reservoir computers. It's not any reservoir computer, admittedly. It's done in this particular paper only for ESNs. So this is an ESN paper, which in passing proves as a prerequisite something that has been out in the literature for many years, which is, well, what we like to think is a nicely rigorous from the high quality stochastic analysis point of view, proof for the universality of something called extreme learning machines. So you see, this reservoir computing paradigm, it has inherited this randomness out of random neural networks. So this was introduced by these people in Singapore, like already 15 years ago, Wang Binghuan. It was very famous when they introduced it, because there are several situations in engineering where you have sensors and you need online learning, where you do not want to have to do back propagation on a neural network in order to have decent performance. So they came up with this idea, and but of course they are not mathematicians, so their interest was not truly proving rigorously that this actually had a raison d'etre, as the French would say. But so for a long time, rigorous proofs of why that happens and having bounds for those have been pending in the literature. So we believe that we have done something like that, and we believe that it will be useful for the community. And then there are two more topics that I wanted to tell you about, and is dimension reduction. So something that we didn't mention much during these 2 days is the fact that in order to come up with these applications, probably not so much in what Ludmila did this morning, but when it comes to dynamical systems, all these Maki, Glass, Kuramoto, Sivashinsky, and others that you see in the literature, they require huge networks, okay? They're usually sparse, they are randomly generated, whatever you want, but they are big. So so you see, having had a certain exposure to control theory and to state space systems and to dimensional reduction techniques, there is the traditional technique that people use in in that kind of systems, which is canonicalization, right? So you don't want to have state space systems or reservoir systems that contain states that are never visited by the dynamics, or that are not efficient, in the sense that you see that there could be state situations that, from the point of view of observation, that is, once you pair them with a readout, they give you something which is indistinguishable. So you want to, when you avoid this undistinguishability and you have full reachability, is when you say that you have a canonical representation. So there is this notion of canonical reservoir computer that is basically just redoing what has been done in the state space systems, but this time around by taking into consideration these semi-infinite inputs and this backwards in time approach that needs to be worked out in here. So, and then a totally different, but totally orthogonal way to do things is these random projections that we worked out in this paper that we did with Joseph, Christa, Lucas, and Ludmila, and Joseph, and where we do exactly what Joseph explained to you yesterday in continuous time. Here we started from a pure discrete time approach. We took a universal paradigm, is these Volterra series expansions, which are close relatives to these signatures that he was telling us about. And well, you randomly project them, and then what you obtain is one of these SAS with random coefficients that we saw 10 minutes ago. So I have other things that I could tell you, but I think that I'm going to stop here, because it's material that I will put in. It has to do with historical considerations, and it has to do also with physical realizations. So there are things. These are things that you can look at them by yourself. I will give Julia the slides, and at the end there is well, for those of you who will not download them, let me just flash the references so that they get recorded. And but I guess that we can do that while we go for questions. So thanks for your attention, and yeah, I'm taking your questions.
Thank you very much, Juan Pablo, for the inspiring talk. Are there questions? We had some questions in the first part, but more are welcome, of course.
It's Friday evening.
Yeah. Well.
Guys, if there are no questions, so you know, I'm the last speaker. So so what I would like is, I think on behalf of all the participants and the other speakers, to thank you guys for this, because we just can't imagine how much work you have to put into this, and I don't know about there, but here well, the administration in Switzerland is always wonderful, but I have seen that you know, with the pandemics, things got very complicated, and there are many things that were trivial before that became extremely challenging now. So I don't even want to imagine how it is in Italy, because it will be like everywhere else. So yeah, thank you very much for organizing this, and for your perseverance in keeping this up.
Thank you to you. I don't know. There's also a comment by Benodian. I don't know, Stefano, do you want to say something to close the meeting? To say goodbye?
Yeah, of course I can say goodbye. No, the only thing I can say is that the meeting was excellent, and it was a consolation to the regret that we couldn't make it physically in Pisa. And I hope, well, we all hope that the situation changes soon, and let's try to convene in Pisa again, maybe in a year from now or something. Anyhow, when things will become a little bit more manageable and more predictable, at least from this point of view.
We call it first edition of the school, so there will be a second edition, I guess.
Exactly. This is precisely what I meant. And it's amazing how much material you have been able to cover in just 2 days, and what a broad panorama you have been giving to us. I think you did a really great job. Thanks a lot to all the 4 speakers. So.
Yeah.
I wanted to say something because I got a message from Jeroen. So he apologizes. He had.
It's my fault. It's my fault. Actually, I regret. I mean, I was clearly not following etiquette. I mean, one should never do what I did. So, Jerome, my full apologies. I was completely naive.
So he was booked for another meeting, and so anyway,
of course.
I think that I should, yeah. So he had a good excuse.
So thank you again.
Thank you, everyone. And,
Thanks a lot for organizing this. This was really nice. I mean, despite the fact that we cannot be in Pisa, I mean, somehow you see people and there is this interaction. It feels lively. Yeah, it was very lively. There are other conferences when things go much more, I would say, on a very boring side, and this was definitely not the case. So it was very nice. It was very well organized. So thanks a lot for that.
Yeah, I can also fully agree only with Ludmila and from Pablo. Thanks again for organizing this and for all the discussions we had.
To you.
Well, it's a pity that Zoom doesn't include the facility to drink something together. So I hope they will think and fix this shortcoming. And, thanks a lot.
Very good.
Okay.
Bye.
See you next time.
Bye, people.
Bye.
Bye.
Bye, everybody. Thank you very much.
Bye.
Bye. Thank you.